Hi, my name is Anton, and welcome to the course Calculus and Optimization for Machine Learning from High School of Economics. Our course primarily aims to build up the necessary mathematical base for data analysis and machine learning. Bearing that in mind, here comes one of the most essential modern-day motivations for studying calculus, the idea of optimization. In various machine learning tasks, we find ourselves in position of initial assumption of the model, the function trying to mimic the rule that produces given output from given input, for example, distinguish between cat and dog in the picture, with a set of parameters. If we come up with the idea of model's error, then it is essential to think about the best set of parameters in order to minimize it, or in other words, train the function. This optimization procedure, even numerically, is rather complicated and thus requires extensive mathematical understanding of underlying concepts. In doing so, it becomes pretty clear that in our day-to-day life we are surrounded by impressively comprehensive functions. For example, aforementioned composite error is a prediction of some algorithm, dependable sometimes on millions of parameters. Tomorrow price in the stock markets dependable on various indexes of the market today and sometimes one's Twitter feed, or the average ocean level as a function of sometimes missing measurements in numerous geographical locations. All this implies that we are in desperate need of the idea of proper approximations with simpler functions with the same properties as the initial complex ones. For example, finding linear approximation to define the slope of the function as instantaneous speed of change. Our course pursues these goals by introducing consequently basic functions concept, the idea of limits, then proceeding with linear approximations and integrals, thus building up the base for almighty optimization procedure. In contradiction with usual calculus courses, we opt to embrace that in order to bring the discussed material to real-life tasks, we need to simultaneously discuss functions of single and several variables. All themes include extensive non-mandatory practical quizzes and interactive plots used in our slides for you to play with, and thus understand the concept we are talking about more clearly. As a final project, we propose a Python programming task on classical optimizational problem from machine learning. Hope to see you soon in the first week. Hi! Welcome to the very first week of the calculus course. Today we are going to lay some common ground and discuss some widely known terms such as functions, mappings, numerical sites, introduce ourselves to the concept of functions graph and discuss basic functions graph transitions. Also, we are going to finish with the first our true calculus concept here, the limits of the sequence. During our week you will see various illustrations in our slides, and you will be able to play with it as interactive attachments to our tasks. Also, you will find some non-mandatory reading materials attached to this week. You can either read them or just ignore them, depends on how brave you are feeling today. See you in the following video. In order to properly discuss actually any mathematical material, we need to define what is a set and what is a numerical set in particular. Firstly, what we are aiming at? We are aiming at the definition of the function itself, or one or several variables. It's our main target during our calculus course. But in order to properly define it, we need to start with two things: the definition of set and the definition of mapping. Basically, a set well, commonly it's called a non-definable or fundamental thing, but we are gonna say that it's some kind of collection, some entity which collects some objects, right? There are several key features of the set. Firstly, we assume that the object either belong to the set or do not belong. We don't count a number of times that a particular object belongs to the set. Thus, basically, one can say that one object could belong to the set or can be included in the set only one time. Okay, and secondly, I'm gonna stress out that there is no order on the elements of the set. So basically, if you are introducing some order, and if you just want to introduce some essential order, and you're looking, for example, at the set of natural numbers or just some numbers at all, you can consider that they can just tell what number is greater than the other. But it is not the case of the set. Set does not know anything about order. Set only knows the answer to the question, does this very object belong to this very set? So something about notations. Firstly, we are going to say that we are going to denote our sets with capital letters, such as written on the slide, and we are gonna say that some element belong to the set. We're gonna denote set with an ordinary element of the set is an ordinary letter, and the state of belongings we are gonna mark with the following symbol. The negative belonging, the fact that set doesn't have this very element, will be denoted with a crossed symbol. So, another thing that I was mentioning when we are talking about sets is subsets. Actually, basically, a subset is a set of elements of the given set. Well, it's kind of an easy thing to imagine. Assume that you're looking at a set. I'm gonna display it with this circle. It's called a Venn diagram. For example, we have the set X, and we have some number of elements here. I'm not just going even to write it out. Assume that it's a set of points on the plane, for example, and some group of points here, some set of points here, which all belong to our X set, but not necessarily all points that belong to our X set. It's called a subset of set X, which is, well, we're going to denote it as Y. Notation here comes something like that. Y is subset of X. Well, obviously, X is always a subset of X. There is also such idea as an empty set which contains nothing, no element in the set. And there is a common understanding that empty set is a subset of any possible set. Or, for example, just if you consider the set of all the good days of the week, Saturday and Sunday are almost definitely subset of this very set, right? Okay, so we are going to speak about during our course mostly about numerical sets, and there are quite a lot famous numerical sets, and you surely know a lot of them already, but I'm going to remind you just to make sure that we're all on the same page. Firstly, we are going to say that there is natural numbers, numbers which are a result of counting some object. For example, I'm going to say that natural numbers are the result of counting oranges. It's kind of tricky because if you actually are looking at serious math here, a proper defining of natural numbers which do not involve the word oranges here becomes pretty vague and pretty complicated, and largely depends on the idea of sets and operations within our cardinal numbers here. But for the sake of our course, we're going to just say that we have natural numbers and everybody understands what it is. So then we're going to proceed with integer numbers, or z set here, which is basically natural numbers with 0 and inverse natural numbers. The idea basically is that if we have a set of natural numbers, we have an operation of summation, just a simple old school plus, then we are going to say that we have to have a neutral element, the element we can add to another one, and the result is still the same. This is a 0, right? And inverse elements, for example, the element we should add to element 1 to get as a result a neutral element, which is obviously -1. Okay, then we have our rational numbers, and that's the point where we're going to stop. Rational numbers are numbers depicted by a fraction, where the numerator is actually an integer number, and the denominator is natural number in order to avoid division by 0, which is prohibited, as you, I'm sure, already know. So, you need to understand that while we are talking about rational numbers, this is quite a large set which contains a lot of elements. For example, element 1 divided by 9 is actually a rational number. And you need to not be embarrassed by the fact that it is also can be written as 0.1 in period, right? Well, just a non-ending notation of ones. It doesn't have anything in particular frightening, because it's just a simple 1 divided by 9, and this is casual rational number. Non-casual case of these infinite decimal fractions, like here, for example, like when you remember pi, or for example square root of 2, and this goes on and goes on. Non-systematic infinite decimal fractions are called real numbers. Actually, all the set of systematic or non-systematic decimal fractions with infinite notation are called real numbers, in order to simplify that. The idea here is that whilst we are talking that integer numbers are closed in terms of the variation plus the summation, right? The rational numbers and real numbers are closed for plus, minus, division, multiplication, well, all the arithmetic operations we've actually know. But the question here is, okay, but what's the difference actually between rational numbers and real numbers? First of all, there is a structural difference which states the following, that real numbers are much more full than rational numbers, and the proper definition of it and the idea why it is so crucially important are included in our first additional materials to the week. You can read it if you want it. But to understand it, I'm going to give you some basic example here, which is sort of widely known. Let's just prove for a second that square root out of 2 is non-rational. So, in order to do it, we are going to assume that it actually is rational. We are going to assume the opposite. So, if square root out of 2 is rational, then it is some kind of fraction with integer denominator and natural denominator, right? So what are we gonna do? We're gonna put left and right side in the power of 2 simultaneously. Thus we get 2 equals to m squared divided by n squared, or just by simple writing it, 2n squared equals to m squared. And so goes our idea. Since the left side is obviously even, you can divide it by 2 without any remainder. Thus, the right side is also even, right? But if the square of some integer number is even, thus this number itself is also even. So basically we can rewrite it in a manner that m equals to 2k, where k is some other integer number, right? So if we substitute in our relation here m with our 2k, we get as a result 2n squared equals to 4k squared, or in other words, we get n squared equals to 2k squared, right? It kind of reminds us of the very relation we started with, but from now we're gonna say that our right part is even, thus our left part is even too, thus n is also should be even. Okay, and so on and so on. If we just gonna substitute n with our, for example, 2t, where t is some other integer number here, then we're gonna say that k is even, right? Then we're gonna say that t is even. Then we're gonna introduce another variable which is also even, and so on and so on. As a result, we're gonna say what? That our m nominator and n denominator should be even, should be divided by any possible power of 2, right? Which is kind of not the case for any integer or natural number, right? You can divide an integer or natural number by 2 only a finite number of times. So this relation doesn't hold, our proposition doesn't hold, and square root out of 2 is not actually a rational number. So why is it so crucially important? For example, assume the following. Here I'm going to just introduce you to some pretty basic idea. Assume you are gonna to have a rule. You're gonna have, well, for example, our just all the real numbers drawn on our real line here, right? All the real numbers here, and we are gonna divide this straight line in two sets. Our first set will be negative numbers and, for example, numbers squared less than 2. Okay, that will be our first set, and our second set will be positive, well, with square greater than 2. That will be our second set, right? So if we are gonna say that that's what we are looking at, basically we are gonna divide all rational numbers into either first set or second set, right? But in between them there will be no actually rational number, right? There is no divider in between them. Because an essential divider here is square root of 2, but square root of 2 we've just proved that is non-rational. But as for real numbers, you can always find some real number as a divider between such two separations, right? Those are called the Dedekind separations or the Dedekind interactions here, and that's basically how real numbers are defined, and that's the reason why are actually heavily used. Okay, so let's proceed to our video and discuss the order of mappings. Now we know the concept of numerical set. So let us discuss the idea of mappings in between two sets. Basically, when we are talking about mappings, we are talking about the relation between two sets. First, let's assume that we have some set x and some set y, and we have some rule which gonna say that if we have some element in the set x, right over here, then we had corresponding element in the set y. Okay. Firstly, you should understand that when we are saying that there is a mapping, we are somehow ordering the sets. We are ordering that there is a mapping from x to y. This arrow has only one pointer here, right? So basically this idea relates to the following. We are gonna define some kind of relation from x to y. For example, from, I don't know, the set of all people to the set, for example, of all favorite ice cream flavors. So that's some kind of other basic pillar here, which we are going to build on all our functions theory and understanding of sequences, multivariate functions, and all the other things. And to finish our basic introduction here, we are going to stop on some logic notation. Whilst we are talking about various definitions in calculus, well, or any other math actually, we are gonna heavily use two basic phrases: for all and exists. In order to avoid such extensive notation or extensive definitions, there are always or usually changed by the following quantifiers, symbols A inverted and E capital inverted, which basically means for all and exists respectively. So I'm gonna just stress out that the idea is the follows. If you are in need of the opposite of your definition or the opposite of your statement, you're gonna basically say that if you have some kind of statement A and you're gonna say not A, that's quite easy in case of these two quantifiers, because the idea of not for all is basically exists at least one which is do not satisfy, right? And the idea not exists basically means that all elements basically contradicts what we are gonna say, right? So it's kind of a nice trick when you need to automatically rewrite your definition or your statement to tell the opposite. We are gonna practice it while we are talking about, for example, our definition of the limit of the sequence later. Now we're ready to speak about the function itself. So, what do we have in order to define a function? We have two sets, x and y, and we have some mapping, we are gonna call it f, from x to y. That's kind of picture we've already seen, right? This mapping is called functional or a function. If basically it only associates the element of x set with only one element of y set. Okay, so the idea here is follows. We are gonna start your nice arrow from the element of x set and gonna lead to some element of y set. But the key point here is that there is no element in the point text where two arrows starts from. Basically, this old Russian fairy tale idea when a warrior starts into the cross of three streets and some stone gonna tell where to go to find, I don't know, an enemy or love or just treasure, isn't working for functions. There is no such thing as such crossroads, okay? For only one element of an X set, not more than one starting arrow. Okay, so let us proceed with some other basic definitions. Firstly, we're gonna say that the set of x is called domain, functions domain, and the set of y's is called functions codomain. Basically, that are sets of arguments, arguments, and set of functions values. Well, let us just see this example. I'm gonna say that there are two functions which are basically defined by this very table. Their domain is the set of 0, 1, 2, 3, and their values are written in the second row around here, right? So basically, the top table here defines the function, right? Because for one input, there is only one output, right? Either it's a number or just some kind of fruit, whatsoever. Okay, but for the second table, it's kind of problematic because, as you see, for input 0, you can get either 1 or 0, so basically it's not a functional mapping after all. Okay, so that's the first one is a function, and the second one, well, is a bad thing. Okay, so let us proceed with some other basic ideas of how to describe a function. Firstly, you can describe a function by the very table of values, which is kind of in handy when your function has a finite or maybe finite small domain, right? Just the same thing that I've recently done on the previous example, right? Also, we are kind of familiar with the idea that function can be described by the formula, something like that. Okay, yeah, I'm going to frighten you quite a lot during this course, so just meet your first nightmare. But of course, when we're speaking about algebraic description of a function, the first thing you're going to understand that basically it's quite a good quantitative description of a function, right? Because you are not losing any quantitative information. You can actually get a value of function at a certain point if it is in the domain, right? But in order to get some qualitative information about our function, just for example, the idea that it is increasing, or it is kind of a circle, or it's kind of smooth, or it's kind of, I don't know, has a lot of maximas and minimas, or something like that, it's kind of trippy thing, right? Because we don't know how this very function actually looks like and how it behaves like. The opposite idea about this function, which kind of basically stresses out on the idea of qualitative analysis, is graphical description. And in order to understand what it is, we are going to define what function graphs is. So what's function graph? Basically, it's a certain curve on a plane. You are just all familiar with it. You need to draw axis, and then you're gonna to draw some kind of nice curve, and that's our functions graph. Formally, we're gonna say that that's the set of all points on the plane such as x, f at x, where x is in functional domain, right? So if you're looking at curve, you're just looking at a set, quite large set, infinite set of points just drawn on the plane out loud. So let us take a moment here and just decide by the functions graph or functions node graph whether or not the mapping we're talking here is functional. Let us assume the following example. Let this be some curve on a plane, right? I'm talking about the blue circle here. Whether or not this curve is functions graph, it's quite easy to say, right? Because if you consider, for example, this argument's value, then there is two possible values of the function, right? A positive one and a negative one. Thus, this very curve shouldn't be the graph of the function. For the first notice, I'm gonna write the equation of the circle right here just to show you how it looks like. By the second of all, we are going to just stress out what is the main idea of the functional mapping and its graph. Basically, the idea is that if you have some point x, then you should have only one intersection of functions graph and this vertical line, okay? Well, or maybe zero function is not defined at this very point, but it's kind of obvious. So let us try to somehow change between algebraic notation and graphical notation. Firstly, let us meet this very function. This is function defined piecewise. Basically, this term means that we have three parts of the argument set less than -1, from -1 to 1, and greater than 1. On each function is set with some just pretty simple expression, right? So we're gonna draw it. Secondly, we are going to speak about its domain, its codomain, and its support, or the set of all arguments with non-zero value. I'm going to cheat on you here and use a computer to draw a function to draw at least one nice picture during this lecture. Okay. So that's basically our functions graph. This is our -1 switch, right? This is our 1 switch. And we should point something out here, because firstly, we're going to say that at this very end function does not have the value corresponds to the absolute value of x. Instead, it has the value which coincides with the idea of 1 minus x, right? Same applies for this very point. There is no 1 minus x, but there is 1 x squared divided by 5, right? So, let us discuss something about functions domain, codomain, and support here. Firstly, what is functions domain? What is the number of arguments function is defined? It's quite easily can be seen that basically it is all the values, because all the real values. So our domain, we are going to denote this with a capital D. Is usually, it's quite common notation, equals to basically all real numbers, right? So as for its codomain, or as for functions range, there is another term here, we're gonna say that it is all the y's that functions actually take, right? So the idea how to check whether or not, for example, some value, real value, for example, like 5, is in the codomain, you're going to just draw a horizontal line and see whether or not it intersects the function's graph. Oh, okay, that intersects, that's 5 in the codomain or 5 is in range. You can easily see if you just take a projection onwards to y-axis that for all let us see, for all positive, right? There is no zero value. For all positive y's, there is some argument which results into this value. So basically we're going to write that it is array starting from non-including 0 up to the plus infinity. And as for the support, it's quite easy. There is only one zero value. Oh, no, there is no zero value, right? Support is just all the real numbers. So that's basically the idea of transition from algebraic to graphical, from graphical to algebraic notations, and finding all possible terms that we've defined in around here. See you in the following video. So, here is the trick. When we are thinking about algebraically defined functions, we are always thinking about elementary functions. Basically, that's the class of functions which is a result of some operations with some basic units. It's kind of intimidating when I'm saying to you that every function you can actually think about defined by the formula is called elementary. But it's just a term and you should not actually care about this very meaning. Okay? So, what are we talking about when we're talking about elementary functions? Firstly, we're talking about some basic units, some stones we are going to build our house wall with, and some allowed operations. Okay, let us start with our basic units. Well, basic elementary functions are just our essential functions that we all know about. For example, it's constant, it's powers of x, it's exponential functions, logarithmic functions, trigonometric, and advanced geometric functions, right? So let us just briefly speak about each of these. Firstly, let us assume that for constant you're quite skilled in terms of functions which are always the same value. But let us just take a look, for example, at a function which is power of x. For example, if we are looking at a function y equals to x, then we're looking at a function which is determined at all real numbers, and it's codomain on real numbers, obviously, but we are taking into consideration x squared, then its codomain changes, right? And if we are taking into consideration square root out of x, then its domain just turns into the all non-negative numbers. And if we are looking at x minus 1/2, then we are looking only on positive domain, right? So when you are looking at powers of x, you should be extremely cautious about which power it is and what additional restrictions it lays on our functions domain and codomain respectively. So, as for other stuff, I'm going to stress out that the exponent in exponential function, the value a, should be always positive in order to avoid taking a square root out of negative number. Same applies for the base of the logarithm. Just to make sure that we are all on the same page. Another restriction for the logarithm is that its base can be all positive numbers except the number 1, because if you are imagining what is the power of 1 in order to get x, you'll either be confused because you could not get x as a result of taking 1 to some power, or there is too much powers in order to get this very x, which is 1, right? Basically, you can put a 1 in any power and get 1 as a result. Okay, So that's our basic blocks, that's our stones for the wall. So how gonna build this actual wall? We're gonna build this actual wall by our arithmetic operations, right? So we got our addition, our difference, multiplication, and division, right? And so the idea here is that whilst applying these operations to the pair of elementary functions, we still get elementary function unless its domain, codomain, support, and whatsoever. Well, functions change, right? But the very idea is that they are still quite simple or just elementary remains, right? So, for example, if we consider polynomial functions towards n, for example, p n towards x, written here, right, as the sum of powers of x multiplied by constant numbers, right? So basically the idea here is that we get there just by finite number of arithmetic operations, multiplications between constant and powers of x, and addition the results with each other, right? So this polynomial function is still an elementary. So let us consider another operation which is allowed in elementary class in order to get another elementary function, which is a composition of functions, or producing a composite function. Basically, the idea here is as follows. Assume that we have not two but three number sets, numerical sets, x, y, and z. And we have two functions. One function is a mapping from x to y, another function is a function from y to z. Thus, applying these two functions consequently, we get some mapping from x set to z set, right? This mapping is called the composition of two functions, or the composite function. Notation here with this little white circle, or with this brackets included system. So basically idea here is that firstly you apply your function f to the argument, and then you apply your function g to the value of the function f. One should say that the domain of function g should be always included into the domain, to the codomain of the function f, right? In order for the function f to return all the values which is allowed to be the argument of the function g. So the thing here is you need to always remember about functions composition that the order of composition is important. And whilst it's kind of tricky to understand when we are looking at the tables of functions, it's quite easy to understand when we are looking at, for example, algebraic notations of functions. Consider two functions here. As for function f, we are going to use exponent of x, and for the function g, we are going to use, for example, x squared. Right? So if we are considering the composition of g and f in this very order, first you apply f, then you apply g. Then you need to basically calculate the following: exponent of x, then squared, which is simply exponent of 2x's, right? But if you consider your composition to the opposite order, when you first get your variable squared, and then you are taking the result into the exponent, then you get the function exponent of x squared, right? So basically it is two different results, and you should always remember that. So now we know what the class of elementary functions is. But actually, since we know the elementary functions, we actually know how their graphs looks like for at least some of them. Well, sometimes the idea of getting a graph for some arbitrary elementary function is quite complicated, but still, in some cases, you can use simple transitions, simple transformations of your already existing graph, already known graph, to get some more complicated example. Let us just assume some basic things here, some basic transitions, and use them in order to draw some more intrinsic curves. For example, you can look at a graph or look at a function which has a vertical shift. Firstly, you had some graph of a function f right here, and then you added some constant, which basically means that you are going up with all your curve for a c in length, right? That's quite easy, that's quite essential for us to understand. If you have x squared and if you have plus 2, then basically all your graph stands up and moves up into the opposite direction by the 2. Okay, that was quite easy. So let us assume pretty much the same thing, but for the idea of adding not to the function itself some constant, but to the argument. Here comes the tricky part. Basically, what you should expect, if you are adding plus c, then you should move all the graph to the left by c, not to the right, to the left. And let us just take a look at this very graph, and the idea here is follows. Assume, for example, that you have a value of 0 at the point 1 of your initial graph here for your function f. Basically, 0 equals to f at the point 1, right? So if you are looking, for example, at a graph f towards x plus 1, then your 0 value is achieved not at x equal to 1, but at x equal to 0, right? Because 0 plus 1 is 1, and you get the old f towards 1, right? So basically, this is from transition from 1 to 0. Okay, so you need to move to the left. Fine. So this is for addition to the function of the argument some constant values. Obviously, you can use, for example, multiplication of the function or the function arguments by some value. It's kind of a contraction, right? So basically, if you are looking, for example, at multiplication in our example by 1/2, then you are multiplying all the function, all the values of the function by half. You are just applying a contraction by the vertical axis, right? So another thing here for multiplying your argument. If you're multiplying your argument by c, then you are going to use your contraction into the opposite direction. Obviously, if you're just looking at, for example, multiplication by 2, you need to contract your graph by half. That's pretty much the same case as for our idea about adding a constant value to the function's argument, right, as an horizontal shift. So, as for the last transitions, we are going to consider applying absolute values. That's quite simple. If you apply the absolute value to the function's argument, basically your function loses all the information about your negative values. Function thinks that you are getting only positive arguments, thus basically the result at -1 is the same as the result at 1, thus function should be symmetrical towards y-axis here, right? So, and if you are applying absolute value to the function itself, then you should understand that if you previously got negative results, then you got the opposite positive results. Here, basically, you should just erase all the parts of the graph which is underneath the x-axis and symmetrically draw the same thing upwards. So let us consider some examples. For example, let us start with a plot of polynomial function. It's elementary, nice, you can easily do it by, for example, finding function's roots here. We're looking at function x power 3 minus 3x squared plus 2x. And what we're going to discuss here, first we're going to say that there is 3 roots. You can easily solve it because it's a simple quadratic equation, right? So there are 3 roots, 0, 1, and 2 for this function. And we just drew a curve through it. Firstly, we are going to start with drawing the graph of the function itself. Here it is, that is nice. How to understand how does it go? Firstly, I've calculated the values at 1/2 and 1.5, there and there, right? And second of all, I'm trying to think about something. If we are just considering a value of at million point, right? If x equals to million, what is the value of our function? Extremely large, extremely low, or somehow around 0, right? Well, in our case, it's obviously extraordinarily large, but so the function goes up in this direction. The same applies here, so this is down direction, and thus we need to draw our function through these points and then follow this very trend. So that was quite easy, right? So let us, for example, take a look at the second part of our example, where we need to draw a function with a graph from value this one, after applying multiplication by 2, inversion of the argument, and vertical shift by 6. So this is our initial graph. That's what we started with. Firstly, I strongly recommend you to start with drawing just writing down the sequence of your actions. What you are supposed to do? Firstly, you're gonna start with f towards x, then you're gonna start with f towards minus x, which basically means that you're gonna symmetrically swap your functions from the left to the right and from the right to the left, right? So it's basically going to look something like this. Okay? Then what you need to do, you need to either decide. You can, for example, vertically move it up by 3 and then multiply, contract it by 2, or you can just multiply it by 2 right now and then move it upwards by 6. As a result, we get something like, for example, this. Right? That's kind of our graph. As I promised, it's extremely ugly because the time for nice plots just have passed, and we are going to revert to them later, but that's understanding what we are going to get as a result, right? So let us assume, for example, another thing here, like f towards absolute value of x divided by 2 plus 4. Once again, I'm going to carefully write the procedure. Firstly, we are going to consider taking an absolute value of the argument, then we are going to, for example, draw a contraction, and then we are going to vertically shift it. So basically, I should expel the left part of the graph and then draw a symmetric picture. Then I need to, for example, contract it by 2, right? So it's going to be something like that. Okay, and then I'm gonna vertically move it up by 4. Let me not try to frighten you with another extremely ugly looking curve here, but the idea, you got it. So, and as for the last part, of course, this is not an elementary transition, but it's kind of easy to understand what will be in the result. Here, let us take a look at the result of inverting our function, or basically not taking an inverse function, right? we are not considering the case of sine and arcsine function. We are talking about just drawing a graph of 1 divided by our f function. So here is some ideas. There is 3 roots, thus there is 3 points where our 1 divided by a function do not exist. I am going to stress them out by such vertical lines here. So, for example, if we go in from the left part to our first vertical dashed line, we're gonna say that our function is getting towards the absolute value extremely small, but negative. Thus, by inverting it, we're gonna get extremely large by the absolute value negative numbers, right? So we're gonna get something like this here. Same idea applies, for example, for the right part in around 0. Here function is small in absolute terms and positive, thus after inverting we get something like this. Then there is all the same thing negative, and there is one positive thing. Since our function tends to be greater and greater, I do think that after inversion it is going to be smaller and smaller. But to properly understand it, we need to calculate a limit, which we are going to address further. So let us start our journey to the limit of the sequence with the following puzzle. Assume that, for example, we have on our hands 3 certain algorithms. First takes, for example, n squared plus n time to complete for n real numbers. Second takes 2n squared minus 6n plus 5. I just pointing out from my head. And the third, for example, takes an algorithm n, I don't know, seconds in time to complete, right? So the question is, which one is faster if the number of elements in your array is growing and growing and growing, and how faster, okay? In order to do it, your essential idea is somehow to change the idea of, for example, first and second algorithm into the idea that we need to assess their relation, right? So let us introduce, for example, our new sequence. We're going to call it AN, which is straight out loud division of the first algorithm's time by the second algorithm time. So we aiming to compare the speed of our algorithm with our new sequence. What we are supposed to do? Well, essential idea is we need to look at the values of this relation and understand what happens to those values if we are increasing our number of the sequence or we are increasing our n, right? Okay, and our hope is that this relation by the growth of n is somehow stabilizes. That is, by all the means, is the definition of the limit of the sequence. We are going to call a real number, a real value, sequence's limit if it resembles our sequence the most as the number grows to infinity. Well, as they say, approach to infinity. Okay? Let us, for example, assume the following sequence. I'm going to schematically draw the sequence 2 plus sine out of n divided by n, and well, we are going to say that there is some kind of an understanding of how this function behaves if we are looking at the infinity, right? So the notation here is that the limit of the sequence, or well, layers as limit of the function and whatsoever, is defined by this very word lim, which is kind of truncated limit, right? Underneath we are writing what approaches what, the variable and what value, right? And here is the function we are trying to torture with our complicated concept here, right? So we are going to say that the limit of this very sequence equals to c. Right. So what's the idea basically? The idea here is that at some moment this sequence is basically this C value plus some kind of non-significant fluctuation, right? So let us try to describe it into more structural manner, right? So the idea here is, let us draw our C level with blue dashed line here. And for example, assume that we are looking at our sequence. For example, we assume that our sequence should evaporate any deviation from the limit. So take a look at, I don't know, the deviation 1/10, right? So we are going to create this kind of gates with plus 1/10, minus 1/10 from the sea level, and the idea here is that from some point our sequence does not deviate from the limit value more than 1/10, right? Does it hold for this very sequence? Right, yeah, this holds because we have, for example, our red moment here, right? Our red line horizontally, from which sequence all lies in between our 1/10 gates, right? Okay, that's fine. Basically, that means that our sequence does not deviate significantly in terms of 1/10. But in order to properly define our limit, we kind of do not care about 1/10. 1/10 is not mathematically, universal constant, right? We are gonna say that we need to have some kind of universal understanding of evaporating our deviation. And in order to do so, basically the idea here is that for any given deviation, the same should happen, right? For example, we start with our 1/10, then we are going to say, for example, our 1 divided by 20 deviation drawn in green here, right? And here is some other moment from which our sequence lies entirely within our green gates, right? For example, somewhere from here. Okay, so basically the idea here is that we are going to write our definition in our extremely formal, extremely mathematical way with quantifiers, with sets. Well, we're going to just fire with all our arms here. So what does this definition say? For any deviation, there is a moment which is called capital N, that afterwards our sequence does not deviate from the limit value more than this given deviation, right? More this given threshold. Okay, so this basically means that in order to, for example, prove that this very thing happens, we need to find out for any deviation what is the number when our lives became the happy ever after, right? So this is our happy ever after for this very given deviation. If we manage to achieve for any given deviation this happily ever after, then our function, our sequence has a limit. Okay. So let us try to use our definition for some examples. Let us start with some basics. For example, an equal to 1 divided by n, right? Firstly, let us imagine what is the limit of these very sequences. Well, it's kind of understandable because 1 is kind of constant and n approaches infinity, thus 1 divided by something very large should be extremely small, right? In other words, if you're having a party and you need to divide the pizza, if there is 100 guests, you get 1/100th of the pizza, and if there is for 1,000,000 guests at your very party, my condolences, then you pretty much get nothing, right? So the limit of this very sequence supposedly should be 0. So let us try to use our definition here. what are we going to do? Firstly, we are going to remind you what is our definition. Our definition stands that for any deviation there is a point that our sequence does not deviate from the limit more than this deviation. Okay? So in other words, we need to find this very moment for any deviation. Okay, so let us look at our definition here and substitute all we know for our example. First of all, let's start with leading inequality here. We are going to say that C equals to 0, an equals to 1 divided by n. Also, I'm going to lose absolute value because 1 divided by n always positive. Thus, we are going to find such a number, a capital N, that 1 divided by any further natural numbers is smaller than epsilon. Okay, that's quite easy because if we rewrite this by multiplying by n and dividing by epsilon subsequently, we get the following, that your n, your number of the element of a sequence, should be greater, just greater than 1 divided by epsilon. So if we need to provide this very moment when your life becomes happily ever after, we need just state that that's this very moment. Except you all do remember that epsilon could be real, thus 1 divided by epsilon could be non-natural. So we are going to use, for example, integer part of 1 divided by epsilon, and we are going to add, for example, 13 in order to avoid any errors as a result of rounding up. Okay, so we've managed to come up with quite a proof of the calculation of this very limit, right? So, firstly, let us learn that if the sequence like the one we've just solved here has a zero limit, then it's called infinitesimal. And right after it, we're gonna look at the example of very similar sequence of sine of n divided by n. It's kind of pretty much the same thing we've started our definition of a sequence with, but we're gonna omit this +2 because it's kind of easy. And we are going to further learn that it doesn't actually make head explode. So what is the limit of this very sequence? As you can see, well, firstly, we can just proceed with our basic definition here, right? We're gonna just write it once again, that we are gonna say that it is a sine of n divided by n minus limit is smaller than deviation. But we need to understand what the limit is, and it's kind of easier to understand and prove right after that the limit is, then show it once again by the definition. Because as you understand, sine is bounded function. When someone says that the function is bounded, that basically means that we can find a lower boundary, a number which is the lowest value of our function, and the upper boundary, which is the greatest value of our function, right? And the function can be lower than the lowest boundary and higher than the upper boundary. So the sine is bounded, thus if we divide all the sides of this inequality by n, we get that our sequence is bounded by two sequence, which is kind of familiar for us because it is our 1 divided by n and minus 1 divided by n, which is obviously approaches the same zero value. Right, thus the sequence in between them should also approach zero value. It's kind of pretty much the same thing. And thus we've actually proven our limit by creating an inequality of with two sequences which approaches the same value. Okay. So this, by the matter of fact, allows us to state more general idea. Here is that the product of bounded, like sign, and infinitesimal, like 1 divided by n, is infinitesimal sequence once again, right? And the idea is pretty much the same. You need to find two boundaries here. Okay, so let us assume, for example, another thing, which is kind of super easy here. What if our sequence is 2n's plus 1? As you can understand, this sequence grows monotonically in a way that every next element is greater than the previous one, right? Well, because 2n plus 1 is greater than 2n plus 1, just because 2 is greater than 0, right? So basically this thing is grows and grows and grows, and more importantly we can show that for any I'm going to use another quantifier here, hooray. For any real number, I'm going to use positive one, there is a moment that our sequence is greater than this real number. Well, you can actually quite easy by just finding n from this inequality, define this very moment. Here it is, right? So basically what we're gonna say is that this sequence looks something like increasing dots, right? And you can just say that after, for example, hitting the level of 10 or 100, you are not going backwards, you're not going under it, right? So this function is called to have infinite, positive infinite limits. Its limit equals to plus infinity. Once again, we're going to use this example to learn some terms here. Firstly, we're going to say that this function approaches plus infinity, and this basically means that if it gets greater, there is a moment when it gets greater than any possible value, and then it never goes lower than this value. It's not necessarily the first time it gets greater than this very value, but there is time when it never goes back. Okay, and the second term here is unbounded, which basically means that you cannot come up with, for example, upper boundary for this very sequence, right? So I'm going to stress out that those are not the same thing, just because assume the function which is assume the sequence which is, for example, n if n is odd or even, let's say even, and 0 if n is even odd, right? For example, assume the sequence which is n for even numbers and 0 for odd numbers, right? Then it is unbounded, obviously, because it kind of follows the number for at least every second value, right? But also it kind of always turns back into the 0 value, thus it does not approach plus infinity. It kind of have no limit at all. This limit does not exist. For another example of sequence that does not have a limit, let us assume the case of sine of pi multiplied by n. Here, because, well, as you all understand, it is basically minus 1 powered n, right? Because sine of pi is minus 1, sine of 2 pi's is 1, then minus 1, 1, minus 1, 1, and so on and so on. So basically we are looking at a sequence like this one, and as you can see, it do not stabilize in around either of these two values. And you cannot say that, for example, the limit of this function is, for example, -1, because you always deviate from it by the deviation of 2, right? Or you cannot say, for example, that the limit of this function is some kind of averaged value 0, right? Because you always deviate from it by 1, and you are supposed to deviate it from it more or less and less. So in these cases, sequences has no limits, or it doesn't converge at all. That's our new term here. Okay, that's nice. So, as you can imagine, nobody actually uses the definition of the limit all the time. It's nice to have some kind of alternative of higher order to understand how to move in more intrinsic cases of limits, right? So, in order to do that, we're gonna learn some basic arithmetic rules for limits. For example, let us assume that we are going to find the limit of the sequence, which is actually sum of two other sequences. In our cases, we are considering the sequence an, which is the sum of bn plus cn, right? So the idea here is, if bn approaches some b as a limit, and Cn approaches some C, one is gonna try to say that then the sequence An should approach the sum of these two limits, right? Let us just understand why it is. Just assume that, for example, our sequence Bn do not deviate from its limit, for example, by epsilon divided by 2 from some number from, for example, n1, okay, or nb. That's nice. And the sequence C is also do not deviate from its limit starting from nc. Okay, we can do it because, as you do remember, both of these sequences have a limit, and thus for any deviation we can state the number in the sequence where the happily ever after starts, right? Where the sequence stops to deviate significantly from its limit. Thus, if you consider these two numbers, you can, for example, come up with the maximum of these two numbers. Thus, after this one, we're gonna call it NA, because you will understand what I'm implying here, right? After this one, each of the terms do not deviate from its sum more than by half an epsilon. Thus, its sum do not deviate from the sum of the limits by more than by just epsilon, right? So basically, we're just using our very naive idea of taking the maximum number of 2 when it starts to be happily ever after. We've just proven our limits of the sequence of the sequence An, right? So let us just generalize it for any further use. The idea here is pretty simple. If you have some kind of arithmetic operation on the limits, the limit of this arithmetic operation is basically the arithmetic operation of the limits. This applies for adding or subtracting, taking a product, or looking at the division of two sequences. Well, obviously, here you should extremely care about not dividing by 0, and far more important thing here is the note. All these rules do apply to the case of finding limits in case all right side limits exist, right? So basically, if you are, for example, taking a look at sequence 1 as a sum of n plus 1 minus n, right?
that is a forbidden relation, because you've just tried to move from the limit of the difference of the function onto the difference of the non-existent limit, because in case this is function approaches plus infinity and this function approaches plus infinity, the limit is by definition do not exist. You do remember, the limit is a finite real number and the infinity is not a real number. And you cannot just subtract one infinity from another and get one in the result. Of course, there can be, for example, instead of one number 2, and there still be infinity minus infinity, and then it's gonna be a nightmare, right? Okay, so when you are using your arithmetic rules, you should be extremely cautious that all the terms in the right side should actually have the limit, should converge. So let us look at the example we've actually started our conversation with. We've discussed the idea of comparing the speeds of two algorithms by looking at their relation, which is n squared plus n divided by 2n squared minus 6n plus 5. So in order to find the limit of this sequence, let us just try to directly apply the idea of arithmetic rules. But there is a bummer, because clearly we can see that numerator approaches infinity and denominator by any means also approaches infinity, so we are not able to divide one by another because the limits of numerator and denominator do not exist. So in order to avoid this thing, we need to somehow transform our sequence in a way that there is a limit of numerator and denominator. In order to do so, we are going to divide both numerator and denominator by n squared. Thus, we get as a result 1 plus 1 divided by n in numerator and 2 minus 6 divided by n plus 5 divided by n squared in the denominator. As you should understand, this doesn't change actually our sequence at all, because it's equivalent transformation, right? But now we can try to find a limit by our arithmetic rule. Because of what? Because actually 1 divided by n approaches 0, as we've showed recently, right? So thus all numerator approaches 1. Okay, I'm gonna write an arrow here in order to stress that that's a limit. So what are we gonna do? In the denominator, pretty much the same, because these two fractions are also infinitesimal or approaches 0, right? Thus, the numerator approaches 1 and denominator approaches 2. And the limit of this very sequence is 1/2. Or another way, one algorithm is 1/2 faster than the other algorithm, or 2 times faster, depending on what you are comparing with what. Nice. Also, let us, for example, consider another useful example here. We are going to look at the sequence, which is once again a division of 5 multiplied by 4 powered 1 divided by n plus 2 powered 1 divided by n minus 6. And in the denominator, we get a 4 powered 1 divided by n minus 6 multiplied by 2 powered 1 divided by n plus 5. Okay, so once again, our idea is to apply our arithmetic rules. In order to do it, we are gonna start with auxiliary limit here and find what actually is the limit of 2 powered 1 divided by n. Since 1 divided by n approaches 0 and 2 powered 0 is actually 1, all this function actually approaches 1. Formally, we do not know the idea of why we can just consider only 1/2 of the sequence here in the power and then just took the power of 2 by its very limit, but we're going to use it to skip all necessity discussion about the continuity of the exponential function here. So our discussion wouldn't be so excruciatingly painful. Okay, so what does it mean for our sequence? Since 2 powered 1 divided by n approaches 1, thus we get that first term in the numerator approaches 5, second approaches 1, and all numerator approaches 0, which is, well, a red flag here, right? Because if we consider the same thing in the denominator, we also get 0, and, well, we cannot divide by 0, and if the denominator was, for example, approaches 1, we all would understand that there is a constant in the numerator and infinitesimal function in the denominator, thus we get some kind of function that approaches infinity, right? But now we do not know, and we're gonna to further extrapolate on this later, but right now we need to somehow handle this one, and in order to do it, I'm going to substitute the expression 2 powered 1 divided by n by some new variable, for example t. Thus we are looking at sequence 5 tn squared. Thus we are looking at sequence 5 tn squared plus tn minus 6 divided by tn squared minus 6tn plus 5. We do know that as n approaches infinity, tn approaches 1. As we're looking at these polynomial functions, we can understand that since after substitution our tn with 1 we get 0, tn is a common root for both polynomials, thus we can assume that we can factor numerator and denominator in the following manner. Let us write it here. Firstly, numerator is tn minus 1 multiplied by 5t n plus 6. Okay, if we just multiply our brackets here, we're gonna get pretty much the correct answer, right? And for the denominator, we're gonna say that this is tn minus 1 multiplied by tn minus 5. Okay, so as a result we get 5tn plus 6 divided by tn minus 5. And if we now take a limit here by our arithmetic rule, we get, as tn approaches 1, we get 11 divided by minus 4, which is minus 11 divided by 4 as a result. So we found this kind of complicated limit here. Now let us consider another useful principle which is used to calculate the limits of sequence, and in order to do so we are going to use the definition of the very famous constant e. So firstly consider the following sequence, which is en, which is basically 1 plus 1 divided by n powered n. So the question is, does it have a limit, and what's the value of this limit? If we're going to use directly our arithmetic rules, we are going to be a little bit confused, because as you all understand, we are looking basically at the multiplication of n brackets. Each of these brackets is 1 plus 1nth. Thus, by arithmetic rules, each of these brackets approaches 1. So we are looking at the multiplication of n and growing number of multiplicators, each of them approaches 1. Common idea here is, if you consider, for example, the sum of n terms, each of them approaches 0, for example, 1 divided by n times. Obviously, it's not quite changing sequence, it's a constant sequence which equals to 1. But if we use our arithmetic rule, we are looking at n terms, each of them approaching 0. So basically, our arithmetic intuition here doesn't work at all. Even more, let us, for example, assume 3 initial values of this sequence. Let me write down a simple table here. We are gonna consider, for example, n 1, 2, 3. If n equals to 1, then we have 2 powered n, 2 powered 1, which is 2, right? If n power equals 2, then we are having 3 divided by 2 powered 2, which is 4 divided by 9, and for 3, this is 64 divided by 27. The idea here is that if you carefully compare all these fractions, you will see that our sequence monotonically increases. That basically means that not only this sequence doesn't approach 1 by arithmetic rule, it also starts from 2 and increases. Well, it seems like so, but we've actually hadn't proved it formally yet. So, in order to understand what is the limit of this sequence, we are going to introduce ourselves to the concept of monotone convergence theorem, which basically states that if our sequence increases monotonically and has an upper boundary, then it converges. The idea basically here is the following. Our sequence is depicted by the red dots, and upper boundary is depicted by blue dashed line upwards. So the idea here is that if we consider the set of all upper boundaries, we can choose the lowest upper boundary, the lowest value, which is greater than all the values of the sequence, right? And this will be the limit of our sequence. This will be the value which resembles our sequence the most. Okay, so let us assume that our blue line actually corresponds to that level. So why this is the limit of our sequence? Firstly, if we are thinking that there is no limit of this sequence, then we should understand then by our monotonic character, our sequence is getting closer and closer to our blue line. Thus, basically, it resembles better and better our blue line. And since our line is the lowest one, basically, if we think that the limit is actually not a blue line here, but, for example, green line somewhere on the top or on the bottom, then we should understand that if we are on the bottom, then we somehow, somewhere our sequence crosses this line and getting only bigger and bigger and closer to blue line. And if we are on the top, then we will be never close to this green line more than the distance between green and blue line. Thus, it's not a sequence limit at all. So, this basically states the principle of monotone convergence theory. Of course, same principle applies for the case of not increasing but decreasing and lowly bounded sequence. Then it also converges. So let us apply this theorem to the case of the sequence En. Basically, we need to show two things here. First one is that this sequence increases, and this graph in particular depicts this very thing, because we just drew on this very graph our En sequence. So this is increases and has some upper boundary. Of course, I'm not stating that I'm gonna just use the lowest upper boundary, because it will be very much the limit, and this all our discussion is kind of has no point, right? So I'm gonna say that there is some upper boundary, for example, upper boundary which equals to 3. Yeah, and it's just some kind of upper restriction for our sequence. So basically, whilst we showed that, and we did it more thoroughly in our additional materials, so we need to show for our sequence En that it increases or decreases and has upper or low boundary, right? So as our graph depicts, we've draw our en elements here, it monotonically increases. And we're gonna say that it has an upper boundary, for example, 3. It's not the lowest upper boundary, because if we use lowest upper boundary, then we use a limit, and this discussion doesn't have many sense here. So we are gonna say that it has some upper boundary 3, and that satisfies all the necessary conditions for our monotonic convergence theory. Thus, this very sequence has some limits. Actually, it is not a known number, it's some kind of new irrational number, which is called E. By far, this is very the definition of our E and not some kind of other understanding. This is the same E that you can meet at the exponent of natural logarithm and so on. As we established earlier, during the application of our arithmetic rules, we can stumble into some frightening cases where we cannot actually call the answer right away. For example, let us take a look at these two sequences, an, which is n squared plus n divided by n, and bn, which is n plus 1 divided by n squared. If we just straight out loud substitute our n with, for example, infinity, as n approaches infinity, we get in both cases infinity divided by infinity. At the same time, well, it's clearly can be seen that the answer for the limit of these two sequences are pretty much different. Because if you divide, for example, the numerator and denominator of each fraction by n, then the first sequence changes into n plus 1 divided by n divided by 1, and the second sequence changes into 1 plus 1 divided by n divided by n. Thus, the first one approaches infinity, and the second one approaches 0. Right? As well as, well, one can come up with the idea of pretty much the same case of infinity divided by infinity with any constant limit instead of 0 or plus infinity or whatsoever. So basically, this case, the substitution with the limit point in this case implies that the direct application of the arithmetic rules can be troublesome. The whole idea of these troublesome cases is commonly referred as indeterminate forms. So basically, if you are getting after the application of arithmetic rule some kind of infinity divided by infinity, or 0 divided by 0, or 0 multiplied by infinity, infinity minus infinity, 0 powered 0, or 1 powered infinity, thus you should definitely think that that is in indeterminate form. And as you can understand in our examples, or for example in our cases when we considered our example about 2 powered 1 divided by n, we are almost expecting ourselves to do another additional work here in order to provide a better sequence to apply the direct arithmetic rules, right? So let us state the obvious. The indeterminate forms doesn't state the answer. It does not give you the answer that everything is bad, there is no limit, or that limit is infinity, or 0, or something like that. Or at least you should not write 0 divided by 0 and feel safe that that's your answer. It's not. Your answer should be value, real number, right? So basically, if you stumble into the case of the indeterminate form, it basically stands that you need to do another additional transformation of your sequence to provide a sufficient form to calculate the limit. Welcome to our Excelsior transparent board. Now we are going to consider some more sophisticated examples of the limits of the sequences, right? So in order to do it, we are going to study 3 classes of functions: polynomial function, exponent, and logarithmic functions. I'm going to just assume that the foundation of the logarithm is natural. one more thing, we're going to consider only exponents greater than 1 in order to achieve monotonically increasing function here. Right. So the idea here is that we are going to establish the relation between those functions, and those limits are so important that I'm going to use some low-budget TV series thing and just flash forward to the result for you to remember it clearly. So the idea here is that the limit of relation of polynomial function and exponential function for any possible power of n and for any possible exponent a greater than 1 is always 0. Same applies for the case of the relation of logarithmic function at some power and any power of n. This relation still approaches 0. Okay, so what we are going to do, we are going to prove these limits by the very definition of the limit of the sequence. For the start, let us just consider that we are looking at, I don't know, for example, n squared and 2 powered n, right? So what we are going to do, we are going to prove that the relation approaches 0. In other words, let us just revisit the definition of our limit here. For any positive deviation epsilon, there is a moment, we called it happily ever after, that afterwards our sequence do not deviate from its limit more than our established threshold epsilon. Okay, that's fine. So we are going to just rewrite what we have here, because our sequence is a relation between n squared and 2 powered n. Our limit is 0. Thus we get that n squared divided by 2 powered n should be smaller than epsilon, or in other words, by multiplying by 2 powered n, we're going to say that n squared should be smaller than epsilon multiplied by 2 powered n. I've omitted the absolute value since our sequence is clearly positive. What we're going to do here, since we need to somehow establish the relation between polynomial and exponential function, we're going to consider that 2 powered n is actually 1 plus 1 powered n. I hope that nobody gonna argue with that. That's kind of pretty clear here. So the thing that we're gonna do, firstly, let us just try to prove the very idea of n squared is smaller than epsilon multiplied by 1 plus 1 powered n. Let us just revisit the 1 plus 1 powered n, and in order to do so, we are going to use our Newton's binom, which you are familiar with from the discrete mathematics course, and if you're not, you can always visit our additional materials, which we are going to remind you with the concept of binomial coefficients and the proof of the Newton's binom all over again. So the idea here is that we get our brackets to sum with binomial coefficients in the following manner. We get 1 plus first binomial multiplied by 1, I'm going to omit that, plus second binomial multiplied by 1 plus 1, plus third binomial, and so on. So we need somehow to establish that this sum multiplied by some small deviation is still greater than n squared, right? So in order to do it, I'm gonna use not the 0, first or second binomials, I'm gonna use the third binomial still, since its power is greater than n squared, right? So let us firstly rewrite it, right? So it is n multiplied by n minus 1 multiplied by n minus 2 divided by 6. That's nice. That's basically a polynomial of power 3, right? And what is its relation between n plus 1 and the third binomial? Clearly, since all the terms in our Newton's binom are positive, then our third binomial is smaller than n plus 1 powered n. And in its turn, the third binomial is greater than, for example, the smallest multiplier here, powered 3, right? we are going to use it just to simplify our output. Okay, that's fine. So if we've proven that for some moment n squared is smaller than epsilon multiplied by n minus 2 power 3 divided by 6, then just by substituting with greater third binomial and 1 plus 1 power 10, we will prove our limit, right? So in order to do it, we're going to write it in the following manner. We're going to move all epsilon and constant parts to the left side and n terms to the right side. In other words, we get 6 divided by epsilon should be smaller than n minus 2 power 3 divided by n squared. Or it's less than, let us just get our denominator smaller, n minus 2 power 3 divided by n minus 2 squared, or just n minus 2. Thus, the moment from where our inequality holds is integer part of 6 divided by epsilon plus this very 2, right? But since we're working with our integer part, I'm going to just add a spare 1 here and say that it's plus 3. Right, so that's the very moment when this inequality holds and this inequality holds. Thus, we've proven that by the definition of the limit, the relation between n squared and 2n approaches 0. By substituting 2 with any possible real number a which is greater than 1, we can prove for any other exponent and for any other polynomial by simply relying on the fact that here we can move from n squared by n powered k and from the third binomial to k plus 1th binomial, right? That's fine. But what it has to do with the idea that we also need to prove the relation between logarithmic and polynomial function. Just for sake of simplicity, let us take a look on relation between natural logarithm of n and n itself. So the idea here is that we do not want to once again try to prove it by definition. We are aiming to just interchange it into the form of polynomial divided by exponential function. In order to do it, we are going to substitute our variable with exponent powered, for example, k. Thus, we get logarithm of exponent powered k, or k, divided by exponent powered k, which is, by our previous statement, infinitesimal, right? Okay, that's fine, but there is one small issue with it. Since we are looking at the relation between natural number as exponents of some other number, this power k is not natural, right? Thus, by its very definition, the relation k divided by e powered k is not actually a sequence. But we can move from it to the sequences using our rounding up of our new k number into some lower and upper boundaries. For example, we can use lower boundary rounding up and upper rounding up, denoted as here, and substitute the k value in our new sequence with this almost certainly natural numbers, right? Thus we get lower boundary and upper boundary on our initial sequence, and thus, since all these sequences are infinitesimal, our initial sequence is also infinitesimal. So we proved that the relations between polynomial and exponential and logarithmic and polynomial are infinitesimal.
Hi! Welcome to the second week of the calculus course. Recently we've covered various basic concepts for functions such as domain, support, range, codomain, and basic transitions of elementary functions graph. Also, we've speak about functions of natural domain or sequences and its limits. Now, it's essential for us to turn over to the case of real domain functions or functions in general. Also, we are going to speak about not only its limits, but the comparison of its asymptotic in the given point, and the idea of multivariate functions, or just administering another degree of freedom into the system. See you in the following video. So, let us see what we've already known and what we are going to define here. The thing that we've known is sequences. Sequences is basically functions of natural domain, where we have a set of natural numbers, and for each natural number we have some value. Okay, that's our already established definition. So, we are going to move forward into the case of functions from real numbers to real numbers. Right? So we need to discuss firstly what is the difference between the structure of the real number set and a natural number set. And actually this structural difference is quite observable. Assume that we have our real numbers drawn on a straight line, and then we just point out all our natural numbers. And consider, for example, the neighborhood of the point 3. I'm gonna stress this out, right? So what's the idea? As for the natural numbers, the closest as we can get is either 2 or 4, right? So the smallest distance in between natural numbers for number 3 is 1. But as for real numbers, as you can all understand, there is no the smallest distance between 3 and other numbers, because we can get as close to 3 as possible, right? So that's basically the concept of limit point of any set. The point is called limit if we can get infinitely close to it by the elements of this set. So the idea is very simple here. We can discuss the limit, we can consider the limit of the function in a given point only if this point is a limit point of the function's domain, right? So the question here is why we've considered the same case for sequences, for example. And it's, by the matter of fact, quite easy, because let me do some kind of infinity here, right? So somewhere in the very right there is an infinity. What is the phrase as close to infinity as possible means, actually? It basically means that we can look at some beams starting from some finite number m towards the infinity, and then we just move this m further and further to the right. So basically the idea is that any neighborhood of infinity means that we can assume that we have some quality, or some condition, or for example our sequence does not get further from its limit, starting from the point m, starting from the number m, and further away. So as for the natural numbers, the only limit point is infinity, because we can get closer and closer to infinity. But for real numbers, the set of limit points are all the numbers plus and minus infinity. So that's basically the idea of our transition from functions from sequences to functions, right? Previously we were speaking only about limits at infinity, and now we can speak about pointwise limits, and we need to properly define it using already existent definitions for sequences. So let us try to generalize the concept of the limit of the sequence into the case of functions of real domain. Basically, what we actually already have. We have the idea that the limit is the value of, well, just any real value which resembles our functions or our sequence the most. The rule here is that if we have any given deviation, then we can assume that our sequence or our function does not deviate much from the limit if we get close enough to the limit point. So let us try to formally write this down. Well, this is kind of a nightmarish because we are going to use our quantifiers as we introduced in the previous week, but everything will be fine. So let us start from the our picture. What we do have here? We do have here our function. This is a blue curve, and then we have a point of interest, a limit point A. Here, right? So what's an idea? We are going to say that this function have a limit equal to c as x approaches a, right? C is drawn over there. So what does it mean? It basically means that if we just state that we allow our function to deviate from the limit by epsilon, the epsilon just any possible real positive value. Then we create some kind of boundaries on our function's value, right? C plus epsilon and C minus epsilon. So this is our epsilon tube here, right? And the idea is that we can get as close to point A as the function doesn't break our epsilon tube. In our case, we've come up with the idea of delta here, neighborhood of the point A, thus epsilon tube and delta tube intersects in rectangle and our function wholly lies within the rectangle. That's kind of nice. So the second thing we need to do is to change our epsilon, right? Because what we want to achieve the idea that we can do this procedure for all possible deviations, right? So that's how our definition works. It's kind of extremely formal one, but we should always start with the formal things, right? So for all deviations, we can get as close to our limit point, thus function does not deviate from its limit much than previously stated deviation, right? That's how it basically can be read in natural language. That's fine. But there is kind of a bummer here. Why do we need to write that our absolute value of x minus a, or well, the distance between arbitrary points in the neighborhood of the a is smaller than delta, which is basically means that it's neighborhood. But what is greater than 0? Greater than 0 actually means that we are not considering the point A itself, right? So basically it means that we are looking at every value of the function in the neighborhood except the point itself. And why is it? Let us assume that there is some enemy around us, and this enemy come at the very point A and just damaged our functions and said that f from A, for example, is not our nice, easy blue curve, and some other point, for example, this one. Okay, remember our definition, well, hand-waving definition, right? So what we've said previously, we've said that the limit is a value that resembles our function in the neighborhood. As we get as close to the limit point, we are not supposed to be at the limit point, okay? We are considering only functions in the neighborhood of it. And in the neighborhood, well, a function doesn't actually care about the value of the function at the very point itself. So we should actually expel our x equal to a from the consideration of the limit. So it's kind of tricky.
Sometimes people use the idea that we need to have another more sequence-based definition for the limit function, and it's kind of expectable because it does read in the following manner. If we assume any sequence of arguments of our function xn which approaches our limit point n, which can be done because because a is our limit point, then the sequence of function values on this sequence of functions arguments should necessarily approach its limit. It's kind of nice because it operates in the same terms that we already have been established, the limit of a sequence, right? But the problem here is that we are talking about all possible approaches to the point A, all possible sequence that approaches point A, which kind of nightmarish object. You can even just imagine how much sequences approaches point A, right? So the first definition is usually used to prove that there is a limit and to calculate it. And the second definition is used to prove that there is no limit or this point is not a limit. So it's used to prove an absence of the limit. Now let us consider some examples of the calculation of functions' limits by the definition. So let's start with the idea of the limit of, for example, function x squared in some arbitrary point A. So what we are going to do, we are going to compute the limit of x squared if x approaches A, right? So firstly, one can understand that this limit is actually easily calculatable by arithmetic rules that we are going to cover further in our lectures. But for the sake of the example, let us just try to find it by the definition. So, as we established, there is two basic definitions of the limit of the function. One concerning deviations on the epsilon delta language, and one concerning sequences, right? Which is more useful for proving absence of the limit of the function. So, as one could imagine, the limit of x squared if x approaches a is a squared. That's pretty simple. Let's try to prove it by our first epsilon delta definition. In order to do so, first let us just revisit it by writing it down. For any positive deviation, you can go as close to the point where the limit is taken, but not exactly at this point. So the deviation between function and its limit, I'm gonna use capital A, is smaller than established threshold. Okay, that's what we're aiming at. Let us substitute what we actually have here. We know what is our function, it's x squared, right? And what is our limit here? Limit is a squared. So we're looking at the absolute value of x squared minus a squared. Let us rewrite it here. Okay, so what we're gonna do? Firstly, we're gonna do some school trick. Since we're looking at the difference of the squares, we will factor it into two brackets. X minus a multiplied by x plus a. So that's easy. More importantly, the absolute value of the multiplication is multiplication of absolute values. Thus we get that we are looking at absolute value of x minus a multiplied by x plus a. The first part here, the first multiplier here, is pretty nice because it is, by the definition of the limit, supposed to be bounded by 0 from the lower side and delta, which we are looking for from the upper side, right? But what one should do with the second multiplier, since it is dependent from the x? Well, let us just consider that our deviation from the point A does not exceed, well, the point A itself, or in other words, the absolute value of x plus a do not exceed 2a's. So we are gonna just use another inequality here. We are gonna consider that the first multiplier is no more than delta, which we are looking for, right? That's our kingdom for a horse. And the second multiplier here is not greater than 2 absolute values of a. We are gonna write absolute value of a here just because we can assume that the limit is also can be taken in negative point, yeah, for negative a's. So what we got here? We got here that basically our deviation do not exceed delta multiplied by 2 absolute value of a's, and if we found a delta, in which case this expression delta multiplied by 2 absolute value of a's is smaller than epsilon, then we actually get our desired inequation that the deviation does not exceed the threshold, right? So in order to find it, we just need to write that this very delta is actually epsilon divided by 2 absolute value of a's, right? Well, of course, one could argue that this results into the equality here, right? So this sign is kind of doubtful, but since the previous sign is pretty strict inequality, so we are gonna say that this very relation still holds, or you can just substitute our delta with half of a delta if you really like it. But the fact still holds. Basically, we just proven that our limit of x squared is a squared and arbitrary point a. So for the second example here, let us just assume that we are looking at some function which is clearly problematic at the limit point. In order to do it, we are gonna consider the limit of the sign of 1 divided by x if x approaches 0. And I'm gonna write question mark as our answer. Okay, so we need to answer two basic things here. Does it have a limit, and what its value if it does? So, well, if one just try to draw a sketch of this graph, what we're gonna have? We are gonna have, well, first two axes, and then we're gonna have function which is oscillating, and since we are getting as close to 0, thus 1 divided by x is getting closer to infinity, right? Thus basically it moves from 0 to 2p, which is kind of the period of the sine function, faster and faster, right? So what we should draw here? We should draw here a function that starts to oscillate faster and faster. Okay. Basically, that's a nightmare, right? So, does it have a limit or not? We are gonna try to prove that it does not by using our second idea that for any approach, for any sequence of arguments that approach our limit point, the limit of the values of the function should approach all the same value, which is the limit of the function at this very point, right? So in order to do it, we're gonna imagine basically two sequences. First one I'm gonna call xn, and this will be the sequence where sine, for example, equals to 0. And in order to do it, we're gonna say that the argument of the sine function should be, for example, 2 multiplied by pi multiplied by n. If we rewrite this in more direct form, xn is 1 divided by 2 pi n, which, let us check, approaches 0 if n approaches infinity, thus it's a valid sequence to approach our limit point. Our x approaches 0, right? This one. So, that's our first one, and then we're going to consider some other sequence of arguments. I'm going to call it yn, in which our function actually has, for example, our sine function has value 1, which is half a pi plus 2 multiplied by pi multiplied by n. Once again, in direct form, it is 1 divided by half a pi plus 2 pi n, and it approaches 0 since we get a constant divided by the function which approaches plus infinity. Okay, that's fine. So basically we have two sequences, and then let us just understand that the sign of 1 divided by xn equals to 0, thus approaches 0, and sine of 1 divided by yn equals to 1, thus approaches 1, and this is not the same limits, thus the function doesn't have a limit, there is an absence of limit. So we are going to write that these limits do not exist.
Of course, as we've seen, the idea of calculation functions limit by definition, it's kind of tricky and takes a lot of time. So people don't usually use the idea that we need to come up with the limit and they'll prove it by definition, right? Here comes our basic arithmetic rules. We've already seen them in case of sequence of limits, so let us just reiterate it, revisit, and cover it once and for all. For example, basic rules here are that the limit of some arithmetic operation is the arithmetic operation of this limit. This works for sum, difference, products, and division of functions. Well, basically, the limit of sum is the sum of limits, and so on. But here comes the tricky part. Of course, you shall always think about the division, because division actually produces kind of a headache for us, because it crucially affects the domain and all that. Well, you can't divide by 0. This is a school rule, right? So the thing that should be worried about is that in the denominator you should always get non-zero value. So basically, when we say that the limit of division is the division of limits, we should require that the limit of the denominator in the initial fraction doesn't approach 0. Okay? So that's a nice try. But here is another thing. Basically, what we should expect that the initial function, this very fraction f divided by g, is also defined in some neighborhood of the limit point. Basically, it means that there is a neighborhood of the point a where function g towards x has no 0 values, because otherwise we kind of have in every neighborhood some crazy point with no value, and we cannot proceed with our epsilon delta formal definition of the limit, right? So that's kind of common thing. We've already seen them, we've already tried them. We're gonna look at the example, but let's stress out one more thing, and it's kind of the most important one here. All these rules are true only in case all right-hand side limits exist. Okay, so all this is correct only if these two terms exist. Basically, it means that if you assume that you have some finite limit function, for example, a function equals to 1, you can't change it into, for example, x plus 1 minus x, and consider a, for example, plus infinity, and say that this holds, right? Infinity is not a limit, is not finite limit, so it doesn't exist. And this is a crucial rule that you all should remember. So let us look, for example, some basic thing, like the limit of fraction x squared minus 1 and x power 3 minus 1. So the limit point here is, well, just for now, for example, is 0. Okay, so what we should think firstly, let us try to calculate the limit by our arithmetic roots. For example, if x approaches 0, then x approaches 0. It's quite easy, right? If x approaches 0, then x squared is basically x multiplied by x. Thus, by our product rule, it also approaches 0 multiplied by 0, 0, right? Same thing applies to x power 3. That's what we get. We get basically that our numerator approaches 0 minus 1, our denominator approaches 0 minus 1, and the answer is, by our arithmetic rules, is 1. Okay, that's quite nice. And please note that all necessary conditions for our division rule is actually satisfied, because we do not consider dividing by 0 at all. Okay, that's nice. But what if our limit point is kind of trickier? So we've seen this function with a limit point 0, but now let us assume the limit when x approaches 1. And this is understandably much more worse, because if x approaches 1, then x squared and x power 3 approaches 1, and then our numerator and denominator approaches both 0, and thus we get something which previously was called indeterminate forms, right? You remember, 0 divided by 0 is our indeterminate form. So what we are going to do in order to avoid this one and for the God's sake just get the answer for this example, right? So the idea basically is that we are going to transform this function with equivalent function just by taking the factor of both numerator and denominator, right? So the numerator is basically multiplication of x plus 1 and x minus 1, and the denominator is x minus 1 multiplied by x squared plus x plus 1. So if we divide our numerator and denominator by their common multiplier, x minus 1, then we get a nice function x plus 1 divided by x squared plus x plus 1. As x approaches 1, the denominator approaches, let us see, 2, I think, right? 1 plus 1, 2. And the denominator approaches 3, hence our answer is 2/3, right? That's fine. But let us take a look, for example, at what we've done. We've basically substituted our function, our start, our initial given function, with some kind of other function here, right? So are these functions the same or not? Basically, you can understand that since we've just divided denominator and numerator by its common multiplier, functions are pretty close, except one point. This point is x equals to 1, right? Because at this very point, the initial function is not defined. And the function we've got during our transformation is actually well defined and has a value 2/3, which was our answer, right? So the thing here is that basically we've changed our function, but we've changed our function only in one point. The one point is our limit point, and as we've previously discussed, we do not care about this very limit point, since our limit avoids consideration of the value at the very limit point when we are talking about epsilon delta formal definition. Since we spoke about it earlier, let us revisit the concept of indeterminate forms, right? So whilst we were talking about limits of sequences, we established that there are quite a lot of nightmarish cases when we are not able to tell the limit straight away. Basically, it was cases when just considering our limit of our function by arithmetic rules resulted in some kind of weird result. For example, 0 divided by 0, infinity divided by infinity, and so on. And I'm going to test this out one more time. 1 powered infinity is also indeterminate form, where 1 is basically a function that approaches 1, not arithmetic number. Okay, so once again, let me remind you that all these indeterminate forms are kind of connected, because one can be derived from another, and the basic one is 0 divided by 0. So, for example, in easy case that we have 0 divided by 0, we have, for example, 1 divided by infinity and 1 divided by infinity. Thus, we have infinity divided by infinity. That's pretty easy. We just take the inversion of both functions, and thus we get our infinity divided by infinity. Same applies, for example, for 1 powered infinity. If we consider transition to exponential form of which by the definition of logarithm, then it is exponent of logarithm of 1 powered infinity, right? That's the definition of logarithm. Thus we have exponent of infinity multiplied by a logarithm of 1, which approaches 0, right? So we have our 0 multiplied by infinity, which can be easily truncated into the form of infinity divided by infinity, or 0 divided by 0. So it's basically all the same and have the same roots, so it's kind of nice, but still the general idea is, if you remember all of them, it's much more easy for you to not have any additional mistakes whilst you are calculating limits. So let us consider some example here, and this is the very obvious thing. Let us assume that we are calculating a limit of 2 polynomial functions where basically our main coefficients are non-zero. So we have polynomial function of nth degree in the numerator and nth degree in the denominator, right? And so what's the limit if x approaches infinity? So basic idea here is that let us, for example, divide by x powered n both numerator and denominator, right? So what do we get? In the numerator we get a0 divided by x powered 10 plus a1 divided by x powered a minus 1 plus so on an minus 1 divided by x plus an. And in the denominator we get something a bit more complicated, because if we divide it by x powered n, we actually do not know relation between n and m, so maybe by this very moment we already exceeded all m degrees of x, and we get, for example, a simple polynomial function after division, or maybe not. So let us, for example, consider the case when m is greater than n. Then, as a result of division, we get b0 divided by x powered n, b1 divided by x powered minus n minus 1, plus so on. Here we get some b. For example, I'm going to say that its number is k here, and so on, and after all this division, we get the last multiplier, the last term as bmth multiplied by x powered m minus n, right? So, of course, as you all do understand, this is true for all m and n without any order, but
either the m minus n positive or negative, then the limit of the denominator and denominator are 0 or infinity, right? So let us just gradually solve what we do have here. Firstly, we can easily tackle the denominator here, right? Because all these fractions approaches 0 by our arithmetic rule, right? Because a0 is a constant and the denominator in all these cases approaches infinity. Because x approaches infinity, right? So a constant divided by infinity gets a result as 0, so the denominator actually approaches our a-nth, right? So the same applies for the denominator right up the case of bk, right? If we are considering bk actually approaches bk. So if m is greater than n, then we got a bunch of infinitesimal terms here, then some finite term, and then some polynomial function on the infinity, which is obviously infinity, right? Thus we got a constant divided by infinity, and as a result we get infinity here. It's easy to understand that if we just consider another order here, then we get 0. Oh, sorry, vice versa, obviously. We just get that we, in case if m greater than n, we get a constant divided by infinity, thus we get 0, and as for the other case, we get infinity divided by constant, which is infinity. So that's quite nice. But what about the case where m equals to n? And that's quite easy, because that basically means that after our division by the x powered n, we get only our main coefficients here, and the answer is an divided by n bm, or bn since n equals to m, right? So that basically covers all possible relations between two polynomial functions with infinite argument here, right? So we've just resolved the indeterminate form for the case of infinity divided by infinity. Let us also assume one of the cases that we've actually seen already for the sequences. Remember, we've considered sequence sinus n divided by n. Yeah, and we spoke about that sine is bounded function, thus it's easy to think about two boundary sequences for this one, which approaches the same value, right? So let us try to extrapolate this rule basically for the case of functions. Let us look, for example, at these two equations and these two graphs. Basically, we are looking at pretty much the same example as in sequences, because we are looking at sine divided by some in unbounded function x, or in other words, we have some bounded functions sine x and infinitesimal function 1 divided by x, which approaches 0, right? So the idea here drawn in the figure, this is our in blue curve our function, and here comes two basic boundaries for it: 1 divided by x and minus 1 divided by x. And since both of them approaches 0, thus our function approaches 0, right? So basic idea here is that if we considering the product of bounded and infinitesimal function, the result is infinitesimal. So thing is quite clear, right? 0 multiplied by something which definitely has some finite limit, but is just simply bounded, is not growing unexpectedly, or isn't just happens to be some extraordinary large functions from time to time, simply bounded, multiplied by infinitesimal, infinitesimal. Same thing apply, for example, for our second function here, because what we do have here is we have x multiplied by some nightmarish cosine function, cosine of exponent of integer part of 1 divided by x factorial multiplied by the x, and this is quite, well, actually frightening. But since cosine is bounded by -1 and 1, and the rest of the function is bounded by 0 and 1, all this multiplier is bounded. Thus, we actually have our infinitesimal function and bounded function. Thus, the limit is simply 0, and we can just move over. When one is talking about functions limits, it's hard to not talk about two very basic things here, which are sometimes referred as important or fabulous or whatsoever. There are two limits that everybody should know, and everybody does really heard of them at least quite a bit. So the first one is already known for us, is a definition of exponent, right? Base of the natural logarithm, whatsoever, the e constant. So what do we have in case of our sequences? Now, sequences, we've talked about that if we're considering the sequence 1 plus 1 divided by n powered n, it approaches some newly defined by with this relation constant e, and that's kind of the definition, right? So the trick there was that this thing is bounded and monotonically grows, thus we have some kind of limit, and we should call it something if it is not a known number. Okay, so let us make a simple transition into the case of functions. Since 1 divided by n approaches 0 as n approaches infinity, then we can just substitute it with a real variable x. Thus we get 1 plus x powered 1 divided by x approaches our e constant if x approaches 0, right? So that's easy, that's quite nice, that's basically a generalization of what we already know. The second limit that everybody knows and we should talk about is a limit concerning trigonometric rules here. Basically, the idea is that as an angle approaches 0, that the sine of its angle is basically an angle itself. Or in other words, the relation between sine of x and x equals to 1 as x approaches 0. So in order to get a sense, get an understanding of what it is, let us do some basic picture about the areas on this graph. For example, let us assume that we are considering the circle with radius equals to 1, so our unit circle, and we are looking at a sector with an angle x, right? So what's an idea here? The idea here is that if x is measured in radians, then the area of this very sector is basically x divided by 2, since the area of the whole circle is pi. As you do remember, the area of the circle is pi multiplied by the radius squared, right? So the area of this sector is proportionally half an x, right? So we have two things here. Firstly, we have a red triangle which lies within our blue sector, thus it has a smaller area, and we have a green triangle which lies, which basically has a sector included in it, thus it has a greater area. Both sides of red triangle equals to 1, and since we know the angle in between them, then the area of it is 1 multiplied by sine of its angle halved, or just sine of x divided by 2. That's nice. Thus we get one boundary here. And as for the green one, we do know that by definition one side of this triangle equals to 1, so the radius of our square, of our circle, and the other side is basically by definition of tangent function is tangent of x. Thus, in order to compute the area of this triangle, we need to remember that it's orthogonal, thus we can just multiply these two sides and divide them by 2, thus we get a tangent of x divided by 2, right? In other words, is sine of x divided by 2 and then divided by cosine of x. Well, since cosine function approaches, let us revisit it. You do remember, as sine approaches 0, if x approaches 0, then cosine approaches 1, as sine approaches, as x approaches 0, right? Thus, it approaches 0, and if we divide both sides by x, for example, or by sine of x, thus we get that sine of x divided by x approaches 1 in the both sides. So we've actually just proven this very limit. That's nice. So let us consider, for example, some example for it. We are going to go for the combination of these two limits and compute a limit as x approaches infinity, sine of 1 divided by x plus cosine of 1 divided by x in power of x, right? So, in order to do, firstly, let us assume that we just substitute 1 divided by x by a new variable t, and t approaches 0 as x approaches infinity, right? Thus, we have a nicer form, sine x plus cosine x powered 1 divided by t. Just let us remind us that our new variable is called t, all right? So, in order to properly do it, we just let us revisit the initial expression here and assume what we are looking at. Just let us try to use our arithmetic rules. Just consider the limit of all the terms in here and decide whether it is or not the indeterminate form, right? So if x approaches infinity, then sine 1 divided by x approaches 0, right? Because sine of 0 is 0. Same applies for the cosine. Cosine of 0 is 1, thus our bracket approaches 1, and all the function is basically the indeterminate form for 1 powered infinity, right? So in order to avoid this, we are gonna to artificially get the form of our definition of E, of our first important limit here, right? So in order to do this, we need to artificially add and then subtract the number 1 in the bracket, right? So we get 1 plus something. Something is sinus t plus cosine t minus 1, right? That's our kind of new x here, the x from there, in the power of 1 divided by t, right? We know that if we divide it by the very idea of 1 divided by x, our new x, right? Thus we get an exponent here. So we need to do the same. Basically, we need to artificially form 1 divided by new x here. In order to do, we are going to, first of all, write exponent, and then we are going to multiply our power here by sine t plus cosine t minus 1. Thus, this multiplier will get us an exponent, and the rest of it will form sine t plus cosine t minus 1 divided by t. So, is it enough? Maybe we can just write the limit straight out loud. Well, still kind of not the case for us, because let us look at it closely. Sine t approaches 0, cosine t approaches 1, thus all the numerator approaches 0, and t approaches 0, thus we get indeterminate form 0 divided by 0, right? But if we just consider cosine t minus 1, we can remember that this is basically the idea when we have basic trigonometric formula here, right? Because 1 minus cosine is 2 sine squared of half an angle, right? And if we look at 2 sine squared divided by t, it basically results into sine of half a t divided by half a t multiplied by sine of half a t, right? And if it is true, thus the first thing, according to our second important limit, approaches 1, the second thing approaches 0, thus this term approaches 0, and the first term approaches 1. Thus we get exponent of 1, or just our constant e. Okay, that was rather complicated, but as you can see, just substantial use of two important limits can get us basically to the answer without any generalizations or hand waving. Now, since we get the idea of limit of functions, let us consider the idea of comparing functions pointwise. For example, an essential thing here is to understand whether or not the behavior of a function in the given point coincide. For example, let us look at our important limit number 2, sin x divided by x. Basically, it means that sin x and x are pretty much the same functions in around 0 point, right? Basically, it means that they're equivalent. You can substitute one with another without any extensional error, right? So here comes an idea that some functions have this property, right? That they are basically the same if we get some kind of limit. And if we consider that our life is just restricted to the area close to, for example, x approaches 0, right? To the neighborhood of x. But some functions do not. So we can somehow consider that there is some kind of class structure or in round functions at the given point. Well, sometimes for example, it's essential in case of programming and all the other stuff. We've considered the case of equivalent functions, but some functions are not equivalent, but are extremely close to it. For example, consider some two polynomial functions right here. For example, x squared and, well, just for the sake of this slide, 5x squared minus 100x, it doesn't actually really matter. They are different, obviously, and we've actually calculated the limit of its relation, right? Do you remember? We've talked about the case of division of two polynomial functions if x approaches infinity. So these functions are not the same, they are not equivalent. Their relation, for example, first divided by second, results into the limit value of 1/5, right? But it is still extremely close together. They're closer than the case, for example, x power 3 and x squared, or x and x squared, or, for example, natural logarithm of x and x squared, right? They're somehow close because they're both relate to the case of quadratic functions of x. So it's kind of essential for us to speak about the classes of polynomial functions, that they relate to the same class here. Well,
sometimes we do not actually understand what's the difference between the functions amongst that class, or we do not know the specifics of functions except this function belongs to the given class. It happens, for example, if we consider the time of the program implementation, of the code implementation, or just the time of some algorithm, right? So what's an idea here? Assume that, for example, you're considering some basic programming task. You have a set of real or natural numbers, n numbers, for example, and then you need to come up with an idea how to sort them, for example, in descending order or whatsoever, right? Let us assume some basic bubble search. You all know the idea here is that you are just running through the numbers in one direction, and if two neighbors do not stand in the right order, then you just switch them, okay? So that's kind of an easy thing, and the idea here is that you need to do, for example, n multiplied by n minus 1 divided by 2 switches here. Okay, that's kind of nice, but here comes the problem. First of all, that's our algorithm, right? So basically, we've established the procedure, but we do not speak about the actual time it took, because, well, assume that first, for example, you've got real numbers here, but maybe you've got, instead of real numbers, for example, chapters from Tolstoy, World and Peace. It's quite hard to compare, well, in comparison to real numbers, because you have two strings, very large strings, and for example, then you got, well, binary numbers and you need to sort them, right? It's kind of different thing, and it takes different time to compare. And the last thought that gives us a headache is basically just assume that you are running the same algorithm right now on your very favorite, I don't know, laptop, phone, iPad or whatsoever, and you just time traveled into some past. For example, you are in the late 90s and you are looking at this very lamp computer which takes the whole room, and then you just running pretty much the same algorithm on whatsoever coding language there is, and then basically you should understand that times differ, times of implementations, times of that your code works quite differs, right? And that's basically the idea when you need to understand that we have some constant multiplier here, which, for example, can be interpreted as the time your machine took to compare two numbers or to swap two numbers. And it depends on various things, on the structure of the objects in the set, or, for example, well, on the date you've time traveled to, right, Doc? So basically, we do not know the idea, the exact form of function, but we do know that the class of this function is pretty much the same as we spoke earlier. It's a quadratic function, right? So it's nice to have an understanding how to tell whether the functions lies in the same class or not. So let us proceed with the idea of comparing two polynomials, for example, and deciding whether or not they belong to the same class. So we define the class itself. In order to do it, we start with the idea of big O notation, which is sometimes denoted as underlined O in handwritten text. And the procedure here is follows. Basically assume that we have two our functions as x squared and 5x squared minus 100x. We somehow are talking about the upper boundary of one function with regard to another. Basically, it means that one function is greater no more than in some fixed number of times than the other one. In other words, we need to write down an inequality here. Basically, assume that we have some neighborhood of our given point, A. For example, we call one function big O from another function in this neighborhood. If there is some constant, positive constant C, such as the relation, absolute value of the relation of functions f and g does not exceed this value C. Okay? So let us consider, for example, our case. We have x squared, for example, let us call it f is x squared, g is 5x squared minus 100x, and we'll assume that x approaches infinity. So what we're gonna do? We're gonna say that some function is greater than the other in some neighborhood of infinity, right? We need to write down something like absolute value of f is less or equal some constant multiplied by absolute value of g. All right. In other words, x squared less or greater than some constant multiplied by absolute value of 5x squared minus 100x. It's quite easy to understand what constant is actually good for us here. For example, I start with the constant c equal to 1. Well, it's kind of obvious that it is, because if we just assume that c equals to 1, thus we get x squared on one side and 5x squared minus 100x on the other side. If we subtract x squared from both sides, thus we get functions which are clearly positive from some point, because we are looking at a parabolic function with positive main coefficient. Thus there is a root, and after this root we do have only positive values. Thus this inequality holds, and 1f is big O towards G. Okay, that was one example. One could easily argue that if we need to swap this function, that still holds, just because instead of writing c equals to 1, let us try to do this accurately here. So basically we need to prove something like this here, right? So in order to do it, we need to consider another c, not a small one, but a greater one, right? So basically, if we start with like c equals to 5, then we get a nice result here. But it's not always the case, because, for example, let us look at some more interesting case. For example, let us assume functions sine of x and x as x approaches 0. Okay, we do know what? That they're basically equivalent. Thus, one should expect that sine x is basically a big O of x, right? And it's quite easy, because the absolute value of sine x, as we stated whilst we were talking about our second important limit, is no greater than modulo x, because the absolute value of x is actually the area of a sector, and sine of x is the area of the triangle, respectively. So thus we get that using a constant c equal to 1, we get this absolutely right. Okay, but what if we substitute the point of interest from 0 to, let us say, infinity? First of all, the idea that sine of x is big O towards x still holds at this very point, because basically sine of x is not greater than 1, and x is as great as you can imagine, x approaches infinity. Thus this inequality still holds, for example, for the same constant equal to 1, right? But if we change it, if we change two functions, then we get pretty conspicuous thing here, because sine x
and x is not related in times, right? Because sin x is still... Sorry, I've told you that we need to swap functions and didn't do it. So it's kind of great deceit here. Okay, so it's less deceitful. So x is big O from sin of x, right? So basically sin of x is bounded by 1 and minus 1, and x is unbounded. Thus, if we try to come up with the idea that x should be less than some constant multiplied by sin of x, and we say that this constant, for example, 10,000 or whatsoever, then we can, for example, take x larger than 2 c's, and this equation will almost definitely just fall off, and this is extremely not the case, it's not right. So when you are talking about big O notation, you always need to consider the order here. What function with regard to what function is a big O, okay? So So, recently we've discussed the case where two functions relate to one to each other as a constant multiplier, right? But sometimes it's nice to understand that one function, for example, decreases sufficiently faster, grows sufficiently faster than the other. For example, consider the case of x squared and x in around 0. If you do remember its graphs, basically x squared and x do relate in the following manner. X squared decreases to 0 as x approaches 0 much more faster than x itself, right? In a way, it is sufficiently fast by the means that it cannot be truncated to the case of not faster than some finite number of times, as in big O, right? So we can say that it's kind of a different relationship if it is a relationship which is called little o or infinitesimal towards some other function. Okay, so what it is here? Well, there's a nice picture of our x squared, and x powered 3. One function is called little or infinitesimal towards the other if its relation approaches 0 as x approaches our limit point a. So that's our formal definition. In other words, one function is infinitesimal function alpha multiplied by the other. It's quite easy, right? In case of x squared, it's basically x multiplied by infinitesimal function x. Okay, that's nice. Let us consider some examples. For example, okay, pretty much same thing. Nothing ever changes here. Start with two polynomials. What we should decide? We should decide whether or not their relation approaches 0 as, for example, let's start with x approaches 0. Does this relation approaches 0? Let us write it in a manner x powered n minus m, and it approaches 0 only in case if n is greater than m, right? Because if this power is negative, then we have the same thing as 1 divided by x that approaches infinity, right? So this case is solved. But what is about x approaches infinity? That's basically vice versa. All the same thing. This power should be negative in order to be 1 divided by x or so on, which approaches 0 as x approaches infinity. Gonna stress out the following thing. There is no less or equal or greater and equal, right? Here, these are strict inequalities. And that's basically the difference between little o and big O in terms of polynomial, right? Okay, as for the other example here, we are going to roll with an idea of sine of x and x as it approaches 0. So, what we do know? We do know that sine of x divided by x should approach 0 in order for it to be infinitesimal one toward the other, right? Sign towards the x. But as you can clearly see by our second most important limit, it approaches 1. Thus, if x approaches 0, sign of x is not infinitesimal towards x, right? It's equivalent toward x. Well, it's kind of well stated. But in case x approaches infinity, that's the limit we've covered recently. You do remember. This is bounded function sine multiplied by infinitesimal function 1 divided by x. Thus the limit equals to 0, and little o notation holds. Sine is infinitesimal towards x if x is unbounded. That's nice. Since we know the definition of little o notation, let us revisit it. Firstly, what we stated? We stated that f is little o towards g, or f is infinitesimal towards g, if its relation approaches 0. Or in other words, f is the result of product of some infinitesimal function and g function, right? So, let us consider the following puzzle. What does it mean if some function is little o towards the constant function 1? As, for example, x approaches a, which doesn't actually matter for our case. It basically means that this function f is the result of product of infinitesimal and function 1, constant 1, right? Thus, it basically means that our function is infinitesimal, written here. But also, let us assume the following case. Assume that our function f has a limit, for example, capital A at the point A, okay? Thus, the function f minus a, our capital A, f minus its limit, is infinitesimal by our arithmetic rules as x approaches limit point, right? Thus, we can write it down that f minus a is little o towards 1, or in other words, f is its limit plus some infinitesimal function. That's kind of obvious, but that's a nice notation. Why? Because let us consider, for example, our second important limit here. Basically, using our just established relation between function limit and little o notation, we can rewrite it in the manner that sine x divided by x equals to 1 plus little o towards 1, right? That's kind of nice. But then you can just rewrite it in the following manner. Let us multiply both sides of the equation by x here. Thus we get sine x equals to x plus. And here comes the trick. Formally, we should write x multiplied by little o towards 1. But you do remember, the little o towards 1 is basically any infinitesimal function, right? But what is the product of infinitesimal function and some other function? It is infinitesimal function towards the function itself, right? Basically, here is written little o towards x. So let's just interchange it. In other words, multiplication in terms of little o notation, it's kind of naive and intuitive. You can just multiply not the function itself, but just the argument of little o notation, right? Okay, so why does it help us? Let us rewrite this very relation in terms of half an angle. For example, sine of x divided by 2 is x divided by 2 plus, once again, we need to formally write little o towards x divided by 2. But since we are talking about infinitesimal functions, division by 2 doesn't change the fact that we are looking at infinitesimal function, right? Thus, we are gonna omit any constant that appears in infinitesimal notation here and just write down little o towards x. So remember, basic trigonometry, 1 minus cosine of x is 2 sine squared of half an angle. Let us substitute our sine of half an angle with our fancy little o notation. Thus we get that the cosine function is 1 minus 2 x divided by 2 plus little o towards x squared. Or in other words, 1 minus x squared divided by 2 minus. That's gonna be extraordinarily complicated, but we're gonna live through it. Just hold on. First of all, we need to write carefully down what we're getting here. We should get 2 multiplied by x divided by 2 multiplied by little o towards x, right? So we get 2x little o towards x minus 2 little o towards x squared, right? So let us spend some time with the last two terms here. Basically what we are looking at is constant multiplier, which we do know it doesn't matter, we can just omit it to the sake of little o notation. And we are looking at multiplication by x. We've just established that that can easily be put into the argument of little o notation. Thus, this term is basically infinitesimal towards x squared. Same applies in the case of the second term, in the following manner. If we have two functions infinitesimal towards x, thus it's basically infinitesimal function multiplied by x squared. Thus we get infinitesimal squared multiplied by x squared, or simply infinitesimal towards x squared. It's easy. So as a result, we get 1 minus x squared divided by 2 plus little o towards x squared. And this is the asymptotical understanding of cosine function in the neighborhood of x. Is basically 1, and then we get our square quadratic function, right? That's nice, and for some of you who know, that's basically the start of the Taylor series for the cosine function. Done extremely easily, extremely fast for the little o notation. So, since we've covered the idea of single-variate functions, it's time to think about the limits for multivariate functions, because let us face it, in real life we do not normally think about that real life function is a function of a single variate, right? Because, for example, the price of your apartment does not depend only on the area of your apartment. It depends, for example, on number of rooms, number of rats to hunt, number of ghost stories in it, right? So basically we get as a result function of quite a number of degrees of freedom. The thing is that we are going to consider only function of several or finite number of variables, right? So it doesn't mean that that's the only case, and one cannot consider, for example, the function of infinite number of variables, but it's kind of unrealistic, and we are going to stay on the ground at least a little bit. So what is a multivariate function? Multivariate function is a mapping from some n-dimensional vector, an n-dimensional set of real numbers to real numbers. As notation written here, basically what is real numbers power 10 is Descartes product of n real number sets. Okay, that's an easy one. Basically, what is, for example, r squared? It's a real plane where r is multiplied by r,
or just you are looking at all possible pairs where the first element is real number and the second element is real number. The same applies, for example, for R-powered 3 or three-dimensional real space. You are looking at the set of three real numbers where first element is all possible real numbers, second element is all possible real numbers, and the third can be all possible real numbers. So usually we will consider only the case of function of two variables, firstly because it's easily generalizable from this point onto all finite number of variable case. And it's quite easy to draw. It's basically the only thing that's easy to draw in a multivariate case, so we will consider only this case. So firstly, we need to state that all the terms that we've defined for single-variable functions or functions at all pretty much hold and remains the same. So we know that what is a domain, the set of all possible variables, what is range or codomain, and what is support of the function. But we're gonna say that from now on, the graph of the multivariate function, or for example, the graph of two-variable function is called a surface. Basically, what it is formally, it is a set of all three-dimensional points as x, y, and f towards xy. Here, which is, well, you know, for example, consider that you are taking a sheet, a clean sheet, and then just throwing it into there, and it is somehow curved into there while it's flying, and that's what is a surface is. Okay, so the trick here is that it's hard for our brain to imagine a surface just by the equation or just at all understand how it looks like, because you need not only to draw it but to imagine it and find the idea of how to rotate it, what turned into what's the result in different sections. Well, that's totally a nightmare in a short words. So we've come up with another idea. Basically, the idea is that if we have a surface, we are kind of want it to be described by our plane picture, plane figure. And in order to do so, we introduce the concept of functions level, or C level. Basically, what it is. Consider that we have an equation f towards x and y, basically our function equals to c. We are interested in all possible pairs, all possible real dots x and y, which satisfies our equation f equals to c. This says this curve on the plane is called functions level. Okay, obviously function has a lot of labels since functions have a lot of different values, right? Let's try to prove some basics here. For example, everybody understands that for different levels do not intersect, right? Because if two different levels intersect, it basically means that they do have some common point x and y, and thus at this very point function is supposed to have two different levels, two different values, which is not possible for the functional mapping, right? Okay. And the second one, for example, each point in the function domain belongs to some level, which is kind of pretty much the same. Assume that we have some point in the domain xy. If it is in the domain, thus we can apply a function to it. Basically, we can consider function's value at this very point. Thus, we have a level which is determined by the value of the function at this very point. Okay, fine. Let us consider some example. For example, let us take pretty awesome linear function x plus 2y's. And we are aiming to draw its levels. Firstly, let's start with writing down an equation. X plus 2y's equals some level c. Right, so let us just
move x to the right part, divide both sides by 2, and thus we get our usual equation of a straight line, except we need to write it carefully down. So what do we have? We do have a straight line with different vertical shifts, which is related to different levels, and the same slope minus 1/2, right? So we need to draw several lines with minus 1/2 slope here. That's our levels. And to finish it off, it's usually common to draw an arrow which implies that going from one level to another in the direction of this arrow, the level rises. Basically, since our sea level is included as positive value into vertical shift, the higher the level, the higher the value of the function on it. So level rises into the opposite direction. Okay. So let us move on to other thing, which is, well, another example, which is the maximum value of two absolute values of coordinates, right? So it's kind of important for example, functional analysis, because the idea of maximum of two absolute values is, for example, one way to determine the distance between two dots in two-dimensional space or whatsoever. So what we're gonna do? We're gonna write an equation down, and basically what it means. It basically means that we have to choose firstly which variable has the greatest value, and then we're gonna say that this variable is fixed with c. Since we are looking at absolute value of x and y, thus the picture is gonna be pretty much the same for all quadrants here, right? So we are going to consider only positive x's and positive y's. Thus, we are looking only for max value of x and y equal to c. Assume that x is greater than y. Thus, basically, it means that x, all points lies below this y equal to x straight line. Thus, we need to draw a line which coincides with the idea that x equals to c. This is a vertical line. Okay? Well, and as you probably all understand, the same applies for the upper part, which coincides that y is the greatest value, y holds the maximum, thus we got this right angle here, and by the symmetricity of absolute value, we got such a nice square with the center in 0. Let us draw several levels, and then let us state that we are talking about expanding levels from center to the outer space. Okay, and as a final touch, let's consider the graph here itself, and what we are basically looking at. We are basically looking at several sections of this graph by horizontal planes, such as z equals to c. So to finish it off, let us consider some other example, which is x squared plus y squared, and it is extremely easy, but this is kind of curve we're gonna to look at quite a lot. So the levels are quite straightforward. Firstly, let us state that this function doesn't have negative levels, all values are positive, and these are equations of a circle with the center at 0. Thus we get the following levels: concentric circles, and as in previous example, the level rises right from the center to the outside. Okay.
the surface of this function looks something like this. This is paraboloid. And the one thing I'm going to say here, basically what we're looking at is a function which is not directly from two variables, because as you can understand, we can add a square root and return it by adding power 2 here, right? So basically the thing which is written under the outer power here is the distance between a point xy and point 0, 0, right? Basically it is the distance towards to the 0 value, right? So this function does not actually depend on to x and y separately. It depends only on the its distance to the 0 point. Thus basically it means that on the circle with the same radius, well, if we just fix the radius, fix the distance towards the 0 point, this function remains the same. Or basically you can just take a function with, for example, y equal to 0 and then rotate it by its OZ axis, and then you will get this pretty nice surface. So now we know the definition of multivariate function and know how to draw some understanding of it by administering the levels of its function to the graph, right? So now let's talk about the limits of the multivariate function. Let us just stick with our basic understanding of what the limit is. The limit is the value that our function resembles the most. Basically, what it means for our multivariate case. In our multivariate case, we can just generalize our extremely complicated but useful definition with epsilon and delta technique, right? So, what we've been saying in it. We're basically saying that the value c is called function's limit in some, for example, two-dimensional point whatsoever. If for any given deviation we can go as close to limit point, that function do not deviate from our limit sufficiently, well, much more than our defined deviation, right? Okay, that's basically what it is, and it doesn't change at all, but the phrase we can go as close to our limit point implies that we now can say what is close to our limit point and what is not. So basically what we're talking about our point AB, we're talking about some arbitrary point xy, and we're gonna say that the distance between these 2 points are smaller than, for example, our delta, then it is delta neighborhood, or we're in a close neighborhood of our limit point. In order to do it, we need to understand some basics. For example, how to calculate the distance between point x and y and a and b. And in order to do it, we're just going to use straight out Pythagoras theorem, which is, well, always you don't know what to do, use Pythagoras theorem. So our distance here is basically square root from sum of squares of the sides of this triangle, which means that it's square root from x minus a squared plus y minus b squared. Okay, that's nice, but how does it differ from the case of single-variate functions? From the standpoint of definition, it's pretty much the same, but let us consider, for example, our real plane, and we are looking at some our limit point AB. Okay, so what should we expect? Previously, what we've talked about? Previously, we've talked about that we are just trying to get as close to our limit point from all the possible straight directions, right? You do remember we had two definitions, one complicated, with epsilon, delta, and 1 with sequences, right? So sequences basically told us go to the limit point as close as you can, then the limit of the sequence of actions values should approach all the same value c, right? This can actually be easily extrapolated here, but, and this is a very big but here, now we are considering all approaches on the plane, not on our green straight line or our real numbers. Okay, so now we can go, for example, from the left, from the right, as in single variate case, but also vertically from the top, or by some straight line here, or maybe just by parabola, or just by some random points into the plane. The only rule here, we need to approach our limit point AB. Okay, so this is extremely more complicated because we have additional degree of freedom, additional variable y. Thus, we need to consider much more possible approaches that we can use to get to the limit function, limit point. And more importantly, the idea that we need just to consider limit by one variable and then by the other will not suffice by the very idea that that's only one way to get here, right? It's like right English way. Just firstly, you need to throw yourself onto the, for example, OX axis or Y axis, and then you need to consider only one variable. This is only two approaches. We need to consider them all. So let us revise what we do have here. Since we've established that we need to consider all approaches to prove, for example, or calculate our limit, we need to prove that on all approaches we get the same results. It's kind of nightmarish. So the technique we are going to use primarily in order to calculate function limits is basically to truncate this calculation to the case of single variables. For example, change all the calculations we are doing into the case of single variate functions by substituting variables, by grouping variables, by just subtracting and just turning our function into the pieces of single variate functions at all. Okay, so but to prove the absence of the limit, it's quite nice to consider that we can just demonstrate a pair of approaches, for example, horizontal or vertical one, or some others, with two different limits, and thus the limit itself won't exist. So, for example, let us take a look at basic polynomial function. Do not be disturbed by the last term. As you can see, it's basically polynomial, just we can get rid out of brackets, and thus we will get a pretty nice polynomial function. How can one say that the limit of this function is easy to calculate? Because it should be easy to calculate, let's face it. What if the polynomial function is not easy to calculate, right? So basically, first of all arithmetic rules are the same because the definition is the same, right? Thus, we should consider only the limits of the terms separately, right? So in order to consider the limits of these terms, for example, let us take the term 5y powered 5 multiplied by x. Okay, why it is easily truncatable to the case of single variate function? Because it's easy, the product of single variate function y equals to, well, function equals to 5, function equals to y powered 5, it's single variate function towards y, right? And the product of function x, which is single variate function towards x. Thus, it approaches 5 approaches 5, y approaches 1, thus y powered 5 approaches 1 powered 5, and x approaches 2. thus this term approaches 10. Okay, that's easy, and thus we can calculate the limit of this polynomial just variable-wise. To proceed further, we will consider some more complicated examples in the following video. So let us consider more constructive examples of limits of single variate functions and the cases of its absence, right? So first let's start with the idea that we sometimes cannot just separate variables into single variate functions. Sometimes we need to group them. For example, consider the limit when x and y approaches point 0a, and we need to find limit of sine of products x and y divided by x. So, of course, one thing that we can always do, we can decide whether there is or not the indeterminate form, right? But it's quite easy because the product of x and y approaches 0 multiplied by a approaches 0, right? The sine of 0 is 0, thus we divide 0 by 0, and this is definitely indeterminate form. So we need to do something with it. Firstly, the thing that it resembles is our second important limit, right? Which was sine t divided by t, right? It approaches 1 as the argument approaches 0. So we need to somehow come up with the same concept here. Basically, let us assume that since we do not know any formulas from trigonometry which separates in the sign of product, thus we need to group the variables in the sign into new variable t, right? Thus, if we find this t variable in the denominator, then we can get our second important limit here. In order to do it, we can just simply add y multiplier and divide by a multiplier our numerator and denominator. Then what we are looking at sine of t divided by t, that approaches 1, multiplied by function of one variable y that approaches a by our task. Thus, all limit equals to a. That was easy. Let us consider the nice view on the surface, and we're actually talking about the limit at this very point. This is 0, and this is our z-axis, right? So this is a nice point. As always, I've attached these graphs into additional materials, and you can rotate it and play with it after the lecture. So, this was a nice and rather simple example. Let us move to more frightening one. Okay, this is the function when we are considering the limit at point 0, 0, and it is the division of two polynomial functions, which should be nice, obviously, because in single variate function it's always for one of the simplest cases, right? So, what happens if we consider xy divided by x squared plus y squared case, right? Well, basically speaking, this is a nightmare, and I'm going to show you it in the following manner. Firstly, let us assume that we need to have some understanding of what it can be in the result. So we need to find any possible candidate for a limit, and in order to do so, we consider some direction of approach of 0, 0 point. For example, I'm going to consider the horizontal approach where x equals some parameter t and y equals to 0, and thus we need to find the limit when t approaches 0, right? So let us substitute x and y with our directions. Thus we get t multiplied by 0 divided by t squared plus 0 squared, which basically means that we are considering limit of 0. Not infinitesimal function, but 0 itself. And the limit of 0 is simply 0. Okay, That's nice. The same applies for vertical direction, for example. But if we just play along with the direction, for example, x equals to t and y equals to t, this diagonal direction, thus we get pretty much different function as a result, because it results into t multiplied by t divided by t squared plus t squared as t approaches 0, or in other words, 1/2. Since 1/2 is not a 0, this function doesn't have a limit, and this is very important. And let us see what it basically means for our surface. Basically, for our surface, let us look. It means that here we have a vertical line. In other words, if we just consider direction x equals to t and y equals to, for example, kt, which is any straight direction towards this 0, point, right? Then our functions turned into kt squared divided by k squared t squared plus t squared, or k divided by k squared plus 1, which is a constant. Thus, all these directions are our levels. Or basically, what we are looking at function with such nice rays as levels, with 0 levels on the axis and 1/2 on the center. Basically, our levels grows here, but at the 0, point there is all possible levels. Basically, we are looking at function which resemble all possible constants from 0 to 1/2, which kind of implies that there is no one constant to rule them all, there is no limit. Okay, so polynomial divided by polynomial can be nightmarish, but does it mean that it is always like this? Well, it does not. Consider that we increase the power of polynomial in the numerator, and then maybe here we can get our nice answer. Okay, firstly, the easiest thing here is to call the limit, because if we just consider our horizontal approach, or just a common case, because we have a polynomial of higher order in numerator than in denominator, thus by our consideration of little o notation, we basically get that this numerator is a little o with regard to denominator, thus its limit should be 0. Well, in the horizontal notation it basically proves our point, because the function turns into 0 itself. Okay, how one should prove that this function approaches 0? Since it's kind of hard to move towards a single varied case, we are going to write the following. We are going to find a boundary on the absolute value of this function, which is single varied function. For example, assume that we expelled from the denominator plus y squared. Thus, denominator necessarily becomes a low value, right? Because y squared is non-negative. Thus, if denominator is lower, then the whole fraction is becomes greater, which is x squared multiplied by y divided by x squared, or just y. Y approaches 0 if y approaches 0, thus basically our function is bounded by y and minus y. All of it approaches 0, thus our function approaches 0. Okay, we proved it. That's nice, and let's take, for example, a look at this surface. It's kind of, well, pretty much awesome surface. It's not extremely damaged, not extremely complicated, just nice curve of paper here. Okay, and as for the last trick that I'm gonna show you here, let us consider pretty much the same function, but in order to prove that something is 0, sometimes people use so-called polar coordinates. It basically implies that we can rewrite our x and y coordinates in terms of the distance to 0 and an angle with, for example, x-axis. Thus, x turns into r cosine of phi angle, and y turns into r multiplied by sine of phi angle. And our idea is basically that we have our function minus its possible limit should be bounded by some function which depends only on the distance towards the limit function, and it approaches 0. It's basically the definition of our limit. It means that the deviation from the limit of our function tends to be less and less if we close and close to our limit point. Okay, so let us check it for our function. Basically what we are looking at r powered 3 multiplied by cosine squared multiplied by sine squared, which doesn't actually matter because we are going to take absolute value, and sine and cosine function are bounded by absolute value with 1. And the denominator is basically r squared. Minus possible limit is 0. Thus we get, after dividing numerator denominator by r squared, we get r multiplied by cosine and sine. And in order to expel the angle here, expel the direction, just to leave understanding that we depend only on how close we are to the limit point, we're gonna say that both cosine and sine function are not greater than 1. Thus it all bounded by the distance by r, and r approaches 0 as r approaches 0. Thus basically we've proven the definition of the limit, and thus we've proven that the limit of our function is 0. It is sometimes a nice trick when you see, for example, these expressions x squared plus y squared, which is r squared, a lot in your function, or for example in the denominator. Hi, welcome to the third week of the calculus course. Recently we have covered the concept of limits for various entities: sequences, single-variate and multivariate functions. Now it's time to turn to more sophisticated and far more famous subject: derivatives. It's just a common knowledge that calculus course is mostly about derivative. The problem here is that most people didn't realize that it's not where it ends. Sorry. Anyhow, the proper way to properly start to study something is to understand why we are studying it. So imagine the following case. Assume that I have to travel from home to work, say 100 kilometers. And, well, say it takes 2 hours for all the way. Thus my average speed is 100 divided by 2, 50 kilometers per hour. And say the limit here is 80 kilometers per hour. Does it necessarily mean that I will not get a ticket for speeding? Well, in case I was driving all the way with the same speed, which is my average speed, like the blue curve on our graph, it's actually right. But in real life it's not. In real life my 50 km per hour argument won't stand in court, because the court actually cares about whether I was driving under the limit all the way through at every point of my way and every point of time. So, in order to understand whether or not I'm getting a ticket, we need to introduce ourselves to a concept of instantaneous speed, the speed of change of my distance from home at every moment of time. That's what derivative means.
So in the following week, we are going to firstly define a derivative, understand basic arithmetic rules for it, and then move forward linear approximations with the use of derivative and derivatives of higher order. So let's begin. I'll see you in the following video. So, in order to define basic speed of change, we need to think about the most simple example here. And the simplest example is actually what we've seen for the average speed. It's a case of a straight line. If we go in all the way with the same average speed, then we know actually what's instantaneous, which is constant speed of change. So let us extrapolate this idea for the case of arbitrary function. So assume the following puzzle, that we have some function f and we have some given point a. What is the closest linear approximation which is the most fittest function for our case in a given point? So let us draw some case. For example, like this. Here is our blue function f and our red approximation drawn. That's our given point A, and well, the second point of intersection we will call x for the sake of simplicity. Is it a good approximation? Well, it depends. From our standpoint of view, it kind of works. But if we just imagine that we live only inside this red square, it kind of actually not such a good approximation, and we need to move our second intersection point closer to the point A. So let us assume some basic definitions here. Firstly, the line that we have drawn recently is called a secant. It's a line which simply intersects our graph twice in the close neighborhood of the point A. And that's not the droid we are looking for. So we've decided that we need to move our point of intersection x towards our given point A. And the idea here is that how close we need to move it? Well, we're kind of expected to move it infinitely close to the point A, which means that we're taking a limit of a second line, which is actually called tangent line. And tangent line here drawn with a green color is actually our answer. So what's about the derivative? Derivative stands for the speed of change, and the speed of change in our case is a slope. So we need to simply define the slope of our green line. In order to do so, we define slope of every second line, which is the fraction between the change of function and the change of argument. And then we take the case where x approaches a. Here our basic definition of the derivative. Congrats! So let us proceed with some basic definitions further. Firstly, let us assume the following notations. First, we start with the change of function, which is simply how much the value of function change from point A to some point x, which is drawn on the slide here. And also the same thing applies to the argument. Here is the change of the argument. We will call it delta f and delta x respectively. The thing that we're actually interested in is the linear part of this function change. It's normally called a differential or df. Basically, the differential is your childhood hopes and dreams. Because imagine that you were in your childhood at the point A, and you were assuming that you are a superlinear, the simplest function of all. And then you are suppose that you were growing like a linear function and life was the most happiest life of all. And you've actually changed as a linear function by your differential. Well, real life is not the simplest one, so the differential is not necessarily coincides with the real functions change. So, in order to understand how they are connected, we need to introduce ourselves to the concept of differentiable function. Differentiable function is basically the thing that we expect from any decent function here, where its linear approximation, linear understanding of change, the differential, is kind of the same as the function change. So, where actually mathematicians and words approximately without any other continuation is kind of a bad thing and not exactly math here. So we need to define what is approximately actually means. In our case, it means that we are infinitesimal towards the change of argument. Here, in our own notation, it is written as O from the function's argument. Well, the single variate functions, as you may remember, is the simplest case error. So here, being differentiable simply means that we are just having a derivative. In other words, differentiable functions are functions that can be closely fitted by straight lines or piecewise straight lines, which is kind of works too. Now, we are going to move to our magic transparent board and try to calculate some basic derivatives by definition. See you in the next more interesting video. Since we know the definition of the derivative at the given point, let us consider some examples of the calculation of these derivatives by the very definition. So let us start with, for example, function x squared in arbitrary point A. Right? First, let us revisit the definition of the derivative itself. The derivative at point A of our function is the limit of the relation between the change of the function at this very point and the change of the argument at this very point. If our x approaches the function we are talking about, the point A. Okay, so what we're gonna do here? We're gonna do the following. We're gonna substitute all the things we know about our function in our definition and try to find this limit. Just pretty simple, pretty straightforward. So, what we do know? Firstly, we do know that we start with the idea that we are looking for the derivative at the point A. Then we are looking at the limit at the point A. That's pretty much the same as the definition. Then we are going to substitute our function with, well, x squared, right? And then the value of the function at the point A is a squared. Once again, one of the most simple things there is. So, what we are going to do? We are going to once again use our simple school trick. Since we are looking at the difference of two squares, then you can factor the denominator as x minus a multiplied by x plus a. As a result of division both denominator and numerator by x minus a, we move from the case when we are looking at the indeterminate form where the numerator approaches 0 and the denominator approaches 0 to the case when we are looking at the limit of the pretty simple function x plus a, x approaches a approaches a, thus basically this sum approaches to a's. That's the idea you're actually familiar with from the very famous relation that the derivative of x squared is 2x's, right? That's the same that we got here. As another example, let us consider, function sine of x, once again in an arbitrary point, just to make sure that we all understand how to calculate it. So once again, let us just roll with very definition here. In order to do it, we are gonna write that we are looking at the limit at the point A of sine of x minus sine of a divided by x minus a. So the thing that we are gonna do, we are gonna use our trigonometric knowledge here and substitute the denominator by the multiplication of 2 of sine of half a difference multiplied by cosine of half a sum. That still doesn't solve the indeterminate form here, right? Because x minus a approaches 0, thus we are having sine of 0 in the denominator, thus we still having 0 divided by 0, right? So what are we gonna do? We are gonna to move our multiplication by 2 to the denominator in the following fashion. We are gonna write it as sine of half a difference multiplied by cosine of half a sum divided by x minus a divided by 2. Okay? So what we are looking at? We are looking at sine of something, an apple, divided by apple, where our apple approaches 0, right? Since x approaches a, then x minus a divided by 2 approaches 0. So we are basically looking at our second important limit, right, from our theme about the limits of single-variate functions. Thus, this relation altogether approaches 1. Or another case, we are just looking at the limit of cosine of x plus a divided by 2, cosine of half a sum, multiplied by 1, which we're gonna omit. And as a result, we get cosine of a. Once again, the famous relation here, the derivative of sine function is cosine function. Okay, so now we know how to calculate two derivatives of two basic functions. As you might know, the table of the derivative of elementary function is widely known, and normally we do not use it to compute once again with definition, we just roll with the table, right? So you should always remember basic derivatives. For example, derivative of the power, which is always power multiplied by x powered n minus 1, right? Then we need to write, for example, derivative of logarithm, which is 1 divided by x. The derivative of exponent, which is exponent itself. The derivative of exponent with different value, which is multiplied by the logarithm of this very value, right? Then we get, for example, our trigonometric derivatives. We've already established them. The derivative of cosine is minus sine. And you also should never forget about the derivatives of inverse trigonometric functions. I'm gonna, for example, roll with arctangent function, inverse tangent function, or the derivative of tangent function. Right? I'm gonna use two notations here. This is 1 divided by 1 plus x squared. The whole table of the derivative of elementary functions can be found in additional materials, and you are supposed to learn it by heart through our course. It's not a mandatory thing, but it kind of will happen whilst you are tackling all the tests you're looking at. Also, you will be given non-mandatory tests here just to drill all your knowledge about the taking of derivatives. So now we know how to find derivatives by definition. Well, it's actually not the case. Nobody finds derivatives only by definition. There is a set of arithmetic rules here, and you're not destined to do these limit calculations for all alternative for the rest of your life. So let us proceed with some basic, the most obvious rules here, which is kind of inherited from the properties of limits. Let us start with the most basic ones. It's the derivative of sum and derivative of difference. It's actually the simplest one and the most intuitive one. The derivative of sum is the sum of derivatives. Same applies for the difference case. Let us just assume some basic example here. For example, let us take the function x squared plus cosine x and assume we're trying to find a derivative here. So by our rule, we need to write the sum of two derivatives of x squared and cosine function, and then it is the one we've actually seen in our magic board video. It's 2x plus minus sine of x. And that's actually it. That's the end of the rule, and well, congrats. You now have a very decent tool to calculate derivatives. Let's move forward. And further, we are trying to think about some other pretty obvious stuff. It's multiplication by number. The multiplication by number, it's kind of a general case for the derivative of sum. Let's just assume the following. Imagine you have some function f, and you need to find the derivative of 2f. One can think of 2f as kind of derivative of a sum, f plus f, which is an easy transition. By our summation rule, it is derivative of f plus derivative of f, which is easily by arithmetic from kindergarten to derivatives of f's. That's it. A more general case assumes that we have some thing like 3 pi x power 3, and we need to find derivative of this. Well, you don't need to be frightened by 3 pi. 3 pi is just a number, or whatever it means. It's just a number. So we need to move it from the derivative and multiply it by the derivative of x power 3, which is actually results in 9 pi x squared. That's it. Congrats. We now know the next rule. So let's move further and let's consider honest multiplication function by function. It's kind of a bit complex at the very moment, but let's try it on some example. For example, let us consider function x multiplied by natural logarithm of x. So it's a product of two functions, x and logarithm x. So we need to use our funny rule. Funny rule here implies that we are getting a sum of two products here. Firstly, we need to multiply derivative of the first one, multiply it by the second function, and the second term is derivative of the second one multiplied by the first one. So all the derivatives here we've actually seen in the previous video, so we just write them down. Derivative of x equals 1, and derivative of natural logarithm is 1 divided by x, so we get in the result natural logarithm of x plus 1. Okay, it's kind of more tricky, but it's still rather easy. So let's move to the last arithmetical rule here, and it's the rule of division. So it's far more complex than all the other, but we are going to live with it quite happily. In order to understand it, we are going with some most basic example of all. You probably remember that in the table of derivatives we have function such as 1 divided by x. Or, in other words, it's x powered minus 1. Since it's a power function, there is a common rule for it, and you need to multiply the power by x powered with the same power minus 1. Simply writing it is minus 1 divided by x squared. Okay, that's how it's done by our table. But how it's done by our division rule? It's actually division of two functions, 1 and x. So let us consider this case also. Of course, results are expected to coincide, but who knows, maybe I'm lying. So by our rule we need to, well, let's start actually with denominator. It's quite easy. You need to square the denominator of the original fraction. And for the denominator, we are going to go with this rather complex rule. First of all, we need to write the derivative of the numerator multiplied by the denominator minus the derivative of the denominator multiplied by numerator. And the derivative of 1 actually is 0, so the first term is absent. And the derivative of the x equals 1, so we are getting our familiar minus 1 divided by x squared. Well, they coincided, so no problem here, and our rule is actually working. Now we are actually in capacity of quite a decent amount of basic rules to go with derivative calculations. But in order to do any derivative, we need to study a bit more, which is our next video. So, let's move further. We need to consider almighty chain rule in order to calculate derivatives here. And firstly, we need to introduce ourselves to the concept of composite functions or a composition of two functions. Well, assume that, as you do remember, functions are always considered as a relation between two sets, arguments and values. So imagine that we have three sets now, x, y, and z. And our function, let's start with surprisingly function g, actually maps x to y. And our function f maps y to z. So the result of it, if we take some argument from the function x, we are kind of having a conveyor situation here, conveyor belt. Firstly, we are moved from x to y by function g, and then the result of function g is moved from y to z by function f. And that's what the composition of two functions is, its consequent application of two functions to one initial argument.
The idea here basically is that we need to assess how much the value in the set of z changes if we slightly change the value of the argument in the set of x. And the idea here is that we do not know the structure of the function from x to z all over, which is our composition here. We do know how it changes between our blue arrows and not our red one. So we need to rewrite our derivatives in terms of derivative of function f and derivative of function g. So let's proceed with it. Firstly, here is the rule. The rule basically states quite obvious thing. Assume that we have, for example, two pipes with filters. I'll try to draw some basic thing. It's one thing, and that's the other thing. First is called G, and second called F. And inflow goes to G, and it goes out from the F. So how G works? G works as a filter. So assume that, for example, if the water goes to the G pipe, the outtake, which is somewhere near here, is actually multiplied by 0.9. 10% of the all inflow are lost, is filtered out. And the outtake from the f function is, for example, 0.8 of the intake of the f function. So we are losing 20% of what actually comes towards the beginning of the f pipe. So as a result, what we are going to lose? Well, it's quite obvious. We need to multiply our outtake, our filtration coefficient, if you may say, of the pipe G and of the pipe F. But the same thing is actually displayed by the rule of the derivative of composition. In order to understand how much function changes, the composite function changes by the change of its initial arguments, we need to understand how much changes inside function, and then how much changes our outer function towards the change of our inside function. Basically, the idea here is that you can't put derivative inside your brackets. The only thing that you can do is understand how one function changes over the argument in its brackets. For function f, the argument here is called function g. So let us consider some basic example, and life will be much more simple and easier. So first of all, let's start with painfully famous and painfully important function, exponent of minus x squared. You will use it for all of your life as a Gaussian distribution, and it's kind of must-have for every decent human being. So it's basically a composition of two functions, exponent of x and minus x squared. So let us consider our rule. Our rule tells us following. First of all, we need to learn how to draw here. Second of all, we need to decide what is inner function, what is outer function here. The rule, the intuitive rule here is kind of simple one. The outer function is the one which you calculate last. So assume that they are trying to find the value of this function at some point. For example, 1. 1 is the awesome point. So in order to do it, you first start with x squared, right? You are considering x squared at point 1. This is your first function. Then you are moving forward to minus x squared. And then you substitute your resulting value and put it inside the exponent. So the last function that we've talked about is exponent. So it's outer function. And the inner function is minus x squared.
So let us write it. Let us start with outer function. Outer function, as we said, is exponent. The derivative of exponent, as we know, it's the same function, so it's exponent of minus x squared. Remember, we are finding a derivative towards inner functions. Our argument is called inner function, minus x squared. It's kind of our artificial x. Let's write it like this. Okay, and then we proceed with the derivative of minus x squared, which is kind of familiar. It's minus 2x, so the answer here is minus 2 exponent of minus x squared multiplied by x. That's kind of tricky. You need to get in touch with it. You need practice. And actually, all the examples and tests that we are going to give you in this week is the thing which is going to help you here. So, as a last point of our search for calculating derivatives, we are going to study some basic trick, which is logarithmic derivative, which is our following video. It's kind of not necessary, but it's nice. Hi. Welcome to the second part of our week. In this part we are going to speak more about linear approximations and tangent lines, actually using our knowledge about the derivatives and what it stands for. So, let us start with remembering basic things which we've learned in the previous video in this week. First of all, we've learned the definition of differentiable functions. It stands for functions which can be easily approximated and easily fitted sufficiently with linear functions, and the change of the functions are close to its differential. So let us extrapolate and rewrite this statement further. First of all, we need to rewrite by its definition functions change and differential. So we get this nice trick. And also let's move our minus f at a term to the right part, and so f at a becomes the part of the right part. It's kind of nice. So what do we have here? We have here an equation for our value of our functions at arbitrary point f, which is close to our given point a. And it's kind of nice. Let's take a look, because that's our value, that's what we are aiming at. And here we have some constant thing, then we have constant value multiplied by linear function, and then we have some kind of arrow. So the first part, first two terms of the right side of this equation is actually stands for linear function. What linear function? Well, you can easily guess. What linear function is connected with the derivative and differentiality? Well, it's tangent line. So we now have the equation of a tangent line, which is kind of awesome here. And, well, congrats. So it's quite easy, but you need to understand, well, basically two rules to compute this line. You need two things. You need to understand the value of derivative at the given point and the value of function itself. And if you substitute x with our given point a, you just got the second term to disappear, it's equals to 0, and you just left with the first term, which is f at t, which stands for our tangent line intersects our curve, our graph of our function f at point a, which is actually what we're aiming for. Well, that's our common figure for this, and that's our green line which we are talking about. So let us consider some example. Well, we are going to go with our awesome example x powered x, and so let us just find a derivative in the point 1 divided by exponent foundation e. So what are we going to do here? We are going to compute two things that we are in need of to write tangent line equation here. First of all, we need to find a derivative in the given point. So we need to find f, the derivative of f, at the point e powered minus 1. So let us remember that it stands for x powered x multiplied by logarithm of x plus 1. And I'm going to use the following notation. You are familiar with it, and we are going to use it further in all our lectures. So we are going to draw this straight tall line and write here that you need to substitute x with 1 divided by e. So let's just write this thing down. It's going to be e powered minus 1 in the power of e powered minus 1. Well, we are going to simplify it, obviously, but let's just proceed with other stuff. Then we need to write a logarithm of e powered minus 1 plus 1. And, well, you can easily understand why I'm not going to simplify the first term of the product, because the second term is actually equals to 0, because natural logarithm of e powered minus 1 is actually minus 1 by definition. So the second term is 0, and all of it equals to 0. So we've computed the derivative in our point, and we just need to write the answer here. Let us write it in some other corner. So y equals to, well, actually 0 multiplied by x minus e powered minus 1 plus the value of the function in this point, which is this term. We are going to multiply our powers here and write it like this. So in other words, y equals to e powered minus 1 divided by e, which is kind of tricky, but it actually means that we have a horizontal tangent line at this point, which kind of means something, and we're going to learn about it more in the last week and in the last part of this week actually too. Now we actually know more about tangent lines, and let us proceed with the understanding of linear approximations of functions. First of all, let us just look at the very same equation we've used earlier. And what does it say? It basically says that in the close neighborhood of the given point A, this, or well, this one, you can substitute your function with its linear approximation. In other words, you can move with differential as the change of function in the given point, and hope that this error here, which is infinitesimal towards function change, doesn't actually cost very much. How fair it is? Well, it's kind of tricky, and in order to understand more of it, you need to consider Taylor series and its accuracy. But for our purposes, we're just going to understand basic approximations which can be derived from these first order approximations here. So let us consider, well, just some basic example. For example, let us compute sine of 29 degrees. Okay, First of all, we need to define three basic things here. We need to define function we are working at, because we're actually looking at some number. We need to write something about f at x. So we are going to write it. So, well, it's kind of obvious here. What is the function which is referred in this example? It's sine of x. Well, nobody's actually surprised here. But what we are going to do, we are going to define 2 points. Point A, which is a good point, a point which is most fittest. In another way, we are comfortable to compute derivative at this point and the value of function itself at this point. So what is this good convenient point near the value, near the argument of the function that we are going to compute here? Well, actually, let us just skip for a second and write the bad point here, because bad point is kind of easy. Bad point is a point that we are looking for, it's 29 degrees. But the good point, well, most of us that remember school course of trigonometry can easily write this thing down. It's 30 degrees, and cosine and tan function of 30 degrees are quite famous, and well, we are going to go with it. So now we are having here our function, our good and our bad point. We can calculate easily the derivative of function f and then substitute with a good point. We can easily calculate the change of argument and, well, get the result here. But we need to be cautious here, because it's kind of tricky. First of all, there is some strange thing here, which is our degrees. You need to understand some basic thing. If we just move forward without degrees, our change of arguments will be measured in degrees. I know this sounds like a physical explanation here, but it's kind of useful to understand. If we move forward with degrees, our answer will be measured in degrees, which is kind of not the case. Sine of something is not an angular thing. It's just a metric thing. It actually is not measured in anything. It's measured in units, because if you remember from Pythagoras' theorem, sinus is the fraction between hypotenuse and the segment of the triangle. So we need to get rid of degrees and move to some other angular measurements, which is measured in units, not in some physical units here. So it is actually radians, and if you do not remember what radian is, I've got an easy rule for you. The rule basically works like this. 180 degrees is pi radians. Half a circle is pi. It's quite easy. Well, in real life you kind of expecting that pi is a circle, but, well, nothing actually works good with these odd jokes. So, another way, if we need to go further with our degrees, we need to use transition to radians and not degrees here. So in other words, 30 degrees is 6 parts of a semicircle, and in our case it is pi divided by 6. Well, and, well, 29 degrees, it's kind of ugly, but we actually do know that it is 30 degrees minus 1 degree, and 1 degree is pi divided by 180, so we are going to go with it, and it's quite nice and easy. So, in other words, x minus a, the change of function here, is minus pi divided by 180, which is nice. So, the last thing to do is to write down our derivative at the point A. So we need to find the derivative of sine function, which is, I hope you remember, cosine function, and we need to substitute x with the good point, which is pi divided by 6, and as a result we get, okay, this is kind of tricky because nobody actually remembers it, but it's square root out of 3 divided by 2. So let us just write the thing down. So what is sine of 29 degrees? It is sine of 30 degrees, which is 1/2, plus the derivative, which is square root out of 3 divided by 2, multiplied by the argument's change, which is minus pi divided by 180. And I'm warning you, function change can be negative, and you should not lose this minus. It's crucial here. And it's your first way to just mess with it completely is to forget that the change is actually can be negative or positive and, well, actually 0, but that's not our case. So what do we get here? Well, first of all, you need to understand that it's kind of question of, well, not very good accuracy, because, well, what is sinus of 29 degrees? It's 1/2 plus something, and this something is actually not so great, because square root out of 3 divided by 2 is less than 1, and minus pi divided by 180 is close to 1 divided by 60 or something like that. And this is somehow close to, well, 1/2 minus 1 divided by 60, which is, well, kind of loose approximation. And we actually just said that the value of sinus of 29 degrees is close to sinus of 30 degrees, which kind of not a great discovery here, but it gives us a sense how close, and we can go with some value here. So, well, it still works. And as a last thing, I need to point out that it's actually it. That's the end. We can now calculate approximate values in many bad points using good points, and, well, it's mathematically absolutely correct, which is a nice understanding and a nice trick. As the last part of our linear approximation theme, we are going to go with one of the most famous and most important theorems in calculus. It's mean value theorem. Usually you do not understand that it's so important because it's kind of vague how to use it in real life. But the result is still impressive, and actually is the groundbreaking thing for the main calculus theorem, which we are going to study further in the 5th week, and all the other facts. So let's start with a puzzle. Puzzle here is going to be as follows. Consider some function f and a segment from a to b, not an infinitesimal change of argument from a to some point x, a real segment. And the idea here is as follows. Assume we have a chord between ends of the graph of this segment. Can you always find a tangent line that at some point of a segment parallel with this chord? Well, let us draw some basic illustration for this and actually consider this theorem all alone. So this is our function f, usually drawn in blue, and here are a chord drawn in dotted dark red color. And an impressive fact is that, okay, obviously the orange tangent line isn't the answer here, but the green is. And the theorem actually stands that there is always some point on this segment with the parallel tangent line. Well, why it is so important, you ask, and it's kind of an obvious question here. But let us move to the formulas for repeat to understand it, because it's actually quite impressive if you just write it down. And the thing here is that the Steve theorem stands that there is always a point C at this segment with a parallel chord. What is a parallelity in terms of straight lines? It is the coinciding of slopes. For the tangent line, the slope is a derivative at this point, which is written in our left part, the derivative of f at the point C. And at the right part, we are writing down the slope of the chord, which is, as you may well understand, the fraction of functions change between the ends of the chord towards the arguments change at the ends of the chord. Or if you rewrite it in a singular form, it's kind of impressive, because what is written down? It's written down an exact equation. It's not the case of our differentiability definition, which stands for we are somehow linear with an arrow which is infinitesimal. Here we have another thing, which is an exact equation. The change of function is exactly proportional to the change of argument with a proportional coefficient equals to a derivative at some point without any errors. The trick here is that this point C, can be very tricky and misguiding, because we are not in power of finding it analytically at any case. But it's kind of nice to understand, because if you know that your function has bound its derivative, for example, it does not go higher than 5 and lower than 3, you know that your function change on every possible segment is proportional to arguments change with a proportional coefficient bounded by two very distant numbers, and you can understand how much your function changes on this segment, and more importantly, the order of change, which is nice, and it is a groundbreaking thing, and it is main calculus theorem, which stands for integrational theorem, and all the other courses. So let us just take a moment to look at this beautiful picture, and I will see you in the next videos, and we will take about higher order derivatives and all the more complex stuff, which is also funny. So, as we proceed further with our understanding of derivative and speed of change, sometimes we need to assume not only the speed of change of a function, but the change of speed of derivative itself. And you don't really realize how common this concept is in real life. I'm gonna go with two basic examples. First of all, it's example of inflation rates. Literally, the speed of inflation, the speed of change of prices change. And, well, you always hear something like that some politician promises that rates would change slower. He actually speaks about the speed of change of the derivative. Another example, it's quite modern and quite important for us. It's example of climate change. And for example, let's take ocean level. There is a common understanding that ocean level on average rises. I'm not speaking about what is an average here and how it is calculated, because it's kind of tricky and it's statistical, and as Mark Twain said, that there is three types of lies. Lies, big lies, and statistics, and well, we're not going to dive into that, but what we're going to speak about, we're going to speak about what's actually an understanding of global climate change here. And the global climate change here, global warming, here is represented as follows. We do understand that ocean level rises and falls, well, quite a lot throughout the human history and all the planet history. But the question here is how fast, characteristically, and what is the trend it changes? Well, because if it changes linearly, for example, growing linearly. It's not a big deal here, it's kind of common thing. But if it is, for example, quadratic, faster than linear, extremely faster than linear, then it is quite a big difference and we need to do something with it. Well, spoiler alert, we need to do something with it. And well, the mathematical definition of global warming is the common class of a derivative of an ocean level. Is the speed of change of ocean level linear or more? Or faster than linear. So all these things are basically tackling the issue of this change of the derivative of a derivative, the second derivative, or the second order derivative. First of all, let us do some formal definition here. We are considering our real valued function f, and we assume that it's differentiable, and we are having some given point a. And so the second derivative is basically the derivative of a derivative, as is a limit where x approaches our given point a of a fraction of change of derivative towards stage of argument. Well, that's something which you are actually not glad to see because it's a definition and we kind of hate all the complex definitions here, but well, it works. Well, in other words, as I said earlier, it's just a derivative of the derivative, and it's nice and easy to calculate here. So let us assume some example. Well, first of all, let's start with a simple function like x squared and consider some understanding of a second derivative here. Well, the first derivative here is, that's right, first derivative is 2x. You all remember that. Yeah, it's nice. And then we all need to find another derivative here, and well, actually, I'm not gonna ask you about it, it's kind of obvious here. It equals just 2, and everybody knows it. So, let us consider more complex examples here as exponent and sinus function of x. Well, firstly, with exponent, that's quite easy, because the derivative of exponent is exponent. The second derivative is pretty much the same thing. You can do anything with an exponent by taking a derivative. And as for sine function, it's a bit tricky, but still impressively the same. As is, the first derivative of sine function is cosine function. Thus, the second derivative of sine function is the derivative of cosine function, which is minus sine function. So let us summarize for a minute here. As for exponent, the second derivative of it is the same function, it holds still. But as for the sine function, the second derivative is minus sine function, minus the function itself. It's kind of implying that sine function and exponent is connected somehow. And if you study further complex analysis or just basic complex number theorems, you will understand that this connection is basically Euler's rule for complex numbers and can be easily used by introducing imaginary part and imaginary numbers into this equation. So let us move further toward the motivation of all the work we are doing here with second derivative. So now we are going to understand the crucial value of concept of the second derivative here by introducing another extremely important thing is convexity. Convexity is something that you will be living with throughout your machine learning course and optimizational recursions if you choose it in your further track. So, firstly, what we are going to understand, it's kind of intuitively easy to get property here, and we are going to roll with it in the following manner. Firstly, let us just try to understand it in basic examples. So we need to proceed further with a basic definition here, and it's kind of an intuitive one, because consider graphs of various functions, for example, x squared plus minus 13 and, well, some exponent here. And we are looking at segments, chords between 2 points that lies on the graph, and, well, here are some of them. Well, this is the end of this segment, this is the end of other segment, and, well, other drawn on the graph. And here is a common property. This segment lies above the curve, lies above the graph, which is the definition of the convexity. The function is called convex, is these chords, ends of which lies on the graph, lies strictly above the curve. Well, one should also think about a non-strict case, then the straight line is also can be called convex. It's kind of tricky because one should also expect that we can vice versa reverse our definition here, and in case that this segment lies below the graph, for example, think of minus x squared or something like this, the function is called concave. It looks something like this and something like this, which is nice. So if we think about non-strict cases, it's kind of tricky because the straight line, something like this, satisfies non-strict definitions for convex and concave cases. So maybe it's not a good idea to have these definitions as a default one. So we are going to run with our strict definitions here. So that's what the convexity is. But the question is, why do we need to study it? And the question and the motivation here is quite basic. We need to study it because it's nice to have convex functions when you need to optimize a function, for example, an arrow function, the cost function, and whatsoever. So let us proceed with some basic optimization terms. So, welcome to the Optimization 101. We need to understand what we are looking for and how we can characterize it. So, the first start is the understanding of what is called extremal points or extremum. First of all, you need to understand that it's a Latin word, so the plural is extrema, and we are going to run with it. So, point, for example, A, is called a local extremum of function f. It is, if it is the greatest, or well, the lowest actually, a value in some neighborhood of the given point. You should carefully understand that this definition actually works if there is any neighborhood that satisfies our demand for the greatest or the lowest value. So you don't need to push for every or somehow not bigger or less than some value. Just any neighborhood would suffice. So let's us just have a look at the most common example. I've taken just a cubic polynomial here to represent some basic cases. So what we do have here, three dots A, B, C. And let us understand, firstly, point A is a local extrema because it is the greatest value, for example, in this neighborhood. Point B is a local extremum because it is the lowest value in this neighborhood. Point A is called local maximum and point B is called local minimum. And point C is neither a minimum or maximum and neither extremum, because whatever we are calling the closest neighborhood here, whatever we are going to draw this square frame, on the left side from the point C we are going to get greater values than the point C, and at the right side we are going to get low values than the point C. So it's not an extremum at all. And I'm going to spend quite a bit on this graph because you need to see one key difference here. We are not speaking about global extrema, the greatest values and lowest values of all. And the thing here is that there are times which you can imagine that local maximum and local minimum does not necessarily mean that the point that is called maximum is necessarily greater than point that's called minimum. Since all the points are called local, the relation between each other, it's not actually defined. Just imagine some kind of this graph, just like extremely long stairs like curve. Well, let us just mark some maximus and minimus here. So this point is actually, let me just take a red color. That's a maximum, that's a minimum, that's a maximum, that's a minimum. Oh, okay, that's a trouble. We have maximum and we have minimum, and minimum is actually greater than maximum. And that's the case, that's what we're talking about. All the things are local. We cannot derive any conclusions just by the term maximum and minimum here. That's actually a sad one, but well, it's just the case. So, what we are going to do here is we are going to understand how it is connected with the derivatives. And to understand how it is connected to the derivatives, we are going to just relate to our mean value theorem. As you remember, mean value theorem told us that the change of a function is proportional to the derivative and the change of the argument. So, in case, for example, our derivative is positive for all the segment or negative for all the segment, a function changes monotonically on this segment. If derivative is positive, then function monotonically grows. And if derivative is negative, then function is monotonically falls. So, as a result, we need to understand the connection between extremum and the derivative. And in order to do so, we need to remember our mean value theorem, because it stands for the change of function is proportional to the change of argument and its derivative. As you assume that derivative is positive or negative on all the segment, then you necessarily get a positive or negative change of function. In other words, the sign of the derivative, the positive or negative, stands for the monotonicity of the function. And since monotonicity of the function is crucial for us, because let us assume, for example, for the point A, to the left side we are going, to the right side we are falling, in which we are the function we are considering. Derivative at the point A cannot be either positive or negative, thus it necessarily should equal to 0. And that's kind of a necessity case for extremums. The rule here works as follows. If function have an extremum at the given point and is differentiable at the given point, then the derivative here equals to 0. So, okay, that's understandable, but how come it is connected with the convexity and the second derivative here? And in order to understand this, we need to move further and understand how the derivative is connected with convexity. So, let me hit you with a theorem right straight from the beginning of the video. In case of convex functions, global extremums are local extremums, and local extremums are global extremums. They coincide. And why does it happen? It's actually quite nice to understand and it's easy and intuitive. Just assume that you have some convex function, for example x squared, but no pressure here, and you just have drawn several tangent lines at several points, like I did on this graph. What do you see? The question here is what is the slope of these curves and how it changes throughout going from the left to the right. And as you see, this is the lowest negative value, this is a bit higher negative value, this is a positive value, this is a high positive value. So the idea here is that the slope actually rises from the left part to the right part. From the left to the right, our derivative actually increases from negative to positive values. As a function that starts from the negative values and goes to the positive values at the very end, at some point it necessarily should cross 0, right? And if it crosses 0, then there is an extremum. So, for example, that's our connection with basic extremum theorems. And let us just have a look at what we've accomplished here. First of all, we do understand how the derivative actually connected with convexity or concavity here. If the derivative of function changes monotonically rises, then the second derivative is positive. Then functions look like x squared. Well, another rule here, if the second derivative is positive is good, then there is a nice smile here and you are happy, and a happy smile looks like concave function. And if the derivative is negative, thus the first derivative is falling for the segment, then the function is concave. Well, in other words, well, negative derivative is bad sign, and bad smile looks like this, and well, since the bad smile looks like this, that's concave function. And also we understand the last thing, and the last thing that since we are monotonically changing, as we just decided, and we have a 0, since we are crossing from positive to negative or from negative to positive case, then we have only one point where our derivative equals to 0, thus we have only one extremum. And that's actually quite the case for our theorem. We've just proved it. You just haven't noticed. We just proved the case that in case we have convex or concave functions, our global extremum actually is local extremum and vice versa, and there is only one of them. And that's fun. Hi. Welcome to the fourth week of the calculus course. Recently, we've covered the concept of differentiability and the derivative of single-variate function. Now it's time to move on to the multivariate case. It is essential, since we know quite a lot of concepts for single-variate functions, such as seconds, tangent lines, linear approximations, that we need to generalize this concept towards the multivariate functions. But it's kind of tricky, because introducing another degree of freedom into the system can cause us some conceptual problems here. Thus, we need to understand what concept here is easily differentializable. And this concept we are going to call the dinosaur law, because since we've used our approximation by straight lines as a definition of differentiability for single-variate functions, thus we are going to use the same definition but the approximation of some hyperlinear concept such as hyperplane for multivariate case. So in the rest of our week we are going just to gradually, first of all, define what is a tangent plane or hyperplane is for multivariate functions, then understand what is the chain rule here, and then we proceed with the derivatives of higher order and the concept of convexity in multivariate case. See you in the following video. So, first of all, we need to thoroughly define what we're talking about. Since we're going to fit our curves, our surfaces with linear objects, let us, as always, assume the two-variable case. Firstly, what we've known for a single-variable case, that we need to find the best linear approximation, which is a tangent line. And then we are going to generalize it towards a tangent plane or tangent hyperplane for the case of functions of more than two variables. So what is a tangent plane? Well, it's kind of essential that since we define the tangent line as a limit of all seconds, then we need to define the tangent plane in the same fashion. We need to define second plane, which is the plane just which goes through our defined given chosen point, and then actually is not the best approximation, and we are seeking for the fittest one, quoting Charles Darwin here. So, since it's quite easy to define this in this way, we can proceed as follows. But, as you can all understand, that's not a constructive way to define our tangent plane, and so we need to elaborate on this further. So, let us roll for a bit with our non-constructive definition. Maybe we can conclude something about our tangent line from it and just it. So, how do we start it? Firstly, let's start with that we have some function f towards x and y and some given chosen point. Assume that that's point a, b. And there is a tangent plane at this point. We do not know how it was defined here, what it is, how to write an equation, but let's just assume that the function does have this tangent plane at this point. I'm gonna highlight this point for all of you. So, what we're gonna do, we're gonna consider a section of this plane and the surface with one specific plane here. Plane is y equal to b. What does it mean? Basically, we are looking at a screen that have been placed on our three-dimensional graph at the point AB parallel to the y-axis. So, what we got as a result? We got two things. Firstly, we've got intersection of our screen with plane, tangent plane, and our surface. As a result of intersection with our surface, we get the function, the curve f towards x and a fixed constant b here. And two planes, tangent plane and our screen, intersects by, as you all know, a straight line. So, what do we get as a result? We get a best approximational plane, tangent plane, which approximates all the surface and our curve f towards x and b in particular, and thus the straight line into the intersection approximates our curve f towards x and b perfectly. So it's tangent line, right? So if it is a tangent line, then we can directly write its slope, which was previously called a derivative. Now we are going to call it partial derivative, so we implying that there is other variables for our function, but we fixed all the other variables except our variable x, and thus we defined its slope. It's change towards the change of only one variable x at this given point. Also, I'm going to stress this out that there is two different notations for partial derivative in operator form with a nice partial sign here, and as usual notation with lower index x here in order to state the variable towards which the partial derivative was calculated. So that's the definition of our partial derivatives, and let us see how it works out on some examples. So now we got our a bit complicated definition here. Let us see what it actually means for our some given functions. For example, let us revisit the definition once again, and I'm going to stress something out for you. Firstly, we all need to understand that basically we can roll in two possible manners here. We can either substitute or fix all the variables except the variable of differentiation. For example, we need to substitute y with b and then find the derivative by the definition or any other technique. And here comes the difference. One can differentiate our function at every point and then substitute our variable x with the point we're actually interested in, or just find a derivative at this very point. It's not a big difference, or everything will be true. So let us see what it actually means. For example, let us take quite simple actually function here, square root from absolute value of x product y, and assume that we're in need of finding partial derivatives at 0 point. So what we're gonna do? We are gonna consider a function which is a restriction of ours for y equals to 0. So as a result, we get function f towards x and 0, which is square root from absolute value x multiplied by 0, which is simply 0 for all possible x's, right? So the derivative of 0, it's pretty obvious that it is 0, and as a result, it is 0 if we substitute x with 0. The same thing applies, obviously, for the derivative partial derivative towards y, so we actually find both partial derivative at the very given point, right? That was easy. So maybe assume that we need to find a derivative in some arbitrary point, right? In order to do so, first of all, let us look at this nice pretty surface here, and that's kind of what we expected, right? Because we've got that our partial derivatives are equal to 0, so we get horizontal tangent lines for our 0, 0 point. So, as for arbitrary point, well, let us assume some other more complicated but actually more nice function here, more smooth function here, x squared plus y squared multiplied by sine of product x and y. And we're going to calculate our derivative in, well, pretty much any point. And here is what I'm going to do. I'm going to just assume that we are going to substitute our, for example, y with the b just on the fly. So what we're going to do, we're going to write our function that's x squared plus b squared multiplied by sine of bx, and right here we're going to just find the derivative by x. So what we're looking at the derivative of the product, and thus we're gonna roll as usual. We need to calculate the derivative of the first one, which is x times 2 and multiplied by the second, and then add vice versa. The first one, the first function, x squared plus b squared multiplied by the derivative of sine of bx, which is essentially a composition of two functions, sine with cosine as a derivative, and bx, which is quite easy. The derivative of it equals to b. So we find our partial derivative. The only thing we have to do is substitute our x with point A, and then here was our answer. Sometimes people usually omit the step of substituting y with b and x with y, because, well, obviously we are talking about the values of this partial derivative at any point, well, where a and b can be arbitrarily anything from the real plane. So we just can skip our substitution with a and b and just roll with our derivative in terms of x and y. That's always true, but I'm just stressing you out that you always think about fixating your other variables in the first place. So now we know how to calculate our partial derivatives with substitution, and that was quite easy. So now we know what is a partial derivative. So let us move on towards the actual equation of tangent line. So what we do know now? We do know now two straight lines, tangent lines in, well, two cross sections with two screens, x equal to a and y equal to b, which are definitely into our tangent plane, right? So is it enough to actually write an equation of this plane? Well, it turns out that it is. Firstly, we need to just revisit some basic things about the equations of the plane. And we start with a scalar equation of a plane, which is as following. It is a scalar product, or just the result of multiplication and summation of two basic things. So assume that we are trying to characterize arbitrary point of our plane x, y, z. And we are going to do so by two things. One given point of our plane, for example, x0, y0, and z0, and a vector which is orthogonal for all our plane. In other words, it is orthogonal for any vector that lies in the plane, actually. So what we're gonna say is that the scalar equation is basically the idea that these two vectors are orthogonal, or in other manner, we're going to multiply our coordinate of the orthogonal vector and the vector which is definitely lying in the plane, which is vector between point x, y, z, our arbitrary point, and point x0, y0, z0. That's our equation of a plane. It's not actually the only thing that we can, how we can define our plane, but it's quite convenient, and it's usually used in many other cases. So another thing I'm going to remind you is the concept of scalar product, which is a mapping from two vectors into real numbers, and it works, well, pretty much as we stated above. It's just a summation of multiplied coordinates of two vectors. It's pretty much what we've done in our scalar equation thing, and as you all probably do know, but let us reiterate, is a scalar product has its geometrical meaning, which is basically a product of the length of two vectors multiplied by the cosine of an angle between them. You also should consider that in the dimensional cases, in multidimensional cases, in spaces of 3, 4, and other dimensions, that's basically a definition of an angle, so it's not quite an easy way to roll with a scalar product here. It's extremely complicated, actually. But it produces some other really thing here, because what we're gonna say, looking at our multiplication by the cosine function, is that the orthogonal case is actually characterized by the value of our scalar product. If two vectors are orthogonal, which means that they have an angle of half pi, so cosine of half pi is 0, so multiplication by the cosine function results into 0 as a scalar product result. So basically that's how one can define that two vectors are orthogonal. So how we're gonna use it? We're going to use it in the following manner. First of all, we know the point that definitely belongs to our tangent plane. It is the point AB, f from AB. That's what we're expecting. That's the point of our approximation. So we need to find the orthogonal vector to all our tangent plane here. But what we do know? We do know two vectors which are directional for our tangent lines, which we mentioned whilst we were defining our partial derivatives, right? They are directional for our tangent lines. Another way, what we do know here? We do know that one of the variables during the calculation of partial derivatives were fixed. For example, whilst we were defining the partial derivatives towards x, y were fixed. This means that the y coordinate of the directional vector of this tangent line equals to 0. The same applies for the y case and x coordinate in this case. So we have actually two vectors, 1, 0 partial derivative towards x and 0, 1 partial derivative towards y, which results into our two vectors definitely lying in our tangent plane. So, as we do know it, we need to construct another vector, the third vector, which is orthogonal to these two. And it's quite easy. Just let us revisit it. It is a vector which is partial derivative towards x, partial derivative towards y, and minus 1. You can easily see that whilst we can calculate this scalar product with the first vector here and the second vector here, we're almost definitely gonna get 0. Well, it's easy because we multiply 1 by some partial derivative and then minus 1 by the same very much partial derivative, and thus in summation we get 0. So now we can write our scalar equation of a plane, and with just an easy transformation, because it's nice to have that target variable on the left side of the equation and all the others on the right hand, we're gonna just write this down. So our equation of the tangent plane is our target variable equals the value of the function at this very point, and then partial derivatives multiplied by the change of arguments x and y respectively. So let us, for example, look at the case of previously discussed function square root from absolute value of product x and y. We've actually already stated that at the point 0, 0, both of our partial derivatives are actually equals to 0. Okay, so I'm gonna just write this down. Okay, that's fine, and so let us proceed with an actual equation. We need to write z equals 2. First of all, the value of our function at point 0, 0, when the absolute value of u0 is 0, so it was quite easy. Then we need to write our partial derivative towards x multiplied by x minus 0 plus partial derivative towards y multiplied by y minus 0. And, well, that's quite an easy one. So, the thing that we are going to call our tangent plane at this point for function square root from multiplication of x and y is a horizontal plane, the plane that coincides with 0xy plane of the three-dimensional space. Okay, that's nice. That was a fine way to define our tangent plane. So, now we know what is our tangent plane supposed to look like if it exists, but still we don't stated how should one decide whether this function can be fitted by our tangent plane or not. That's basically the concept of differentiability from our single variable case, but right now it is two-variable case or multi-variable case in general. So, we are discussing this fitable concepts here. We are going to fit our function with plane or hyperplane respectively. So, what we're going to do, we're going to just write with a very basic thing here. Our function, which is f from x and y, equals to our tangent plane as we defined in the previous video, plus some kind of error, right? This is the error that we get while we are approximating our function with a tangent plane. But what's that error? As we previously remember, in single variable case, this was little o infinitesimal towards the change of our variable. But right now we are actually looking at a case where we have two variables and we were looking at some point a, b and point x, y at the plane. So the change is actually, well, quite a lot of things, but we're going to refer to it as just a simple distance between two points in the real plane, and thus by the Pythagoras theorem it's quite easily calculatable, right? It's a square root from sum of squares of the segments which are just sides of this triangle. So, that's our definition. Our function is differentiable if it is actually can be approximated by a tangent plane, as we defined in the video before. So, let us just make this point crystal clear for you. Differentiable has a derivative. That's right, but only for single-variate functions. Okay? For multivariate functions, differentiable is much more powerful than the existence of the derivative itself. And it's crucial here, because as you can see, what actually changed? The thing that has changed is the number of degrees of freedom, the number of variables, right? There were one variable, 1 degree of freedom, and now it's 2 or more degrees of freedom. Thus, if for only x it's a good fit, for only one variable its tangent plane is quite a good approximation, it does not mean that for all the variables x and y in composite it's gonna be the best thing that we can come up with. So we need to carefully refer to this definition and do not feel comfortable just by calculating our partial derivatives as it was in our single variable case. the last thing we've covered is the definition of differentiability. And it's quite tricky, right? Because I've just said to you that your life just got sufficiently harder here, sufficiently more complicated. So let us just see what it actually means. Well, first of all, there is a quite fine line between differentiability and derivatives, and we've actually have looked at this at our square root from absolute value of x multiplied by y case. You do remember that its tangent plane, I'm going to just write pi capital here, is z equals to 0, right? So the thing we are going to say here is that it is differentiable in case our f towards xy function, our square root from absolute value, is actually can be properly approximated by just simple 0, right? And it's kind of frightening here, so let us check this thoroughly. So what we're gonna check here, we're gonna check that square root of x multiplied by y is actually little o, or infinitesimal, towards the distance between the point xy and point 0, 0, right? Xy and 0, 0 here. So by the Pythagoras theorem, it's square root from x squared plus y squared, right? Okay, so what we're gonna do to check whether or not it's true as x and y approaches 0 simultaneously. So we need to check the definition of the small o notation, which is that the relation between left part and right part is infinitesimal. So in order to do this, we need to calculate the limit where x and y both approaches 0, and we are looking at square root from x multiplied by y divided by square root from x squared plus y squared, and I'm going to just use the common square root here and write this down, and at this very point you all know the answer, because we've actually spoke about this limit whilst we were actually defining the limit of multivariate functions in the previous videos. Because if we consider just the case of x equal to y equal to some parameter t, then we clearly see that this function turns into just square root out of 1/2, because, well, in nominator it is just t squared, and in the denominator it's t squared times 2. So it approaches 1/2, well, square root of 1/2, and not 0. Thus, this relation does not hold, and we're going to write an inequality sign here. And our function square root of absolute value of x multiplied by y is not differentiable at the point 0, 0. In other words, the plane that we've actually come up with a candidate to tangent plane is not a perfect approximation here. And let us see just a picture here. It's quite expectable, right? Because we here we see at 0, 0 point some peak, right? This kind of thing. And as you all remember, in a single variate case, this peak, this sharp edge, is the first thing that, first sign that you are gonna have no just a perfect linear approximation here. So it basically holds in a multivariate case, but as you all remember, the constructing this surface picture is quite hard, so it's nice that we can do it just analytically without any extensive computer plotting help. Here is another tricky example here. Assume that we are looking at this piecewise defined function. It's defined at every point as multiplication of polynomial function and sine function, and at the very 0 point it is just a 0. Firstly, let us think about its partial derivatives. Well, in order to do so, firstly we need to substitute our function y at our function with 0, which results into x squared multiplied by sine of x powered minus 2 if x is not a 0, right? And a 0 if x is a 0. You all need to remember that if it was a piecewise definition, it's gonna be in most cases same piecewise definition, and well, life doesn't get easy at this waypoint. But it gets easier later, because as we've stated, that's the case where we're gonna need to revisit our definition of the derivative. And to do so, we need to just write our definition as a limit, right? As x approaches 0, we need to find the limit of the change of the function, which is x squared multiplied by sine of x powered minus 1, and the value of the function at the point of differentiation, which is 0 here, right? And the change of our argument, which is x minus 0, which is 0. And as a result, we get, as x approaches 0, function x, because we can just divide by x in the numerator and denominator. As a result, we get x multiplied by sine function of x powered minus 1, and it's their limits we've actually seen earlier, because the x functions is infinitesimal at the point 0, and sine function is bounded, thus we get 0 as a result. So our partial derivative here equals to 0. The same stands for the partial derivative towards y. So the function we're actually looking at has the same candidate as partial derivative and the same candidate as tangent plane here, which is z just equals to the plane 0, right? Let us reiterate this. Okay, so does it actually mean that we are going to have a nightmarish example as in the previous video again, and function is non-differentiable? Well, let's see. We all actually decided that we need, as in the previous case, to find the limit of the function minus its tangent plane, which is 0. It's quite nice. Divided by the square root of x squared plus y squared, and here is where it's become, well, quite nice, because you can just divide the denominator and numerator by the denominator, and as a result the power 1 as in x squared plus y squared turns into a square root in the numerator, but it is still infinitesimal function, and sine is still, well, nothing. It doesn't approach anything, but it is bounded. But bounded multiplied by infinitesimal is still infinitesimal, and thus we get our 0 as a result. So just let us take the fact: this function, ugly, well, not the prettiest one actually, is differentiable at our 0, 0 point, but more pretty square root is not differentiable. That's life. Sorry. Okay, so that was another example, and once again I'm just gonna stress this out, that we're gonna be extremely cautious with our definition of differentiability and our calculation of partial derivatives from now on. Okay, so now we know what is differentiability, and we've seen some examples. And it is still seems like extremely complicated thing to check and to live with, right? So the idea here is that maybe we can come up with something which can just simplify our life. For example, when you think about polynomial function of two variables, like we've come up here, x squared multiplied by y plus x powered 5 minus y multiplied by x minus 1. Okay, it's quite easy to come up with any possible polynomial function, right? Well, what do you expect? Well, this function should be differentiable at any point. There is no way it's not going to be differentiable. So we are going to find a way to somehow avoid this extremely complicated proof of differentiability for these simple cases. And here it becomes tricky, because what we're actually going to seek for is sufficient condition, because the necessity here is the existence of partial derivative, and it's quite understandable here, because we need to define our tangent line, and thus we need to define our tangent lines, thus we need our partial derivatives. But when it became sufficient, and here just follow my lead, the existence of partial derivatives becomes sufficient in case they're continuous, or in other words, their limit coincides with their value at our point of approximation, the point AB. So what are we gonna expect from them? Assume that we've, instead of calculating our partial derivatives at some given point AB, moved on and calculated our partial derivatives at every possible point. Thus, we are basically looking at another new two-variable function, for example, g towards x and y, right? And this very function can be, first of all, it should be defined at AB, and second of all, we can find a limit of this function at this very point. And if it coincides with our value of function g at point AB, thus this function is continuous. Basically, what we're talking about is that our partial derivatives as functions of two variables are decent functions in a way that it doesn't have any discontinuations, any infinity approaches, or some jumps in the neighborhood of our chosen point. This basically and obviously stands for our polynomial functions, since we can easily calculate any limit of polynomial function, and partial derivative of polynomial function is polynomial function. And for more other elementary functions, as we discussed in our previous weeks, certainly only for their domain. So from now on we can just ditch our extremely complicated definition of differentiability and use this sufficient condition, but only in case the function is elementary and the pointer is into the domain. But it's still nice. Now it's time to speak about more essential thing here. For single variable case, we've actually discussed that we are going to speak about the change of function and its speed, and thus appear the derivative, right? But what for a multivariate case? What for our two-variable function? Does it have the same meaning, and what does have the same meaning? Because from now on we do not have our single and one to rule them all derivative, and we have only partial derivative here, and partial, well, actually means not the whole thing. So, first of all, we are going to speak about some basic multidimensional geometry, which you all already familiar with by our deriving of the tangent plane equation. But it's nice to have it covered once and for all.
So, we've actually spoke about scalar product and what it is. It's just our mapping and can be computed by summation of multiplication of coordinates, right? So, there is some tricky thing here, because we need to start with an idea of what is in a vector, because we've spoke that scalar product is a mapping from a pair of vectors, right? So what is in a vector? And that's where it becomes, well, a bit complicated, because vectors are only elements of vector space. I'm gonna use notation capital V here just in order to stress that that's a vector space, right? So what is a vector space? Is a set of objects which can follow certain rules. There are basically two rules and, well, other axiomatic things which can be expected from any set with two defined operations. So what we are gonna have to have in a vector space. We are going to have two operations. The multiplication by a number, in our case by a real number, and the ability to add two vectors and get another vector as a result. So, basically what we're going to say here is that if we multiply any object in this space, in this set, with the real number, we're going to get some other, well, or maybe the same object in this space. And if we add up two objects in vector space, two vectors in vector space, then we're gonna get in the result another vector. Okay, that's fine. That's quite an understandable thing for all the vectors we've already known. But here is what's different. The idea here is that we normally think about vectors as some ordered sets of numbers, right? Real numbers, rational numbers, whatsoever. But that's only coordinates of the vector, and that's true only for the case when we've set the basis of our given vector space, right? It's what the basis is basically the set of vectors which defines the space, and it's the idea that we do not have to draw all the possible dots on the real plane when we draw some graph, right? We just draw axis. Basically, the axis is all the possible multiplications of two basic vectors multiplied by any real number. So that's what's the difference between coordinates and vector space, the vectors actually. Because vector is something, it's just a noodle in soup, a polynomial, a function, whatsoever. But a coordinate appears only after you've set some ground rule, some basis, and then you defined how to actually get all the other vectors from this basic set of vectors. It's always important to understand the difference between one and the other. For more comprehensive coverage of this topic, you can consider either our additional materials or the part of the course about the linear algebra. So, since now we know what is a vector space and vectors at all, we actually do understand all about our scalar product, right? So our scalar product definition. We have vectors, we have mapping, all the same that we've actually covered earlier, and we have our geometrical rule. Our geometrical rule results basically into two things: the criterion of being orthogonal and the definition of vector's length, which can be calculated by taking a square root of vector scalary multiplied by itself. It's quite easy to understand why, because if you consider our geometrical mean
meaning of scalar product and substitute the second vector with the first one, just assume that we have vector b equals to vector a, then the angle in between them is pretty obviously 0, 1, thus the cosine function equals to 1. Thus we actually get that the scalar product of a and a is the square root of its length. So that's our two corollary from the definition of scalar product. So now we know pretty much everything to define the very important thing of our course, the gradient of the function. So let us state it in the clearest fashion possible. There is no the derivative for the multivariate case. There is no the speed of change for the function if it has more than one variable. There are only partial derivatives, and if we stack them together as a vector, we get a gradient of a function, a vector of partial derivatives. Sometimes it is said that a vector of first derivatives or first partial derivatives. There are several notations for it. We state only the grad of f or this reverse triangle, which is Greek character nabla. And as usual, we just write it down. That's partial derivative towards x and partial derivative towards y stacked to a vector here. You need to remember one key point here. The gradient as the derivative for a single variable function as both partial derivatives are point-wise concepts, right? So basically what one should expect that the gradient here exists at every point of the real plane, and at every point it could be different. So basically now we are looking not only at real plane, we are looking at our real plane as a skin of hedgehog or something like that. We are looking at a plane with a vector at every single point of it. So let us consider some basic example. For example, let us consider just our x squared plus y squared function. We've seen it a lot while we were talking about the function of multivariate case, and let us just try to compute the gradient here. Firstly, what we need to do, we need to find both partial derivatives, right? So the derivative towards x and the derivative towards y. And it's quite easy because in those cases, one of the terms here, one of the terms either x squared or y squared doesn't depend on the other variable, thus we need to just differentiate the other term. So it results, well, everybody know it, and I'm too slow, in 2x's and 2y's as a gradient here. And what does it mean for our picture? Let us draw some basic x, y, O plane, and how does this vector look like? For example, assume that we have point 1, 1, and then we are looking at the vector 2, 2, right? Or we are looking at the points, for example, 2, 1, and then we are looking at the vector. Let us carefully compute it. If it is 2, 1, then it's 2 times 2, and 2 times 1, which is 4, 2, right? And it looks like this. Well, in other words, those are the vectors which are starts from the 0, 0 point, as it seems so. And, well, maybe consider some more complicated example here, but I'm not gonna try to draw a nice picture here. It's kind of tricky because it's much more comprehensive function. So what do we need here? We need to once again just calculate our partial derivatives and stack them into the vector, right? So towards x, it's a simple exponential function, thus we get, towards x, it's just simple polynomial function, thus we get x powered y minus 1 multiplied by the power, and towards y it's our exponential function, thus we get a logarithm of x multiplied by x powered y, and that's how our gradient looks like. It's quite easy, but it's nice to have one single concept to describe the behavior of our function for all the possible points. Now, let us move on to more famous and more important principle here, the chain rule, which is heavily used in, for example, deep learning and neural networks. In order to do so, we start with the case of actually one independent variable. So, formally, what do we have? We have a multivariate function, as usually we would consider our function f towards x and y, and where two variables are actually dependent from some other independent variable t. Let's do some nice scheme here. We have our target, right, f. Then we have x and y, which should be our variables, but they are actually dependent one. And then we had an actual variable, a parameter t here. So what we're asked about? We're asked about the derivative of new function, which is a function, let's call it g, towards t, function of f with straight out loud written dependencies x towards t and y towards t. So, how one should find the derivative of this function towards the parameter? To understand it, we're going to use chain rule, and let us start with some basic principle which we are going to borrow from the biology. And this principle called Planck's eye view. Basic idea here is, to put it formally, that we should operate only the relations with their neighbors on the graph and not just jumping from one parameter to the target variable, right? In other words, assume that you are a flower growing on the field. Thus, you actually can see only your nearest neighbors, and you do not understand that somewhere out there in 2 meters you have another flower, and it's actually connected to you. So imagine there is some wind blowing. Then the flower, which is 2 meters from you, starts moving. Okay, that's quite easy, right? But then, as a chain of events happening, the flower in 2 meters from you starts moving, then it touches his neighbors, then their neighbors, and so on, so on, so on, and then the scene actually reaches you. But you do not know that all these complicated thing happens. The only thing you know is that you've been touched by your neighbor. So that's exactly how we're gonna do it. So we are going to understand how fast the function f changes. We do not know the straightforward relation between f and t, right? But what we do know that f changes with the speed of partial derivative towards x if x changes, right? The same thing applies to y. If y changes, then f changes with the speed partial derivatives towards y. So the same thing applies for x and y respectively, right? So if x changes, then it changes with the speed x, the derivative of x towards t, and the same for y. So let us just look at top and bottom halves of this scheme, right? So t changes, then changes x. X changes, then changes f, right? Let us write the speed here. So we are going just write x, derivative of x towards t multiplied by the derivative of f towards x. So as a result we get the effect of change of t on the f, and the same thing applies for the bottom half, and those effects actually should be added up. Okay, and that's what is the derivative of new function g. Okay, that's nice, and that's basically how chain rule works here. Assume that we have an example. For example, our function is x multiplied by y squared, and an actual dependencies on our variables from t is x equals to t and y equals to t squared. So the function we are talking about is actually, let us rewrite, g towards t is t as x multiplied by t squared or t powered 5. Okay, thus its derivative towards its only variable, it's 5 t powered 4. Okay, that's what we are supposed to get, right? Let us rewrite this scene in the fashion of the chain rule. So what are we supposed to write? We're supposed to write our derivative, which is dg towards dt, equals to partial derivative towards x, which is y squared, multiplied by the derivative of x, which is 1, plus partial derivative towards y, which is 2xy, multiplied by the derivative of y, which is 2t. Okay, at the first glance, it's kind of extremely different notations here, but let us substitute in the chain rule all the variables that we actually do know. So y squared turns into t powered 4, and the second term for xy t turns into 4t multiplied by t squared multiplied by t, and well, no surprise, we've got our 5 multiplied by t powered 4, which is, well, seems like our chain rule actually works. So let us reiterate the rule itself. The derivative towards independent variable can be calculated by summing all the parts of our scheme by multiplying subsequently the changes of the function towards its dependent variable. So, since we've actually come up with the idea of the derivative for multivariate case, we should think about second partial derivatives, as we did in the single variate case, when we thought about the derivative and then thought about the speed of change, right? So, let us do another funny scheme here. So, first of all, we have our function here, right? That's our function level. Then we do differentiate it by x and y respectively, and thus we get partial derivatives of the gradient whatsoever right here, right? So that's kind of nice and expectable, and we do know it. And then comes the turn of the second partial derivatives. As always, we think about second partial derivative as a derivative of a derivative, but now we can differentiate nominate either by x or y. Thus, instead of 1 second derivative, we get, well, 1, 2, 3, 4 partial derivatives here. Well, towards x 2 times, towards x and y and x, and y 2 times. Well, the notation you actually do see here because, well, it's just tries to stress out the order and the set of differentiations that we've actually come up with here. In other words, what we do, we just differentiate the function one time and then we add another differentiation. So we compute partial derivative towards x and then we compute the derivative of its derivative towards y, right? So, and to finish it, we are going to speak maybe another notation, and it's just an operator notation. And that's kind of expectable because when we've been talking about the derivative of single-variate function, we've talked about the operator of taking the first derivative d towards dx, right? So here it's still the same. Assume that we have our first partial derivative towards x, for example. It is a procedure when we actually get as an input function f, and as a result we return our partial derivative. So just by putting f behind all the other symbols in this notation, we get f, which is an argument for this procedure, and then basically the symbol for this procedure. It's just an instruction what to do. Thus, in order to calculate the second partial derivative, we need to apply this operator several times, well, 2 times actually. Firstly, we apply operator of differentiation by x, for example, and then differentiation by y. Okay? As you may see, the order of differentiation here is kind of tricky because if you just multiply this fraction and fraction of differentiation by y and partial derivative for x, right? You get in the denominator order partial y partial x, right? But as for the notation we've discussed earlier with just simply using indexes, we've written the last differentiation, the last one, right? So it's kind of tricky, but later we are going to discuss the problem of order of differentiation itself, and it's not gonna be such a mess later on. But now let us consider some examples. Okay, first let's take a look at the function x powered y squared. Once again, I'm gonna just remind you that if we have such multi-stage power, then we're gonna move from top to the bottom, right? So something like this. Okay. So we need to firstly compute x y squared and then put x in the power of y squared. Okay. So let's start with basic. Let's start with gradient. Okay. Partial derivative towards x, partial derivative towards y. So towards x is it is just simply a polynomial function. Thus we get x powered y squared minus 1 multiplied by y squared, right? We need to write it down. Okay, and towards x, towards y, it's just an exponential function, which with a nice exponent here. So we're gonna write logarithm x multiplied by x powered y squared, and then we should remember that it is a composition of two functions, which is a in power of x and x squared, right? So we need to multiply everything by 2y's. Nice. So then we can proceed with, for example, second derivative towards x 2 times. And in order to do this, we need to differentiate the result of our first partial derivative by x. Y squared is a constant towards x, so it remains. And then we get, well, another case of polynomial function. So we need just to move the power as a multiplier behind and decrease the power by 1. So we get as a result y squared multiplied by y squared minus 1 multiplied by x powered y squared minus 2. So, okay, let us assume another one, which is derivative towards x and y. I'm gonna just write that we need to differentiate the same thing towards y. And thus we get the derivative of the multiplication, which is 2y's multiplied by x powered y squared minus 1 plus y squared multiplied by logarithm of x by the same, x powered y minus y squared minus 1 multiplied by 2y's. Awesome. Well, and well, maybe for the last one, I'm not going to compute the derivative towards y and then towards x, just because, as we will see later, they are destined to coincide here. So what is for the case of derivative towards y 2 times, we're gonna need to differentiate logarithm x multiplied by x powered y squared multiplied by 2y's towards y, which is, once again, logarithm x is a constant, then we get 2 as a constant, then we get the derivative of the product. And okay, let's just write it down, it's kind of boring. So we're not gonna waste any precious time here. Okay, that's what was the process of computing all the possible partial derivatives for our given function. That was quite, well, demanding. Okay, so see you in the next video. In single-variate case, the step from second derivative was to the derivative of higher order, second derivative, well, third and others, right? So the idea here is that we need to understand what is the differential for the multivariate function and proceed from second partial derivatives to the second differential, right? So, let us, for a while, try to generalize the concept that has existed already, right? So, what we were speaking about the differential for single-variate function. The idea was that, as you remember, the differential is your childhood hopes and dreams. It is the change of the function if it was just a linear object. In our case, we are changing from a straight line, tangent line, from a plane or hyperplane, tangent hyperplane, in the spaces of more than 3 dimensions, right? So this change was actually written down in the equation of our tangent plane. It is basically the multiplication of partial derivative toward by the change of argument, well, and the summation of all these changes. In other words, you can just easily write it down as a scalar product of the gradient at this very given point and the change vector of changes of all the variables used in the function. Okay, that's nice. We've come up with the idea of the differential just by generalizing the existing concept for single-variate functions. So, let us assume some, okay, maybe just for a while, let us assume that we have more than 2 variables, like for example 3 variables in our function, and we have some, well, interesting, nice point. I'm gonna do the point 1, 1, 1. Okay, 3 variables, easy point. Okay, so what we need to do to find the differential of function f at this very point? We need firstly to start with calculating all the partial derivatives here. Okay, let us start with the derivative towards x. Our idea was to firstly write down the function we are dealing with. We need to substitute all the variables except variable x. Thus we get x divided by 1 powered 1, well, and the derivative by x. Well, life is easy and awesome and actually kind of nice, because we are taking a derivative out of x, which is 1 at well, every point, so we don't need to bother anymore. So let us proceed with derivative towards y, and in this case it is the derivative of 1 divided by y, and it is minus 1 divided by y squared, or minus 1 if we substitute y with its value. And for the last derivative, we are gonna just write down the function. The derivative towards z is the result of differentiation of function 1 powered z, and it's quite easy because 1 powered z is simply 1 and the derivative of the constant is 0. Thus we get all the partial derivatives. So let's just write what we've got. We need to write down that differential is partial derivative of towards x multiplied by change of x dx, plus the derivative towards y multiplied by the change of y, plus the derivative towards z multiplied by the change of z. By simplifying, we get dx minus dy, and that's our differential for the f function. So let us consider the operator notation for first and second differentials respectively. The idea here is that we can actually think about non-operator definition of the second differential, but it's kind of messy and takes a lot of additional efforts to come up with. But well, here using our operator, we just can generalize it straightforwardly. So the first one, we need to once again revisit the definition of our differential of multivariate function. As you do remember, it is just the scalar product of the gradient and change of all arguments, right? So let us assume that we do have function f in both terms, right? Thus we can somehow put it behind all those terms and add a bracket here, right? So basically what we got here, we got f multiplied on the left by some rule. The instruction what to do to calculate the differential of two variable function, right? Take a derivative towards x, multiply by dx, plus take a derivative towards y and multiply by dy. So that's our operator of the differential. Here it is. It's quite nice. So now we know it. Okay, how does this help us into the defining of the second differential? That's why. That's how. What is the second differential? Well, intuitively, it is a differential of differential, right? So we need to compute the differential of partial derivative multiplied by dx, plus partial derivative multiplied by dy. It's nightmare. But let's us take a look for one time again at our operator notation. Basically, we said that applying an operator, applying a differential towards function f, is the same as multiplying it by some brackets, right? That's kind of complicated, but still just multiplying. So what is iterative 2 times application of differential operator here? Is basically multiplication by the bracket squared. Okay, it's quite nice, because what? Because our school course of basic algebra taught us that in order to compute this square of sum, we need to basically write the first term squared plus the second term squared plus 2 times one multiplied by another. Right? So that's exactly what we're gonna do here. We're gonna write the first term squared, the second term squared, and 2 times first multiplied by the second. That's awesome. That's extremely easy, but it is the definition of the second differential here. But there is a small but as always. Okay. The idea here is that whilst we were in school, when we calculated a plus b squared, we thought of this operation as our usual multiplication of real numbers. And in real numbers, if you multiply a and b, the order does not matter. The term is commutative. And as we actually spoke in the previous video, the order of differentiation, the order of applying the operator of the partial derivative here actually do matters. So we are going to use this expression for second differential only in assumption that the order doesn't matter, or for example all our partial derivatives are differentiable once again. There is a high derivative whatsoever. So that's what our second differential is about. So, since we come up with the definition of the second differential, let us consider some basic example for it. For example, let us use the function exponent of ax plus by. For the first time, let us use the final form when we actually truncated all our computations to the second partial derivatives. So we need to compute first partial derivative, second partial derivative, and write them all down in the correct form of the second differential here. Okay, so let me just briefly state what we're looking at. Partial derivative towards x is, well, quite easy. It's this exponent plus by. I'm gonna write function f instead of it for the sake of simplicity later, multiplied by the partial derivative of the power, which is simply a. Same applies for partial derivative towards y. It is this exponent multiplied by b. That's nice. So what's for the second derivatives here? As you do see, basically first partial derivatives here are the function multiplied by different constants, so it will be quite easy to differentiate it once again. Basically we have a, which is the same thing which happened earlier, right? Then we need to differentiate the function exponent of ax plus by, which is the same as the function itself, so we need to multiply it by a one more time and write the function. In the same manner, the partial derivative towards x and y is going to work. Firstly, we need to write a as inherited by the partial derivative towards x, and then we're gonna write the partial derivative towards y, which is ab multiplied by the function. Well, and as for the derivative of towards y 2 times, it is b squared on our exponent. Okay, let's write the exponent down. So our partial derivatives are found. Then we're gonna just write our second differential down. Its first partial derivative a squared f multiplied by dx squared plus 2 second partial derivative of towards xy abf multiplied by dx dy plus b squared f dy squared. Okay, if your
lucky enough, you can see that, first of all, you can just move f out of each term, and what is left is basically the square of sum, right? So just let us write this in nice fashion. We get a multiplied by dx plus b multiplied by dy squared multiplied by f, right? So it's quite easy to understand that we've started from the complete form of the second differential here, and we've ended up with our operator squared form as a result. So one can easily write, for example, the differential of nth order here. We actually need to just substitute the second, the power of 2 by the power of n, and multiply it by the function. Okay, so as you can see, we've not only computed the second differential by knowing all the derivatives, we've just managed to find all the differentials here, just writing down straight out loud the complete form of the differential, which is almost certainly nice. Okay, we discussed almost everything about the derivative, but as you do remember, for single variate case, we've also come up with the idea of convex and concave functions. And it will be nice to understand how this concept changed or not changed after transition into the multiple dimensions. So, you do understand that there is kind of tricky thing, because we've actually come up with the idea that everything that can be easily generalized should be generalized, right? So what was the convex function for us in single variate case? We drew the function's graph, then we drew a segment with an nth on its graph, and what we are expecting from the function is that its graph is definitely below this segment for all possible segments, right? So it's kind of trippy here, because you want to say that since we have a surface, we don't have a segment, we have a plane or just a part of a plane, and thus all the graph should be under this part of a plane, which is a nightmare, because understand what is a part of a plane and what was in the intersection, it's kind of nightmare. So we are gonna use a much more simple generalization here, just left it as it is. What does it mean? It basically means that if we have our surface, that we can once again plot any possible segment starting from one point of the graph of the function and in the other point of the function, and this segment is supposed to be higher than the surface underneath it, or the curve underneath it, if you will. But that basically means that we don't change the definition at all. So, well, obvious example. Consider the surface x squared plus y squared. We've seen it already more than one time, so it's quite easy to understand that this is a convex function, right? Because if you consider any pair of points here, the pair of points, for example, this and this one, and this segment almost definitely is higher than the curve underneath it. So it's kind of an alternative of our basic y equals x squared, which was our 101 example for the convexity for a single variate case. Well, alternative is, well, also quite expectable, because we have this x squared minus y squared, and it's kind of the parabola two times, because for x section we have
x squared with a positive multiplier, well, with a 1. And for the y section, we have something like this, right? We have minus y squared quadratic functions, which means that they are convex in the opposite direction, they are concave. So if you consider, for example, point 0, 0, then you can see that there is two sections, y equals to 0 and x equals to 0, with an opposite convexity towards the case of single variate functions. Thus, these functions in the whole is not either convex or concave at all. So the thing we are expected to find about the convexity is the link between the convexity and the second derivatives, right? So let us assume that we are going to find something in common between single variate case and its link between the second derivative and convexity, and multivariate case. Well, straightforward connection here is kind of devouring because, well, what you are expected to see here is the idea that second derivative of single variate functions should be positive for the function to be convex. And of course there is a concave case, right, as you all do remember, but it's kind of the same thing but without the sign, so we are not discussing it, well, it's kind of obvious. So of course we do not have the idea of the second partial derivative here, right? We do not understand what it is, what is the concept, right? As well as we do not know what is the first derivative of the whole multivariate function is. But what we can do here, assume that our second derivative is positive for all x's on, well, for example, some segment, right? Then if we multiply it by dx squared, non-negative value, the inequality holds, right? But the thing that we've actually got ourselves into the left part of the equation is the second differential of function f, for which is positive for all possible changes of the argument. So that is the concept which already exists in the case of multivariate functions, and we're going to generalize our convexity rule out of it. So assume that we're gonna say pretty much the same thing. Function is convex if the second differential is positive for all possible changes of variables. Okay, that's fine, that's nice. But we have a problem here because changes of variables are kind of a vector here, right? Changes towards x, changes towards y, dx, dy, a vector. So we need to understand how to properly find and define the case whether or not this second differential is always positive. Firstly, let us look at the second differential in its full form. Okay, let's look at it as we've been looking at school, because what we're seeing here is a quadratic function, right? Toward, for example, dx or dy, or maybe its relation whatsoever. We are looking at something which kind of resembles ax squared plus bx plus c. Okay, so and what are we expected to find here? We expected to find that this function is always positive. How can it happen? As you do remember, the graph of this function is, well, parabola, and it looks like this, or maybe like this one. And of course, what we should demand from our second differential from our quadratic function in order for it in order to be always positive. First of all, it should be with
a negative discriminant here, right? Because if it does have any roots, thus it has a positive and negative values, and thus we are not going to have our strict plus sign as in our proposed rule, right? So we need to look at the discriminant of our function. Remember, b squared minus 4ac, and then just ask it to be negative, right? No roots. And for the other part, it depends. If a parabolic function have no roots, it's either rated upwards or well, downwards, so which is basically defined by the first coefficient, which is the second derivative towards x twice, right? So what we get here? We get here the first one. We need to relay onto the discriminant of the parabolic function. In our case, it is our variable d, capital here, which means either or not this parabolic function has roots. So if this d, which is a negative discriminant in our case, is positive, then it has no roots. Thus it can be either convex or concave. And if, well, the rest of quite easy, right? If the first coefficient is positive, then it's convex, then if it's negative, it's concave. And that's all. We've, by using only our school algebra, just come up with the idea of how to define multivariate convexity. The thing is that our convexity is, and our rule, is kind of rip-off from linear algebra because it is the concept of semi-positive infinity of the form of the second differential. But you are going to learn more about it in the course of linear algebra or in our additional materials, as always. But now, to make sure that we do understand what's going on, let us consider the following example. Let us look at the function a squared plus b y squared plus c xy, and firstly compute the second differential and define under what conditions on a, b, c. I'm just going to say that a, b, c are real and are not zeros, just to simplify the case for us. So what we're gonna do first, we're gonna start with partial derivatives, which is kind of the easiest case, because towards x is 2ax plus cy, and towards y is 2by plus cx, right? And then we are gonna just write down the second partial derivatives. I think we are going even to avoid writing down our second differential here and just use our convexity or concavity rule straightforward. So the second derivative towards x is the derivative of the first partial derivative towards x. So it is 2a. The same applies for the second partial derivative towards y 2 times, which is 2b as a result. And as for the derivative towards xy, we are going to write as a c, because we need to, for example, differentiate the derivative towards x by y, which is c. Okay, so what is our negative discriminant, the d value here? We need to multiply our partial derivative towards x and towards y's, and subtract partial derivative towards x and y squared, right? So we're gonna write 4ab minus c squared. And well, as you all can understand, it's kind of related to the discriminant itself, so that's pretty much the reason why we're using it. Okay, so let us assume, for example, some cases. Okay, for example, what we need to ask to get some convexity or concavity here, we need to ask that d
is a positive value, so 4ab should be larger than c squared. Okay, so what can we expect from here? If a is positive, then we should expect that it is convex, right? If a is negative, then we should expect that it is concave. That's the result. But the question that we should finish with is the question of whether or not we actually understand why we are speaking about, for example, the first coefficient towards x and not first coefficient towards y. Well, because you can easily see that x and y are interceptable here, right? So you can just look not on the first or the second derivative towards x twice, but on the second derivative towards y twice. And this is where our D rule comes into the light, because assume that we have positive a. Thus we should understand that our function is convex. So by our rule, if a is positive, c squared is positive, thus b also should be positive, right? The same applies for the negative a. There b should be always negative. Thus, it doesn't actually matter what we are looking at, the second derivative towards x 2 times or towards y 2 times, it always should be the same sign, and our conclusion should be always the same. The last thing that we are gonna say here is that the cases where we have some zeros during our calculations are kind of tricky and need more attention is provided by this simple rule that we just proved, built, and actually fancied. So we are going to elaborate more on this whilst we are speaking about our optimization routine on the last week, I believe. And for now, we've just come up with the convexity determination idea on the fly.
Hi, welcome to the 5th week of the calculus course. Recently we've covered the concept of derivative for both single-variate and multivariate functions. And now it's time to turn over to the inverse operation for taking a derivative, integration. Well, first of all, one should always understand that if we introduce some operation, we also should consider the possibility of introducing an inverse one and what take us to actually define one. So, what is an integration? Basically, what we had previously, we had a function and we thought about the instantaneous change of its speed. But now we should think of an inverse task. We have instantaneous speed of the change of a function, and we need to consider the function itself, find the function itself. In other words, we need to continuously sum all the instantaneous changes of our function to introduce the function itself, to reconstruct function. Well, that's what integration basically is. It's a continuous summation. But that's where it gets tricky. Let us just consider some basic example here. For example, let us draw some, basic curve. For example, this sine function that we have here. So, the most basic thing for integration is, for example, defining the length of this curve. And the simplest one, if you just were in kindergarten and you were asked how long this path takes, you were thinking something like, okay, I'm going to put some dots here, this one, this one, this one, this one, and then I will draw a polyline. Well, in kindergarten you do not know what is polyline, but you know what a segment is, what a straight line is. So you draw it and then you calculate the sum length and you call it a result. Well, nowadays when you are more aged and you know much more, you can draw, for example, much
smaller segments or something like that. And as a result, you should understand that by introducing smaller and smaller segments, you will somehow be close to the actual length of the curve. But what is the natural answer here? Because ideally, you should think about infinitesimal pieces here, infinitesimal segments. So you need to summarize all these infinitesimal segments, and that's how you will get the curve. But, well, obviously, in the real life, it's not possible because you always get a finite number of these segments. But this finite number is also always a good approximation. So why do you even bother and consider continuous summation or integrals if you can always go with something like closed finite sums? Well, among the things that there are always some non-discrete variables. For example, time is essentially a non-discrete variable, right? You should always understand that in case of variables with a wide range, with multiple values in the range, the summation is always tricky because you have lots of terms in the sum, and it's kind of in need of some nicer form as a sum. But you actually can't get one unless you consider it's a continuous variable. That's basically the concept which is heavily used in probability theory and mathematical statistics, which you will study further, when you basically made a key change in transition from discrete variables, discrete random variables to continuous random variables. So that's what we are going to do. We are going to introduce ourselves to a basic toolbox for understanding continuous summation or integrals. For the following week, we are going to do it in the following manner. We're going to start with antiderivatives and, well, in other words, indefinite integrals. Then we are going to apply this concept to calculation the area under curve and substantially transfer this to the case of multivariate functions. Also, we are going to touch some numerical methods here, and you will be given a non-mandatory programming task by the end of the week. Okay, see you in the following video. So, let us consider the inverse operation to our differentiation. We will call it antiderivative and properly define it in the following video. So, let us start, well, as always, with a puzzle, the simplest one of all. Assume that we've been given with some derivative. For example, in our case, the derivative of unknown function is 3x squared plus x. So the puzzle here is to find our f from x. So, well, that's kind of simple because in our derivative what we see two terms in a sum. We do know what, that the sum of derivative is the derivative of sum and vice versa. Thus, in order to find the initial function f, we need to consider the initial function for both terms in our derivatives. So, in our case, we need to find what function after differentiation gives us 3x squared and what function after differentiation gives us x. So, for the 3x squared, it's kind of simple because it's a table example here. Do you remember? It is the case for x powered 3, right? X powered 3. And as a result of taking a derivative, we get exactly 3x squared. Okay, that was an easy one. But what for the x? Well, we do not have on our table exactly the derivative equals to x. But what do we have? We have x squared, right? And x squared is somehow close to x. It gives us 2 x's, right? So in order to avoid this additional 2 multiplier, we need to multiply all our function with some constant multiplier such as 1/2, right? So if we do 1/2 here, then by the rule of differentiation, this constant multiplier actually can be moved out of the differentiation, and thus we need to divide this 2x by 2, and then resulted in x. So our answer here, f equals x power 3 plus x squared divided by 2. Okay, that was an easy one. So we find it, right? So, is that all possible answers? Well, obviously it is not, because, well, if we have this answer, we can easily just insert some, for example, +1, or +100, or +100 pi, or +100 pi powered e. Whatever you want. It's a constant. After differentiation, it will turn into +0, nothing. So the full answer here, or the fuller answer here, is actually our answer plus all possible vertical shifts, plus any possible constant. Here, the proper way to describe this function is to actually put something about what possible constants here should be concerned, and in our case it's just all possible real numbers. Okay, so what we actually find here, let's turn to more formal definitions. And as for the formal definitions, we should understand that our example of function f is called antiderivative. It's one candidate for the answer to our extremely simple puzzle. It's just any function which derivative coincides with ours. But as for the full set of possible answers here, it is called indefinite integral, or just, well, result of a definite integration. And the trick is just simple here. If you knew some antiderivative, you actually knew the definite integral, and now you can just state that all possible antiderivatives is our one found plus any possible constant, well, exactly like we did previously. So that basically states our task here. We're given with derivative, and we found all possible answers, all possible functions which derivative coincides with ours. That's how one should define indefinite integral. So, we need to consider basic rules about basic calculations of antiderivative. And in order to do so, we actually take a look at our table of derivatives and then move towards the definite integrals by reversing this table. First of all, just let's consider our derivative of the constant, right? Derivative of constant, well, is actually quite known as a zero, and thus an integral of a zero is any possible constant right here. That was the easiest one. It's always nice to have the easiest one. So, as for the others, the derivative of x equals 1, thus the derivative of 1 is x plus any possible constant, and, well, you actually should expect something like this. Well, so let's move over to the integral of the power function. And that's a tricky one, because let us just consider it very, very carefully. Take a look. The derivative of power function results in introducing additional multiplier, well, constant multiplier, which equals to the actually the power we are talking about. So when we are integrating power function x powered n, we should always remember that we need to equalize this multiplication by this one multiplier. So in order to get x powered n, you need to consider power plus 1, but also you need to remember that after differentiation you will get it multiplied by its power, so we need to divide by it. Thus we get our extremely easy, but so you need to actually take a look at it very carefully, answer. And that's also where we should be want. If we have any division, in our case division by n plus 1, we should always write something n plus 1 is not the 0. Well, if it isn't the 0, then there is a special case when the power is actually minus 1. And in case power is actually minus 1, you need to integrate 1 divided by x. And it's kind of nice because you actually do know the answer. The answer here is logarithm x, and, well, of course, you should always add plus constant, but always you should remember that it's actually kind of tricky one, because we should add the absolute value of x instead of x in the argument of the logarithm, and we are going to cover the reasons for it in the following video. But, well, you just should always remember that that's the case for the power function, and that's exceptional one. As for the others, it's kind of the same principle, but more simpler, because for the exponent it's kind of easy, because the derivative of exponent is itself, thus the integral is pretty much the same. And for the trigonometric functions, it is still this fun circle of 4, as we covered in the our third week. So, for example, the derivative of cosine function is sine function, and the funny thing here is that the integral of 1 divided by 1 plus x squared is actually a tangent function, which is kind of intriguing, because you have here something like polynomial divided by polynomial, and the result is inverse trigonometric function, which is, well, surprising. And this is one of the most basic integrals you should always study, and, well, I'm happy to introduce you to it. Well, as for the last two things, is kind of understandable, well, and expectable here, that if the derivative of sum is sum of derivatives, thus the integral of sum is sum of integrals. And, well, it's pretty much straightforward and easy sequence here, as well as the one for the constant multiplier. I've changed the name of the multiplier from C to K in order to avoid misinterpretation with our additional any possible constant in the integration below. So we are going to write it in the following manner. If your function is multiplied by any constant multiplier, then you can safely move it out of the integrand, and thus you get this pretty nice and straightforward rule. So, well, let us just summarize it in one sentence. It's the same table, yeah. That's the basic rule for the integrals, indefinite integrals. It's the same table that's for the derivatives, vice versa. And if you just happen to know that some function has this derivative, then you know the integral of this derivative, and that's the end of the game. But in some cases, you need to do extra work here. You need to manage to find this function, well, in case you do not know it by heart. And that's where we move to our two basic rules of calculation. The change of the actual argument of the integration, change of integration variable, and integration by parts. And in order to introduce you to these rules, we are going to use our magic transport board, as always.
So now let us consider two basic tricks of calculation indefinite integrals: changing the variable of integration and integration by parts. Let us start with changing the variable. The design here is as follows. Assume that we have some integral of the function f, and we think that it will be nice function from the table of integration if we substitute our old
variable x with some new variable t in the following manner. Consider that our variable x is actually a function of a new variable t. Okay, so we need to fully substitute all x's in our integral with new variables t. In order to do it, we need to firstly substitute x as the argument of the function f, which is easy, just substitute it with our x over t function. And we need to understand how to change our dx term here, right? Basically, in order to do it, we need to remember what dx actually means. It's notation for the differential of the function, right? Since our x is a function of one variable, single-variable function, thus its differential is simply the derivative of the function multiplied by change of variable t, dt. Okay? So if you pay attention carefully, we simply moved from the functional equality to the equality of differentials, which is kind of easy, right? So what do we get as a result? We get the following expression here. We get integral over the function f at x at t multiplied by the derivative of x multiplied by dt with regard to the dt. Right? So simply we get the composition of f and x functions multiplied by the derivative of x function, right? So that's the rule of changing the variable here. But what should we do to properly understand it? Well, firstly, you all need to understand that instead of normally going from the left to the right, here, right? The good idea here is to go in vice versa, in reverse direction. If you are looking at the integral, you sometimes can easily see that there is some nice block such as the derivative of x, which is easy to substitute with a new variable, right? So normally what people do, people move from the right part to the left part of this equation. So let us consider some examples here, right? So the most simple example here, the simplest one, is, for example, the integral of x divided by 1 plus x squared over the x variable. Okay, so what should we do here? Firstly, we should consult with our table of integrals. Is there any something that looks like this very function? Okay, there isn't, right? It's not the easiest case. So what we should do, we should think about some tweak, some change of the variable of integration in order to simplify our function, in order to include our function into the table, right? So as you can see, the idea of x multiplied by the dx somehow resembles known differential, right? You do remember that x is somehow connected with the derivative of x squared, right? So let us consider that we actually looking at the new variable, for example, y, which is actually x squared. So we need to move from the x variable to y variable in the following fashion. Let us take the differential of both parts of our substitution. Thus, the left part turns into the free differential of y, and the right part turns into multiplication of the derivative of the right part and the change of the variable in it. So we get the derivative of x squared 2x multiplied by dx, right? So let us carefully look what we see here. We see already familiar term x multiplied by dx. So if we try to substitute all x's in our integral, we get x multiplied by dx, which is actually dy divided by 2, right? dy divided by 2. Multiplied by 1 plus x squared. 1 plus and x squared is actually y. Okay, that's a win. We've got simpler integral here. To finalize it, what should we do? Firstly, we should move our constant multiplier from the integral, and as a result we get integral of 1 divided by 1 plus y. with regard to the y. Okay, so that's an easier one. How we should properly do it? Firstly, we can just write our answer straight away. It's kind of easy to understand what is the function which derivative coincides with 1 divided by y plus 1. But instead of it, I'm going to show you once again the idea of changing the variable. In other words, we're gonna call y plus 1 a new variable. I don't know, for example, t. That's basically dy equals to dt. And that's an easy transition. But sometimes it's done in some other more fancier way. Just assume that you somehow move your plus 1, add your plus 1 to the differential up here. So what basically you've done? You've basically said that the differential of some function and the differential of some function plus constant is pretty much the same thing, which is kind of obvious because the differential plus constant is obviously 0, right? So as a result we get 1/2, which is still the same, of integral of dt divided by t, which is a table 1, and we need to write 1/2 of logarithm of absolute value of t plus constant. And then, necessary, we need to move backwards to our initial variable, because we were asked about function over x, and we should answer with the function over x. So we need to write 1/2 of logarithm of absolute value of t is actually y plus 1 and y is x squared, thus we get x squared plus 1 plus our constant. Okay, that's how the change of the variable is done. One could argue that we can omit our absolute value because x squared plus 1 is actually always positive, but let us just keep it for the sake of simplicity here in order to not contradict with our initial table of integrals. So that's the first trick. That's quite easy, that's quite understandable. Other trick is much more simpler, but you should all understand the motivation here. Let us start with the idea of the integral by parts by the derivative of the product of two functions. Consider that we have our multiplication f by g, and the rule here is that we need to write something like the derivative of the first term multiplied by the second plus the first term multiplied by the derivative of the second. And what we are going to do, we are going to integrate both parts of this expression. So as a result we get the integral of the derivative is actually a function which has been tortured by all our procedures of differentiation and integration, right? Because it's the direct and inverse operations here, right? And for the left part, for the right part, we get integral of the derivative of f multiplied by g plus integral of f multiplied by derivative of g. Okay, so that's basically the rule. The rule says that the integrals of two functions, for example, the derivative of some function f multiplied by some function g is actually connected with its multiplication and the integral of moved derivative case. I'm gonna rewrite it in the more fancier way, which is commonly used in textbooks. What we're gonna do? We're gonna say that we're integrating multiplications of two functions, one of which is actually a derivative of some function and the other is some kind of a function. And what we should write the multiplication of initial function minus the integral of the first part multiplied by the derivative of the second part. Okay, so after it we're gonna call our f and g functions first and second part respectively. So why should actually we care about this rule? Why it makes our lives easier? Because what the idea here? The idea here is that we've moved our differentiation from one function, from function f to function g. Why should we actually do it? Firstly, the idea here is that g function is complicated, complex function. And its derivative, okay, let's say it's easy one, is simple function to integrate, right? So we move from the complex function to easy function, right? And their function kind of does not just ruin all the integration procedure for us. So let us consider, for example, the case of integral of inverse tangent or tangent function. So, as you do remember, our tangent function doesn't appear in the table of integrals or doesn't appear in the table of derivative as a result of differentiation, right? So it's kind of complex and we do not know what to do with it until we somehow transform it. So that's exactly the case when we should think about integration by parts. So the idea here is that we call some terms in our expression here the first part, which is the derivative of some function, and some terms the second part. Second part is complex function with easy derivative. So that's quite obviously our inverse tangent function, right? So the derivative of this function is 1 divided by 1 plus x squared. So what's for the second part? What's for the f function? What we can see here is that our function being integrated is kind of doesn't seem like the multiplication of two functions, but we can artificially just write that our function is actually multiplied by 1. It's kind of obvious relation, right? So the derivative of the second function, f, is 1. Thus, our f function is simply x, for example. So, let me close the bracket, and then we're going to rewrite it, what we get as a result. Firstly, what we should start with? We should start with the idea of multiplication our f, which is x, with our g, which is arctangent function of x minus the integral of actually f function, which is x, multiplied by the derivative of our complex function, which is 1 plus x squared, powered minus 1. So as a result, we get x multiplied by our tangent function minus integral of x divided by 1 plus x squared. Okay, by pure coincidence, nobody knows that it will happen. It's pretty much the same integral that we've started in the case of changing the variable, right? So we're going to just substitute our integral with an answer, and let's have a feast and celebrate it. Okay, so we can just write the answer straight out loud here. It is x multiplied by our tangent function minus our 1/2 of logarithm of x squared plus 1 plus constant. Okay, so what we've actually achieved here, it's kind of fun, because we've started with some simple rules, simple cases, with simple integral, and our answer is pretty complex and frightening. So it's actually nice when we can get our frightening answer with simple techniques and everybody understands what we've done here. So that's basically our two ideas that allow us to calculate our indefinite integrals. Now let us consider some more frightening example of the indefinite integral. In order to do it, we are considering integral of absolute value of x. Once again, let us remind ourselves, what does it mean? It means that we need to find all the functions. For example, I'm going to call it capital F of x, that the derivative of that function is our given function f towards x, right? So we need to find all of them. So as you all understand, there is no such thing as absolute value of x in the table of derivatives, right? So we need to somehow come up with more intrinsic idea about how can we do it, how can we calculate an indefinite integral here. And in order to do it, let us just consider the very definition of absolute value. Since the absolute value is the argument itself if the argument is non-negative, and minus argument minus x if x is negative, then we need to find the integral of this piecewise defined function, right? Well, here comes the trick. Since we clearly do know the integral of the first part and of the second part separately, let us just write it down. So let's just integrate our non-negative part, then our negative part, and then we're gonna understand what we need to do afterwards. So the integral of x is x squared divided by 2 by our almighty table of indefinite integrals or table of derivatives, right? So that's only true if x is non-negative. And as for the second part, it's minus x squared divided by 2 for negative variables. So that's quite easy. So since we found our integrals independently, thus we are gonna add two constants. And the idea here is, since we haven't established yet the relation between two parts, we are gonna say that those constants are arbitrary. So the constant C1 does not know anything about constant C2, right? So let us, for example, draw the sample of graph we've just come up with. So the idea here is that we have our parabolic function, for example, something like this, in the positive part, and some parabolic function looking downwards in the negative part, right? So that's something like it, right? Since we do not know anything about C1 and C2, then we do not know how they behave with regard to each other, right? So we do not know nothing about their vertical shift towards each other. Fine, but should we actually care about this vertical shift? Let us once again revisit the definition. Definition says that for any point in the domain of the function f, function being integrated, the function of answer, our indefinite integral, should be differentiable and its derivative should coincide with the value of a function, right? Our function absolute value of x is defined at, for example, x equal to 0, right? But the function we've come up with, our blue graph here, has its discontinuity at 0 point, thus it has no derivative here. So in this very case, we are all kind of doomed here because we do not have a derivative at 0 point. So in order to avoid it, we need to somehow modify our function so it doesn't have any discontinuation at 0 point. And basically it's quite simple. You need to somehow move left and right parts in order for them to be a continuous or just simple, usually ordinary function, right? In other words, you should consider the left limit and the right limit of our parts here, or another, just consider that we have x squared, thus if we are approaching 0, it in both cases approaches 0. So basically for these functions, for these limits to coincide at 0 point, you need two values of two constant shifts, C1 and C2, be equal. I'm gonna denote them as 1 minus c. Okay, so our function, our indefinite integral of the absolute value, turns into the case of x squared divided by 2 or minus x squared divided by 2, or in other words, x multiplied by absolute value of x divided by 2, that's exactly what we're talking about, plus constant shift for any real numbers. Okay, that's the answer. But here let us compare it with another example, which is kind of textbook. The example here is indefinite integral of 1 divided by x. So what does the textbook says? A textbook says that you need to write a logarithm of absolute value of x plus c down here, right? So firstly, why we need here the absolute value? Because our function, our input function 1 divided by x is defined, I'm gonna write its domain down, is defined for all real numbers except 0, right? So the answer should always be differentiable for all real numbers except 0. So if we just wrote our logarithm of x here, then we will restrict ourselves for only positive values, right? So we need to somehow consider a negative value, and since for negative value logarithm of absolute value of x is logarithm of minus x, and we take the derivative, we are looking at our composite function, right? This composition of a logarithm, which is derivative 1 divided by argument, and the derivative of minus x, which is minus 1, thus we get 1 divided by x, so our answer is actually a correct one. But does it actually answer the question to find all possible functions with the derivative coinciding with 1 divided by x? Let us, for the sake of simplicity, consider the graph of our function we are starting with, right? So what we're gonna do? We're gonna draw, for example, our 1 divided by x. It's a hyperbolus. And then we are gonna just write over here, right? Draw the graph of our answer, right? So what our answer looks like? Basically, our answer looks like a logarithmic function with a symmetry towards positive and negative arguments, right? So it's gonna be something like this, and all of you gonna believe that this is symmetrical thing because it's somehow the best I can draw on the blackboard, right? So what we are looking at? We are looking at, in comparison with the case of absolute value of x, the graph of two paths where two paths actually do not connect, right? And one should ask necessarily, should they be connected? Or should we consider the vertical shift between them to be the same, or it can be arbitrarily anything, right? Because if you just think about the indefinite integral of the positive axis, then you can move this part of the graph independently upwards and downwards. Same applies here, but should you simultaneously move them upwards and downwards? Well, there is a clear question to it. Since there is no point of connection, since there is no linkage at 0, because 0 does not include in our domain of our function being integrated, thus there is no such need for simultaneous vertical shift, right? So the full answer here is actually not logarithm of absolute value, but logarithm of x plus c1 if x is greater than 0, and logarithm of minus x plus c2 if x is lower than 0 for any possible c1 and c2 independently. Of course, since this answer is extremely complicated and hard to work with in more sophisticated cases and more complex functions, it's usually omitted, since in order to move from one part of the graph to another, you should jump over the singularity, the point where function approaches infinity, right? Since you shouldn't actually be comparing these two parts of graph. So usually the notation of logarithm of absolute value plus 1 constant is used just for the sake of simplicity. But you should always know that everybody lies and the textbook lies here, right? So the full answer here is vertical shift with 2 arbitrary constants.
Remember, when we talked about derivatives mostly of single-variate functions, we've actually pointed out that by knowing arithmetic and a rule of composition of functions, the chain rule, we've actually reduced our finding the derivative task to a technical issue. You can easily write a program which can do it for you. So is it the case for indefinite integrals? Well, it seems like it's not. That's where it gets tricky, because we should introduce ourselves to the concept of integrable in elementary functions, function actually. So what does it mean? If function is called integrable in elementary functions, it means that its antiderivative can be written in a finite number of arithmetic operations and composition of elementary functions, the ones which we've introduced in the first week. So it basically means that if we are given a function which is written with a formula, elementary function, and then we try to attempt to find antiderivative, we just can simply write this thing down in one formula without any dots, any sums, any such things which can extensively make it more comprehensive and more complex. So, in our case, the case of this definition actually means that some functions are non-integrable in elementary. So let me just try to point this out for you. That does not mean that there is no antiderivatives for them. It actually does mean that we cannot write them down. For example, let us consider some functions like our almighty Gauss distribution, which is your best friend for the rest of your lives. Or some other function like sinus of x squared, or sine of x divided by x, and there are some others. There is actually a theorem that states that they have a derivative. They have an antiderivative, but this antiderivative cannot be written in finite form, cannot be written in elementary form. And just take a moment here and understand what I've been saying here. That's kind of extremely surprising. That's the point when you can be astonished by it, because there is an actual theorem which tells us that there is no function that can be written, but there is some which cannot. And it's fascinating because there is a fact that states of the existence of some function, but it also states that you will never be able to actually write this function down, well, in any non-extremely complex form. And that's, well, that's the real math here. That's the mathematics, and that's called something like Abel-Ruffini theorem, and that's extraordinary thing. You can actually look up it. It's unimaginable experience. So, in our case, whilst we introduced ourselves to the concept of non-integrable functions, we actually should understand what is the class of integrable functions is integrable in elementary functions case. So, we should be able to define that some functions is guaranteed to be integrable in elementary functions and some are not. So what's the case for it? Well, some non-integrable things we've actually seen in the previous slide. So we should come up with the idea of some definitely integrable in elementary class, right? So this class is actually called rational fractions or rational functions. And let's just take a look. A rational fraction is some fraction which is the result of polynomial numerator and polynomial denominator. Well, but you should also consider that the coefficients on these polynomials, well, both in the numerator and denominator, is necessary should be rational numbers, or just any real numbers actually. But we are going to roll with rational here. So If we have our rational fraction, then it always can be factorized to simpler fractions, and thus it can be integrated in a real in elementary functions. Let us consider some, well, most basic example here. So let us find the indefinite integral for the function 1 divided by 1 minus x squared. Well, firstly, you should always understand that this procedure is rather complicated, and as a bonus part of our week, we've actually submitted a full algorithm in form of conspect for you down below. So you can actually look it up and understand that it's kind of extremely complex, and it is something which involves the thing called main theorem of algebra here. But for our purposes, we're going to roll with one of the most non-extremely complex examples here. But the procedure basically is still the same. We need to simplify our rational fraction into the sum of fractions, and then we are going to integrate these fractions y by y. So, in order to do this, we are going to consider our function 1 divided by 1 minus x squared and factorize the denominator. Well, it's kind of a school case. The denominator factorizes in two multipliers, 1 minus x and 1 plus x. So the idea basically is that this fraction, which has been factorized, can also be reduced to the sum of two much more simpler fractions with the same denominators, which are actually our multipliers of our initial denominator. So we need to write something like unknown constant a divided by 1 minus x plus unknown constant, let me call it b, plus 1 plus x. So, what is a and b? You actually can just reverse our operation by writing these fractions under the same denominator, and it will result in something like a plus b plus a minus b multiplied by x in the denominator, and our denominator is still the same. So what we do have here, we do have that 1 should be equal to this polynomial. So you can easily think that it follows that here a should equal b, because we do have x here and we do not have x in initial function. Thus, we should consider that coefficient before the x should be 0, and a plus b actually equals 1, thus a equals b equals 1/2. That's our a and b coefficients. Thus, we need simply to integrate functions 1 divided by 1 minus x and 1 divided by 1 plus x. So in order to do this, we are going, well, first of all, to make some space here and consider this by term. Firstly, we need to integrate 1/2 multiplied by 1 divided by 1 plus x. And that's the case for our basic change of the variable, right? I'm going to make more space here. So, what we've done previously, we've introduced another variable. We're going to call it t, and we've actually moved from x plus 1 to the t. Thus, the t is the x, and that's it, 1 multiplied by the x. So we can rewrite all integral in the form of 1/2 integral by dt of 1 divided by t. So the answer is 1/2 of logarithm of module of the absolute value of t plus
any possible constants. That's the answer. Fine, that's kind of easy one, right? The same thing should be done with our second constant, with our second term. Let us carefully write this down. It's also 1/2 of dx divided by 1 minus x. Thus, we are going to pull the same thing, but you should be extremely careful with it, because we are going to call a new variable 1 minus x. Thus, the differential of new variable is minus the x. So we got minus 1/2 of the integral by the new variable of 1 divided by 2. Thus, it's minus 1/2 logarithm module t plus constant. And the last thing to do is here to reverse our variable to the initial one. And that's how we've managed to do. So, the question here basically is the following. What functions can be reduced, what integrals can be reduced to the case of rational fractions? First of all, rational fractions can be reduced to rational fractions because it's a class. So another one is actually something called trigonometric rational functions, which basically rational functions involving tangent, cosine, and sine functions. That's all can be easily reduced to the rational case. Another one is hyperbolic functions. It's kind of exotic one, but well, it's always nice to know. And well, many others actually, but in order to understand it, you should always consider the following. Integrating irrational fractions is not the answer, is not the best way to actually compute your answer, compute your antiderivative. Integrating irrational functions actually is the way to guarantee that the answer is achievable. You can also find it, but it's not actually the thing you should do by hand. It's kind of algorithmic thing which can easily be done by any in programming package or something like that, symbolic programming package. But it's kind of computationally heavy and well, extremely boring thing. So it is the way to guarantee that answer is achievable, but not the way to fastly get it. But it's always nice to understand where you can get the answer and where you are in trouble. So that's somehow explains our concept of integrability in elementary functions. See you in the following video. So, now we know what is antiderivative. Let us move on to the case of continuous summation. And in order to illustrate this, we are going to use the most basic example, which is the area under curve. So, assume that we have some function f. I've actually drawn a basic sine wave here, and some closed segment from A to B. And we need to understand what is the area under the curve is with one simple addition to it. We need to think about oriented area of this figure, under this figure actually. And let me define this for you in the following manner. Let us just consider that the sign in before the area of the curve is actually coincides with the sign of the function at this segment. For example, if function lies over 0 with positive y's, with positive values, we get positive area, and if it is if it coincides with negative values of the function, it is negative area. Well, it's actually in two places here. So that's what's called a rated area here. But how do we calculate one? Well, consider the most easy case for us to calculate area. It's a rectangle, right? Rectangular figures are extremely nice to calculate area. But how are we supposed to substitute this curve which is actually clearly not rectangular by some rectangular alternative. Well, if we draw something like this, it's kind of rectangular, but it's kind of not the same thing. It's a false area. It's not the same figure, right? So we need to be more accurate and more specific. For example, we need to use some more thinner, much more thinner rectangles, and thus we can get some understanding of the area of the curve by summing these rectangles and around here. So ideally what we should do, we should consider these rectangles much more thinner, infinitesimally thinner, and then we can get some understanding of area under this curve more exactly, right? So let us consider all the necessary build-up for this concept. Firstly, we should understand how do we find a layout for this for the borders of these rectangles. In order to do so, we introduce the concept of partition of this segment. We're gonna call the partition the number of points of this segment, for example, n points here, and we are going to order it from A to B, just for the sake of simplicity, and the maximal length of the segment in between neighboring dots, we're gonna call the diameter of the partition in order to understand well, how wide this partition in general is. So if the diameter is rather small, thus we know that since it's the maximal segment, thus all the other segments are smaller than the diameter. So we do not actually need to specify all the lengths here, we just need to understand what the diameter is. And I extremely should stress out to you that we are not working only with uniform partitions, which implies that all the lengths are the same. No, they arbitrarily can be just chosen as you want, you just need to clearly state what the maximal value is. So that's our partition. So that's kind of borders of our rectangles, right? We are going to build up something like this. But if we now know the width of them, we also need to specify the heights of them, right? And in order to do so, we are going to tag our partition. And well, this partition are normally known as tagged one. In order to do so, we are going to choose arbitrary some point at every segment here. This, and this. Well, every segment has a designated point. We're gonna call it T for each partition here. And thus we get some understanding, because at this point we're gonna call the height of the respective rectangular as the value and function of at this very point. So if it is chosen something like this, we are gonna draw rectangular with this height. So that's our rectangular, and the area of this rectangular is going to be our the one that we are going to put in an answer, right? And remember that it's going to be negative. So we can come up with something which is called Riemann sum, which is basically the sum of all these areas we just defined, right? So what do we have? We have partition that we've set, right? Then at every segment of this partition, we've chosen some point at which we actually consider our function. Thus, we tagged our partition. Then we've calculated the area of each rectangular for each segment of our partition by multiplying the value of the function at this partition by the width of the segment of this partition. Then by summing it, we've got something which is somehow close to our answer, right?
if all the segments of our partition were extremely small, extremely narrow, rectangulars, then we are going to have our area, right? So the last thing we need to do is just take a limit, right? Well, everybody knows when I'm speaking about extremely small, I'm going to take a limit, so here it is. So, but I'm going to stress out, the limit only considers that we are going to have infinitesimal diameter of the partition, and thus we have infinitesimal each segment, and that kind of works for us. Notation here is our common integral symbol, right? And we here have subscript and index here, which describes our segment of integration. So it basically means that you need to consider oriented area under the curve f at x from a to b. That's what it is. But the most complex thing here is that we should consider this limit independently from tagging. When I say we choose our points arbitrarily in the tagging, I mean that we are not actually in power to choose special ones like right and left and the maximal or the minimal one. We just gonna go with any. And we do not specify an actual partition. We just know that it is going narrow, narrow, and narrow, right? So that's kind of a complex thing. The definition of our definite integral, sorry for this one, is kind of extremely complex. Thus, as you may expect, nobody actually uses it, but we are going to understand how to calculate it by node definition in upfollowing videos. So by now we just do know what the area under the curve is and what is the definite integral is. So that's kind of nice. Okay, in the previous video we frightened you. That's fine. Now we are going to explain what we actually have here. After having this complex definition of definite integral, we should consider what it actually means and how do we differ between integrable functions, which can be found, right? Which has its extremely complex limit that we've defined earlier, and non-integrable functions. And in order to do so, let us introduce some boundaries on Riemann sums, called Darboux sums, which is named after French mathematician here. So, if we consider some basic partition, well, just let us just set it and we are not going to touch it for some time. We can always think of some special taggings. For example, for each segment of this partition, we can consider the lower value of the function or infimum value, or the upper value, the maximal value here, or the primum of this function on this segment, right? So any possible area of the rectangular chosen, for example, let us consider this segment, right? Any possible tagging results in the rectangular something like this, in between the small one and the big one rectangulars, right? So thus any Riemann sum is actually bounded by the lower sum, the lower Darboux sum, and the upper Darboux sum, which is written in this nice inequality. So if the difference between them approaches 0, or they are both approaches the same value, then any possible Riemann sum approaches the same value and thus limit exists. So if you just consider some arbitrary function and you need to understand can you find integral, definite integral or not, you should also think about Darboux sums, which defines the boundaries for any Riemann sum here. Let us consider some example. Well,
First of all, let us start with some bizarre example, actually. This example normally called an indicator of rational numbers. So let us consider the function which is called Dirichlet function, which differs between rational and non-rational real numbers. So it has values equal to 1 if the argument is rational, and values equal to 0 if argument is non-rational. So what does it mean for Darboux sums? Well, firstly, whilst I have defined extremely complex function for you, you should expect that the answer is no, you can't find any integral here. So we are going to consider some, well, actually any segments, but I'm going to roll with from 1 to 0. And what does it mean? Let us assume that we have some partition here, right? So what is upper Darboux sum and what is lower Darboux sum? Actually, we're going to think about what is the smallest tagging and what is the largest tagging here. And it's kind of easy, because if we consider any segment of our partition from x minus e minus 1 to x y, here we can actually find things that at every segment we can actually find a rational number and in the very same time non-rational number. Well, because that's the difference between rational numbers and real numbers. You do remember that's what we started our first week with. So here we have rational and also non-rational numbers. Thus, we can find the point where a function has value equal to 1 and equal to 0. Thus, upper Darboux sum here coincides with the case where it is always 1, and the lower is coincides with the case when we actually choose the taggings, which respectively results into 0 value. Thus, the lower sum of Darboux functions for this Dirichlet function for any possible tagging results from substituting this small m with 0, so the lower sum actually equal to 0. And the upper sum here is actually can be calculated by substituting the value with 1, and thus we get the sum of the lengths of segments of partition. Thus we get the length of the whole segment, which is actually 1. Obviously, if we consider any limit here, we have constant numbers for the lower sum and upper sum, thus they actually doesn't approach the same number. So this function is not integrable. So that's the basic but extremely complex example of non-integrable functions. So here we have it. But as we define some non-integrable case, one should actually think of sufficient rules how we can differ from integrable and non-integrable examples. And that's what we're gonna do in the next video. Okay, now, as I promised, we should think about sufficient conditions for integrability. And, well, we've actually recently come up with non-integrable example, and now we should move on to some much more simpler cases, actually. So, we're not gonna try to prove this one for you, but we're gonna just state it as basic cases. For example, if the function is monotonic or monotonically rightish or false whatsoever, or has no discontinuations on the whole segment, then it is integrable on this segment. It's kind of nice things. For example, if you consider x squared, which is defined and plotted in the figure like this, and that's our x squared from 1 to 0, it's quite easy to understand that first of all it is monotonically rises, and second of all it has no discontinuations, well, nicest functions of all. So it's totally integrable. Thus, just let us try to consider how one should calculate the actual integral here. And in order to do so, let us just consider some partial case. It's not a general case you should understand, but we know that for any partition and any tagging, we should get the same limit here, since the function is integrable. Thus, for any special partition and special tagging, the answer should still be the same. So let us consider uniformal partition here. So we have 1 to 0, and we have, for example, n dots in partition. Thus, we have the same length of each segment, and the dots actually 0, 1 divided by n, 2 divided by n, and whatever, up to n divided by n, which actually equals to 1. And let us assume, for the sake of simplicity, that we are considering some point here. Well, for example, let us assume that we consider tagging with the right end of each segment, right? So for each segment of this partition, the area under the curve should be written as follows. The length of each partition is 1 divided by n, right? And we should multiply it by the value of function in our tagged point. Tagged point in our case, for example, for the first one is 1 divided by n squared, right? Okay, that was nice. So for the second one is 2 divided by n squared multiplied by the length, which is the same, and whatsoever, and it goes and goes and goes and goes. So let us just try to rewrite it in the more comprehensive way. First of all, we should consider moving this common multiplier and this common divisor here. So we are getting something like denominator n power 3, and in the numerator we have 1 squared plus 2 squared plus 3 squared, and this goes up till n squared, which is actually the value for the last segment. No, right here. Okay, so it's time to remember your discrete mathematics course, which was the first one in this online degree program, and remember the formula for this sum of squared for first n natural numbers. And it's quite easy. I'm gonna to write this down for you. It is n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6 n power 3. So that's it. If you don't remember, please revisit the video from the discrete mathematics course concerning induction. So, and if you don't want to remember induction, well, that's sort of easy, and just believe me that that formula is right. So the last thing we need to do is we need to actually find the limit, calculate the answer. And in order to do so, we need to find the limit when the diameter of this partition approaches 0. In other words, in our case, if the partition is uniformal, thus the length of each segment coincides with the diameter and equals to 1 divided by n. Thus, if it approaches 0, then n should approach infinity. And we need to consider the limit of this sequence whilst n approaches infinity. And it's kind of an easy one for us, because it's polynomial divided by polynomial, and we all do know how to handle this one. We need to divide both numerator and denominator by the highest power. In our case, it's the third power, and we get 1 multiplied it by 1 plus 1 divided by n, multiplied by 2 plus 1 divided by n, divided by 6. And if n approaches infinity, 1 divided by n approaches 0, thus this is 0, this is 0, and we get 2 divided by 6, or in other words, 1/3. And 1/3 is actually our answer. That's nice, and I'm going to congratulate you with the first definite integral you've actually calculated. So here we are going to move forward with understanding how we avoid these extremely complex cases of taking limits and using some discrete mathematics rules and induction, and for more general case of calculating definite integrals. Okay, so as usual, we should understand that our definition is rather complex, and so we are not going to use it at all. And here is a point where we're gonna to throw the definition out and understand how to avoid using it at all. And in order to do so, we need to establish the connection between an indefinite and definite integrals here. So in order to do this, we are going to introduce the following concept: the integral with changing upper limit. And first of all, let me point this out. We're considering the definite integral where the upper limit is the variable. Thus, the variable of integration has been changed in order to avoid misinterpretation and, well, any possible mistakes here. So, what is our function phi from x? Phi from x is a function which should be calculated as follows. We got some value x, and then we've returned the value of function which coincides with the result of definite integration of our function f from a to x. Okay, the function here is that if function f has no discontinuations on this very segment, then the resulting function is differentiable. And moreover, and more importantly, it's not only differentiable, it is antiderivative of the function being integrated. So, how come it happens? Let us just assume and try to illustrate this in our pictures here. So, assume that we've drawn an antiderivative here. I'm going to call this function phi from x. Well, and the point we are starting with is our point A. So, if we have any function and it is differentiable and antiderivative is necessarily differentiable, as you all remember, then we can, by the very definition we had on the third week, easily and sufficiently approximate it with piecewise linear function, right? And more importantly, this piecewise linear function can be built up with the paths that coincide with various tangent lines in some points. So these points are marked with blue, and the resulting pieces of tangent lines are drawn in red in our pictures. So, in order to understand how much this function changes throughout from A to, for example, B, here, right? We need to understand how much changes our piecewise linear approximation suffers, right? So, since we do know what these segments are, we do know that changes of linear functions, tangent line functions, is actually called differentials, right? And differentials are the results of multiplication the derivative in this point, right, by the change of the variable. But as we know, our phi function is antiderivative. The derivative of antiderivative is the initial function. So here we have function f
from x multiplied by the change of the variable. And in order to understand the whole change of our function from a to b, we need to summarize all these terms, values of f multiplied by the change of variable. And if we want a better approximation by piecewise linear function, we need to shorten these linear segments, thus making the diameter of this distribution, as you can easily see, approach to 0. Thus, we actually end up with our desired definite integral, and that's actually the magical part. We can now stop here for a moment and take a look, because right here we've just connected the derivative, the concept of differentiability, piecewise linear approximation, and the antiderivatives in order to find the value of definite integrals, and that's kind of impressive, right? So, to simplify all our thoughts here, we need to come up with easy, straightforward the rule of calculation of definite integrals. So in order to do here, just let's take a look at the integral from a to b. In our notation, it equals to the value of function phi at the point b, right? But what do we know about the function phi is kind of vague, because we know that it's some antiderivative, but we do not know what the derivative it is, because there are a set of them, right? Called indefinite integral. So we need to define the derivative itself. And it's kind of easy to do, because the value of function phi at the point a, right here, is actually the area under curve from a to a, the area under the segment, the vertical segment, which is kind of obvious that it's 0. So we need the antiderivative which equals to 0 at the point a. Well, in order to generalize and don't think much of it, it can easily be done if we just take any possible derivative and subtract the value at the point a from it, thus taking vertical shift in order to just match our function with a 0 at the point a. And so we get our almighty fundamental theorem of calculus. The definite integral from a to b, in case our function being integrated does not have any discontinuations of the segment, equals the difference of values of any antiderivative in upper bound of integration and lower bound of integration. And that's kind of impressive. So to finish this up, we're going to consider some basic example. For example, let us take a look at the result of integration of power function from 0 to 1. As you all do remember, by this very moment, its antiderivative can be written as 1 divided by n plus 1 multiplied by x powered n plus 1. And thus we need to move forward to this subtraction, right? To this difference. Normally we use a Holoing notation. We drew this large vertical line and write this 0 and 1 as upper index. So as a result, we need to write it in the form of our formula, right? So we need to, firstly, we need to substitute x with upper limit, which equals 1 divided by n plus 1 multiplied by 1, minus the same thing where x substituted by the lower limit, which results to the 0. So we get as our answer 1 divided by n plus 1. That's kind of incredible, because instead of using our extremely complex definition, we've actually managed to fight with this example just by the very our fundamental theorem, which was kind of simple. So it's time to congratulate ourselves with the very fact that we can now easily calculate definite integrals by the knowledge of indefinite. Okay, Now we do know how to actually calculate definite integrals in case of finite segments, right? But since we are actually studying it for the sake of probability theory or mathematical statistics, you should think about the cases when they ask something like, and what if the variable just simply less than 5, for example, or more than 5, and that's kind of implies that we need to introduce summation not only on finite segment, but from the summation from some point up to the infinity. So, for example, we need to define this one, and in order to do so, let us just introduce ourselves to the concept of improper integrals. So, improper integral is something which you can easily define by yourself in naive or intuitive manner. If you need to integrate in between a and some for example, plus infinity, you can just say that you are integrating from a up to some point b, right? For example, this, and then you just need to move b toward the infinity very far. Thus, that's basically what it is. In more formal terms, you need to take a limit of all possible integrals, right? From a to some changing upper limit b. So this is called improper integral, and of course, where there is some limit, you always should think about that it could exist or could not exist, right? So if it exists, that the integral is called convergent, or it says that integral converges. Otherwise, it does not converge, and well, that includes the case of the limit equals to plus infinity. Okay, so one more important thing here to understand, and that's when we are talking about the upper limit approaching the infinity, we should always consider that the function is integrable at every segment up to this infinity point. In other cases, in other words, we should understand that the function is integrable on any subsegment on this set from a to plus infinity. So, how do one should calculate these improper integrals? It's kind of easy because we always need to use our fundamental theorem of calculus. So let us combine our definition and knowledge of fundamental theorem of calculus in the following manner. Assume that we have to calculate the integral of f from a to plus infinity, thus we need to find a limit. But the limits are very familiar definite integrals, and then in case we do know some antiderivative for function f, we can just substitute the integral with the difference of this antiderivative in upper limit and lower limit. Right, but if we carefully consider this equality, we can see that only the term f at b point actually involves the variable that we are considering in the limit approaches our plus infinity. And the second term is a constant one, and thus we don't need to consider limits for it. So it can be simplified in the form of we need to find a limit at the point b and then subtract the value of antiderivative at the point a. In other words, fundamental theorem of calculus works for the improper integrals, but if you cannot just substitute x with an actual value, well, in case of plus infinity you cannot, because plus infinity, as you do remember, is not a number. You just need to consider a limit at this point instead of actual value. That's it. That's pretty straightforward. So let us move on to some example. For example, that's once again extremely common thing in probability theory. So we're gonna just tackle it right away, and this is something which is called exponential distribution, and you will be familiar with it and you will use it all over the course. So First of all, we need to assume that we need to find antiderivative here. So we need to integrate exponents of minus a multiplied by x. So how we should do it? Well, as you all understand, we need to substitute our variable in the following manner. I'm going to introduce a variable y, which equals a multiplied by x. Thus, a multiplied by differential of x is differential of y. Okay? So the last thing we need to do is to actually write all the thing down. I'm going to stress out that I'm not writing down all the limits of the integral here in order to avoid thinking about how they're going to change under my change of variables, and I'm just going to move both backwards to the initial value after I get the answer. So what we have here? We have here some integral of what? Of exponent of minus y, right? Multiplied by old time differential of x. Now it is differential of y divided by a. In other words, we get 1 divided by a multiplied by integral of exponent of minus y towards y. And we do know that this is pretty simple. It's minus 1 divided by a multiplied by exponent of minus y. And we need to actually substitute it with y equals ax to move backwards to the initial variables. And thus we get minus 1 divided by a multiplied by exponent of minus ax, and the only thing left to do is to add our actual limits here. So what we should do, we should write down the limit of x approaches plus infinity minus 1 divided by a multiplied by exponent of minus ax, minus the value of the antiderivative at the point 0, right? At the point 0, exponent equals to 1, thus we get minus 1 divided by a. So let us carefully look at this limit, right? So first of all, here is our constant multiplicator, and well, we don't care about it. It can be easily tackled. Right, we are going to consider our exponent right here, right? So what are we looking at? We are looking at the power which approaches minus infinity, right? Exponent of minus infinity approaches 0, as we stated at our second week. So the whole term approaches 0, thus our answer is 1 divided by a. And that's it. That's basically how you do calculate your improper integrals. You need to find your antiderivative, and then you need to find additional limit in order to substitute it into fundamental theorem of calculus. So let us consider another crucial example of improper integrals, the integral of the power function. So it's x powered minus a. For the sake of simplicity, firstly let us assume that a doesn't equal 1. Okay, I'm going to write this down. It's our first case, all right? So what we should do here, we should calculate our antiderivative, right? And in order to do so, we need to divide 1 by power of x plus 1. This results in 1 minus a multiplied by x powered 1 minus a. And afterwards, we need to substitute our x with upper and lower limits. So the question of convergency here actually stems on the fact of the existence of the limit at the upper point, right? So we need to establish whether the limit of this function at the plus infinity actually exists and in what cases it doesn't. In order to understand it, well, it's kind of easy because once again we have a constant multiplier and then we have power function. So we need to decide whether the power function has a limit at the plus infinity or does not. And it's pretty much easy because, as you do remember, the power function with positive power actually approaches plus infinity. It looks like this or like this, right? And the power function with negative values actually looks like this, negative power, right? So there is a simple one. If the power of x is positive, then the limit doesn't exist. The limit function approaches plus infinity at infinity. And if the power actually is negative, then the function approaches 0 at the plus infinity. So we are going to write this result down. If a is not the 1, and if a minus 1, okay, that's 1 minus a, is greater than 0, then the integral does not converge. I'm going to symbolically write the arrow and just cross it. And if 1 minus a is actually negative, the integral converges. Okay. And what's for the case of a equal to 1? Okay, we are going to look at integral of 1 divided by x. And well, once again, you do know that the answer is logarithm of the absolute value of x. You need to substitute with upper and lower bounds, and once again we need to understand what is the limit of logarithm of plus infinity is. As you well know, it's plus infinity, and thus the integral does not converge. That's fine. So we can simply add this case in the scope for the not convergent cases. Okay. Let us summarize our results here. The integral that we've talked about converges if a is greater than 1 and does not converge otherwise. That's fine. But why do we need this special and pretty simple case? We need it in the following idea. Sometimes it's hard or impossible to calculate actual antiderivative, or, well, it's easier to compare the function to some which is when actually in knowledge of the answer, right? For example, just assume that we are speaking about improper integral of the function f, and we have some function, for example, g, and we do know that both functions lies over 0, they're both positive, and one function is always greater than the other. For example, let us assume that g is greater than f at every point, and the improper integral of g converges. Then, understandable, the proper integral of f converges too, because the only way it can be not convergent is its area under this curve approaches infinity. But if the area under f curve, the red curve, approaches infinity, then the area under the g curve also approaches infinity, because one actually includes the other, and thus the integral should also be non-convergent. That's normally called a comparative rule, or rule of comparison, in terms of deciding whether the integral converges or not. Let us Just think of some basic example here. For example, the integral which is x divided by 1 plus x squared, right? Well, you can proceed with actual calculation of the antiderivative, and we've done it with our magic report at the very beginning of talking about antiderivatives. But here we are going to say something more general. Okay, as for example, if we take a look at the function x divided by 1 plus x squared, right? You've actually seen the antiderivative of it. We've started with it when we were using our magic transport board. But whilst it's easy to just rewrite the answer here and try to find limits, we are going to roll with some more, much more easier method here using our rule of comparison. So we have our function, which is x divided by 1 plus x squared. And we're going to say that it is somehow comparable with some function with known answer. Right now, we know answer for all the function which are power function of x, right? So maybe we can come up with some comparison with it, okay? So asymptotically speaking, we are looking at the function which is somehow close to 1 divided by x, right? Because the denominator grows as x and denominator basically grows as x squared, and they are equivalent in this manner, right? So in order to understand how this integral converges, we need to understand and remember how this converges. And as we previously stated, integral of the function 1 divided by x does not converge. So, arbitrarily speaking, we need to come up with some inequality here. For example, we need to say that since it does not converge, the function we are comparing it with should be greater than it. So maybe we should write something like 1 divided by 2x's here. But informally speaking, equivalent functions are basically the same. They are bounded by each other. So if one of them converges, then the other one converges. And if one of them doesn't converge, then the other doesn't converge. And thus we can even generalize our comparison rule into understanding how equivalent functions actually work here. So by using this very easy example, we can just, without any calculations of additional antiderivatives, just call the answer straight away. At the very same time, let us just take a look at the Gauss distribution, exponent of minus x squared here. I'm going to drive a schematic here for you. And what we're going to look at, we're going to look at the fact whether this integral converges or not. So we need to come up with something which is can be used as a comparison for this function. Let's just take a moment here and think about it. Firstly, what we should understand that this function, as we do know whilst we were talking about functions asymptotics, is extremely fast at approaching 0 while x rises up to the infinity, right? It is faster than any possible polynomial function. It's faster than any power function. So if we do use this function and we try to compare it with some known polynomial function, we already know the answer. But as for polynomial functions, that is kind of tricky, because we've actually spoke about the convergence on the segment from 1 to plus infinity, and now we're talking about from 0 plus 1 to infinity. And as you all do understand, 0 is slightly more complex than 1 towards functions 1 divided by x or x squared, right? It's kind of another tricky point for it. So we are not going to compare it with a power function, and we are going to compare it with a widely known function that we've actually calculated on the previous video. Do you remember we've worked with something which is called exponential distribution, or just basic exponents
of functions, right? Basic sum of linear axis, right? So let me just consider the following one. Does this inequality hold? Exponent of minus x squared is less than exponent of minus x. Well, in order to understand it, we need to compare powers, right? Because we are looking at exponent of obviously negative numbers, thus the greater the number, the lower the exponent. Here, well, obviously x squared is greater than x if x greater or equal than 1. So for the segment from 1 to plus infinity, this inequality holds, and thus we can easily call it convergent, because we've actually calculated the integral of exponent of minus x on the previous video, and there was our answer. So limit obviously exists. So what for the actual integral we are looking at, which is not from 1 to plus infinity, which is from 0 to plus infinity? And that's kind of easy, because as we do know, we can add areas under curves, because, well, if you want to calculate the area of two figures, you just need to summarize the areas of two separate paths, right? So we need to write the integral from 0 to 1 plus the integral from 1 to plus infinity. As for the second one, we actually do know that it necessarily converges. But as for the second one, we do not even care about convergence, because it is an integral definite, and more importantly, with finite limits, with finite bounds, and more importantly, our function being integrated does not have any discontinuations on the segments, so it necessarily is integratable. So as a result, this also is a nice number, and all integral actually exists and converges. And it's kind of a really interesting thing, because as we previously stated, we cannot calculate the antiderivative for our exponent of minus x squared function, right? But we can actually quite simply call it convergent. So thus it makes sense that all our kind of tricky science here is actually useful and can be used in understanding why do we actually consider some basic example from probability theory and does not actually call it non-sensitive and all the other stuff. Okay, so at this very point we are actually in power of calculating any possible definite integrals, whether it's proper or improper integrals, using our fundamental theorem of calculus. Now it's time to think about how the numerical methods for calculation, whether it is not possible to calculate antiderivative, works, and what does it stand for. And that's the theme of our following video. Okay. Now we should consider the case where we are not actually able to find the antiderivative in elementary functions, or maybe because we are actually considering real-life examples when we are coming up with some data-based functions. Functions are always given in, not always, but often given in only in certain points, or just being introduced some grid, and then the function on the grid is given. So what we should think about, how are we supposed to find any integral or just approximation of definite integral in those cases. And in order to do so, there has been proposed a number of numerical methods, and we are going to cover some of them, most importantly stressing out the error and its order for each of them.
So we start with some basics in here, which is midpoint rule. Well, the most basic idea of numerical method is just take what we've been doing whilst we've been defining Darboux sums and use it for the calculation. So what we've done while we defined Riemann sums or Darboux sums, we've substituted our function and area under the function, which with some rectangular, right? So what rectangular we should choose? We can go with just left or right rectangular, or maybe we can just take a midpoint, which coincides with the value of function at the middle of the segment of partition, and then calculate the area under the rectangular, which coincides with the value of function at midpoint by the height. So basically the integral here is approximated with the following formula. We calculate the length of the segment, which is difference between b and a, and then multiply it by the value of function in the middle point. So if we use this approximation for every point of our uniform partitioning, then we get some error, right? And this error is kind of fun, because what we have here, this error which can be asymptotically assessed by 1 divided by n squared with some constant multiplier here. This multiplier is genuinely important because we are going to compare it in between the methods. I am stressing out that one part of this multiplier is actually the maximal value of the second derivative, which is kind of interesting, because if your function which you've been considering has unbounded or extremely high values of the second derivative, thus the actual mistake of your numerical methods can be rather high. Same case applies for the next method, which is trapezoidal rule. And trapezoidal rule is basically the idea that instead of approximating with rectangular figure, we're going to approximate it with this trapezoidal figure, which is formed by drawing a chord between the ends of the graph coincided with the segment of the partitioning. By the rule of the area of trapezoidal figures, we are having just an average value of the vertical segments, thus f at a plus f at b multiplied by the length of the segment. And the error is pretty much the same, but I am going to stress out that, that our higher boundary is 2 times higher because of the 12 multiplier in the denominator. Thus, it actually doesn't mean that trapezoidal rule is normally worse than an actual midpoint rule. It's just that the error is guaranteed to be under this measure. So, well, actually, normally you should expect that in practical tasks, trapezoidal rule is better than midpoint rule, and well, your picture actually implies that's kind of the point here. But this is somehow a sequential simplification here, because we started with midpoint rule, which is approximating the function with a constant. Then we moved to approximating the function with a straight line. And then we are going to approximate the function with parabola here for the Simpson's rule. And that's where it gets tricky, because in order to understand it properly, you need to understand what is Lagrange interpolating polynomial is. But since we are not taking it into consideration during our course, and you can look up all the necessary theory in the bonus materials in the description under below, you just need to understand that the general idea is that if you have 2 points, you can drive one and only straight line. with them. But if you have 3 points, you can draw one and only parabola, or the polynomial of the second degree here. The rule is basically if you have n points, then your approximating polynomial is the degree of n minus 1. Thus, the result of integration is kind of complex, but it actually pays off, because you are looking at sine function drawn in dark red, which is approximated by the parabolic function, which is drawn in green. And this is extraordinary, because if it fits practically ideally here, and the area is bounded by the fourth order of 1 divided by n, and once again, the emphasis here on the included maximal value of the derivative. In our case, it's the fourth derivative of the fourth order. And it's kind of the most intriguing thing, because normally if you look at some functions, you expect the derivatives to be bounded and bounded at much more stricter after several differentiations. But it's not the case for some complex ones. For example, if you consider function like x powered x, which we considered during our talk about derivatives, it has kind of unbounded derivatives, and especially for the second and upper ones. So it's kind of unintuitively for these functions, midpoint rule is better than trapezoidal and Simpson's rule, and you are free to check this with our involuntarily and unmandatory programming task, which is attached to this week's additional materials. So, summarizing all these 3 rules, now you are in knowledge of the basic techniques which can be used to numerically definitely integrate some function over some segment. But the most crucial point here is to understand that whilst are bounded by different values, here you carefully need to understand the properties of the function to use the correct method here.
Now it's time to build up an optimization procedure out of this base. So, let us once again cover what we do know. We do know partial derivatives, we do know the generalization of convexity, and we do know some relations between convexity and the optimizations from the single variate functions. So we need to establish how to properly move with this procedure for the multivariate case, and how to characterize this function growth with all the concepts we already know for the multivariate functions. The following week we are going to firstly start with the idea of directional derivative and its relation to gradient. Then we are going to understand the sufficient condition of multivariate extrema, and we will finalize with the idea and motivation of a gradient descent and brief description of your final project. See you in the following video. Firstly, let's start with the idea of the directional derivative. And we need to be honest with each other. When we defined partial derivatives, we actually defined the derivatives of function restrictions. Restrictions towards some preferable directions, right? Firstly, what we've done? We've considered only function which is restricted by the plane well, in horizontal projection with this horizontal section and this vertical section, right? That was how we defined our partial derivatives. But what if we are thinking about the growth of function towards some other direction, some other plane, some other screen which is not horizontal or vertical on x or y plane, right? What is the speed of growth and how should one properly define it? The answer is, as you may guess, the directional derivative. Well, so firstly, as the directional derivative has two parts, the word derivative is kind of familiar for us. We need to understand what is that directional means and what is the direction properly defined for mathematics. Well, obviously, the direction on the plane is a vector, right? Because if you have certain just arbitrary point and you have to show some direction, you just go into something like this, go there. That's a simple arrow, right? So, first we need to understand something. The direction doesn't have a length in a way that, for example, a segment has a length, or the way that the dot goes from one to another, a curve has a length, right? The direction has only the idea of where to go, where towards the, for example, axis of the plane, right? So, there is an assumption that the directional vector is always normalized, or in other words, its length equal to 1. That's fine. So, well, in two-dimensional cases, basically the directional vector is a vector which is has cosine and sine functions of the angle with, for example, OX axis, right? So let us consider some simple graph here. We have our axis, we have our 0 point, and then what? Then we have directions for partial derivative towards x, right? 1, 0. Direction for partial derivative towards y, 0, 1. And some other direction, I'm gonna call it L for most of the slides, right? So what is this direction? This direction is basically a vector with unified length. Thus, by the Pythagoras theorem and by definition of cosine and sine functions, we can actually find its coordinates if we do know the angle between this vector and x-axis, right? So, if this angle equals to, for example, gamma, then we can proceed with coordinates cosine gamma and sine gamma respectively, right? Sometimes these coordinates are called cosine of directional angles because, as you may obviously understand, that the other angle here is p divided by 2 minus gamma, and its cosine is basically the sine of gamma by the very basic trigonometric rules. So, now we know what is the direction, right? So let us try to define a derivative from here. So, what is the most basic knowledge of the derivatives that we do have? The derivative of single-variate function is the limit of function change towards the argument change, right? So let's try to write it down. Firstly, formally, we have two-variable function, f towards x and y, given point, and the direction. We are going to use a notation as for the partial derivatives here. So basically, we are writing that we are in a search for the speed of change of a function towards the direction L, right? And then we are, well, just writing the very basic thing that our relation of function change to our function argument, as we always do in a derivative definition. But the thing here is how one should define function change and the change of the argument. Well, firstly, let us consider some basic setup here. Here is our point,
AB, hero's direction, and assume that the second point, the point we are comparing ours with, okay? Since we are considering the change of function and the change of argument, we need to consider some other point and compare this other point, for example, xy, with ours. But that's not an arbitrary point, right? That's the point on our direction, the point on the straight line which starts from the point AB and follows the directional vector L. Okay, so since it is like that, then the change between x coordinate of the initial point and the x coordinate with a point xy is basically should be proportional to the x coordinate of the direction, right? The same applies for the change of the second variable of the y change. Thus, the change of the function is basically the difference between the value at the initial point, the point AB, and the value at the point which we've got as a result of applying this directional vector to the point AB t times. Basically multiplying our direction by t. A nice touch here is that the distance between the initial point and the point xy, the point we were comparing our function with, is proportional to t. It actually is t because the length of our direction equals to 1. So we have pretty much all the setup we need, we just need to write the result down. So, as a result, we get that our directional derivative is the limit towards t approaches 0, the change of the function divided by t. Once again, I'm gonna stress this out. You need to normalize your direction here, otherwise your answer will be drawn exactly in the length of the direction times. And one more thing, I'm gonna give you this notation once again, except that the notation written on the slide is operational, and the second notation is the usual one for us with a lower index. So that's what is directional derivative through its definition. Let us consider some fine example here. First of all, let's just stop for a second at these very functions and understand why it is so disturbing here. We are going to proceed as follows. We are not going to consider whether it's differentiable or not. It's not, by the matter of fact. We're just gonna think about whether or not it has a limit at the point 0, 0. And here where it gets tricky, because let us assume that we are looking at some approach, for example, x equals t, y equals 0. Quite common, our horizontal approach, we did this on the second week. Our function turns into, well, 0 divided by t powered 4 plus 0, right? So basically it is 0. So if there is a limit of this function at 0 point, it equals to 0. But if you consider non-straight, parabolic, quadratic approach, for example, x equals t, y equals t squared, then the function turns into 1/2, and 1/2 actually approaches 1/2, whether or not you are taking any limit. So this function doesn't have any limit at 0 point, thus it's not continuous, it's not differentiable, it's utterly disastrous. But what about our derivative? What we should do? We should consider, for example, some direction, right? We need to understand what the direction is all about. So let us just take arbitrary direction
cosine alpha, sine alpha. Right? Who cares? We can do just in general case. Thus, we need to, well, since we are talking about AB equals to 0, 0, we need to compute the limit of st approaches 0, the change of function minus its value at 0 point, which is 0, right? Divided by t. I'm going to change x and y straight out by t multiplied by L to make it simpler. So what we're going to have here? We're going to have t squared cosine squared multiplied by t sine divided by, okay, this is a disastrous one, t powered 4 cosine powered 4 plus t powered 2 sine powered 2. Okay, this kind of frightens us, but we can work this out. First of all, we can just divide numerator and denominator by t squared, and we are left with a t in the numerator and t in the numerator of the whole fraction here, so we can divide it also, and thus we get some, well, pretty nice expression here. We get sine of alpha multiplied by cosine squared divided by t squared. Well, and there goes cosine powered 4 plus sine squared, right? If t approaches 0, this whole term approaches 0, and thus we have our answer. Cosine squared divided by sine alpha. Well, and in case alpha is not 0, we can actually count on this very answer, right? So let us just take a moment here. This function is bad. This function is not continuous, this function is not differentiable, but it has directional derivatives for most of the directions, right? Okay, this is kind of funny because even if you can't say anything good about this function, it doesn't have decent linear approximation, it still its growth towards various directions can be pretty much assessed easily and fully. Now we have come up with the definition of directional derivative. Okay, this is almost certainly nice, but it's kind of vague and, well, you actually don't want to calculate it all over again when you need to find the directional derivative. So we need to find an alternative way, an easier way, maybe more computable way to find a directional derivative in a given point. In order to do it, we are going to first of all remind ourselves some concepts that we already know. First of all, let's start with the gradient, which is a vector of first derivatives, right? Written out here. And the scalar product of two vectors, which is, well, in our two-dimensional case, is multiplication of coordinates summed. Also, it has a geometrical meaning, which is basically multiplication of vectors' lengths towards the cosine of the vector in between them, which is schematically drawn in the picture on the slide here. So, first of all, let us revisit some basic scalar product properties here. Is this symmetrical with, well, no surprise here, because obviously its geometrical sense is symmetrical, right? You do not care on the order of multiplication of two real numbers. And for the others, it defines the vector length, it is bilinear, and it defines the angle between vectors. That's all we already knew, right? It's kind of the easiest part of all our course. But what we also do know, we also do know what is a differentiable function, right? The differentiable function is the function which is approximated by its tangent plane thoroughly. In our case, it is infinitesimally towards the distance between a given point and the point of approximation, right? So why do we are building all of these steps on top of each other? Just to define the directional derivative more easily. Let us just try to look at our definition of differentiation in terms of directional derivative. If we are computing directional derivatives, then the change of argument, we've drawn it earlier, is t multiplied by x coordinate of the direction, and the change of y coordinate is t multiplied by y coordinate of direction, right? More importantly, the distance between the function and the approximation, the function at a given point and the approximation point is simply t, since our direction is normalized, right? So let us try to write the definition of our directional derivative down. What we get? We get a limit when t approaches 0, change of function divided by t, right? Assume that our function is differentiable at the point AB. Then the change of function can be rewritten in terms of first derivative and an infinitesimal function towards the distance, right? So let us write this down, and we are going to substitute the change of argument with tlx and the change of y argument as tly. Well, and well, the actual distance between two dots with the t as we computed earlier. So what we do have here? We do have here sum in the numerator proportional to the denominator, right? To the t. We can divide both numerator and denominator by t, and thus we get, well, the first term, which is independent from the value of the limit, right? The second term, well, the same thing, similarly. And the last thing we have here is small o from 1, which is simply infinitesimal function, as you do remember. Thus, its limit is just equals to 0. As a result, we get pretty nice notation. We get partial derivative multiplied by the x-coordinate of the direction plus partial derivative towards y multiplied by the y-coordinate of the direction, or simply scalar product of our gradient and our direction. That's extraordinarily nice formula. So we established an easy relation between the directional derivative and the gradient, and the derivative itself. It's a scalar product, right? So let us consider some example here. Just let us take a look at function x squared plus 2y squared, for example, at point 1, 2. And, well, we are going to ask ourselves a question. What is the direction with the maximal value of directional derivative? Just
an easy one. So, what we need to do? Firstly, we do not argue even that the function f is differentiable at the point m, right? Because it's polynomial, thus it has a decent partial derivatives. You do remember our sufficient condition of differentiability, right? So, we need just to find here the gradient of the function at the point 1, 2. In order to do so, I'm going just to write partial derivative towards x, which is 2x, and partial derivative towards y, which is 4y. And then we are going to substitute y and x with 1 and 2 respectively, thus we get 2, 8 as a result. That's our gradient. So, what we're gonna think about here, we have some arbitrary direction cosine alpha, sine alpha, and we are gonna speak about what its maximal value of this very weird expression, right? So firstly we need to compute our directional derivative, which is simple scalar product of the gradient we've just found and our arbitrary direction, which is 2 cosine functions plus 8 sine out of alpha, which is nice and pretty obvious, but it's kind of tricky to answer what is the maximal value and why. So in order to do it, we are going to draw some pretty approximate picture. Assume that that's our point, 1, 2. Doesn't look like it, but it's never mind. And we have here our gradient, right? So what we are talking about is computing our directional derivative with arbitrary direction L. Let us revisit the idea of scalar product, right? What we do have here? We do have here also not only simple formula for coordinates, right? But also its geometrical meaning. In other words, we can state that it's the length of the our gradient multiplied by the length of L multiplied by some, well, angle. We are going to call it, for example, gamma. Well, the length of the gradient, well, it's quite easy, right? It is 2 squared plus a squared. Okay, that's a nightmare. It's square root of 68. Square root of 68. Let it be. The length of the direction is always 1, and the thing that is left is, well, cosine of some arbitrary angle gamma. Thus, in order to come up with the maximal value, you just need to understand what the maximal value of cosine function, which is 1. So the maximal here is square root of 68. Okay. By doing so, we've actually come to a very interesting idea here, because not only we spoke about whether or not is geometrical meaning is more important than the actual computational rule for the scalar product, we also found that the maximal value of directional derivative somehow equals to the length of the gradient. We are going to use that rule further in order to establish the direction of maximal growth and the speed of maximal growth of the function at a given point. Since we established in our latest example that the maximal growth is somehow related to the gradient, let us try to generalize this concept for arbitrary function and arbitrary point. Firstly, let's start with revisiting our calculation rule for the directional derivative. The directional derivative equals to scalar product of the gradient at the given point and the directional vector in case the directional vector is normalized. Also, we are going to stress out one more time that we are particularly interested into the geometrical sense of the scalar product, which is a multiplication of the length of the vector with cosine of the angle in between them. So, the question is, for a fixed point, fixed function, what is the direction of maximal growth? That's kind of straightforward. Moreover, if the point is fixed, then one should expect that partial derivatives are fixed, thus we know the values at this very point, thus the gradient is fixed and the length is simply known, and we could not alter them. The length of the direction is pretty much the same, it equals to 1, thus we couldn't change it either. So the only thing we are actually able to modify here is the cosine of the angle in between the gradient and the direction of the differentiation, right? So basically the only thing we can changeable here is this. So by the definition of the cosine function, the maximum value of the cosine function is 1. And it happens if the angle between two vectors equals to 0, or vectors are co-directed. So to sum up what it does mean in terms of our maximal growth and the direction of maximal growth. The speed of maximal growth, the maximum value of the directional derivative for any point for any function, is differentiable, is the length of the gradient at this very point. And the direction of maximal growth is the gradient itself. Basically, of course, formally we should say that the direction is a normalized vector, thus we need not only state that it's co-directed with the gradient, but we should normalize the gradient. But it doesn't change the very idea that at this very point, the gradient shows not only the direction where to go to get the maximal value, but how fast your function changes in around there. So, let us consider, for example, some basic function like z equal to x squared plus y squared, right? So that's our parabola, which is resulted after the rotating our functions. We stated it in the first meeting of this function in the earliest weeks. So first let us start with considering the gradient of this function, which is 2x to y. Thus, for any possible point AB, the direction of maximal growth at this point, I'm gonna write L max, is well, basically 2a to b's divided by the length of this vector. It's kind of complicated. And the value of the derivative on this direction is 2 square root of a squared plus b squared, right? That was kind of easy. By the matter of fact, the direction of maximal growth also state the direction of minimal growth or maximal decrease. If you will, it is minus gradient or anti-gradient. And we're gonna use it in the following slide. Now, since we know partial derivatives and the direction of maximal growth, the essential idea is to understand how to find the point where a function has maximal or minimal value, how to define function extrema. So basically, we are going to generalize all the things we already said for the single variate function. Let us start with the basics. Let's start with definition. What point is called extremal? A point is called extremal if in some neighborhood of this point function has the greatest or the lowest value at this very point. That's quite the same as it was before.
So what we do remember? We do remember that being extremal is also somehow connected with the first derivative of a single variable function, right? First, let us remind ourselves that we've covered the concept of stationary point. The stationary point is a point where all first partial derivatives equal to 0. Well, in other words, the function at this very point has 0 speed of change at any possible direction. As you maybe do remember, the stationarity is not sufficient but necessary condition for extremum. It basically means that the function has an extremum at this very point, then and differentiable actually is here, then this point should be stationary. But it's not a sufficient case, and we are going to show it in the following manner. Well, consider two functions, our rotating parabola and function x squared minus y squared, which is hyperboloid. So, firstly, let us assume that we are going to compute a gradient for both of these functions. For the first function, it is 2x to y, and for the second function, it is 2x minus 2y, right? So basically, if we are looking for all possible stationary dots, here in both cases, the stationary point is unique and it is 0, 0, right? But as we clearly understand, for the first function is almost certainly a minimum and a global minimum, because both x squared and y squared couldn't be less than 0, and at the point 0, 0, the function has value 0, which is a global minimum for it, right? But as for the second function, if we, for example, assume the restriction of the function by y equal to 0, thus we get nice f or z equal to x squared, and the point 0, 0 towards x squared is a minimum, right? But as we consider another restriction, for example, x equal to 0, then we get our f equal to minus y squared, which results into the maximum in the point 0, 0. Thus, basically, for the one restriction, it's maximal value, for the other, it's minimal value. We've actually already seen this surface. It was looking kind of a saddle one, right? You do remember we had one parabolic function looking upwards and other parabolic function looking downwards. Basically, this is a case where a stationary point doesn't have an extremum in it. So if we already established a necessary condition, then we need to think about the sufficient one. And let's follow the same rule pretty much here. For the single variable function, the sufficient condition was almost about the concavity or convexity of the function. If you do remember, if the function was convex in the stationary point, then it was a minimum. And in order to remember it, we draw something like this. It is a convex function, and concave function something like this. This is a minimum, this is a maximum, right? So convexity is extremely linked with the optimization in our case. So let's just try to use the same principle here. If the function is convex, that's a minimum. If the function in concave, that's a maximum. For the multivariate case, which is extremely useful here, because we already established how to find whether the function is convex or concave in case of multiple variables, right? In order to do so, we've considered whether or not the second differential of the function is positive or negative semi-definite. I'm going to remind you. Firstly, we've looked at the full form of the second differential, and we've looked at it as a quadratic function of towards dx either or dy. And we've considered the d value, which is the result of multiplication of second derivative towards x 2 times multiplied by second derivative towards y 2 times minus squared second derivative towards xy.
And the idea was that if this value, which is minus discriminant of the parabolic function in second differential, is positive, then by deciding whether the first coefficient is positive or negative, we can differ between convex and concave cases. And if the discriminant is negative, then basically we have a non-extremum case. So let us try to use this rule and an example show how all this works just from the start to the beginning. Firstly, our procedure works as follows. Find partial derivatives, then find stationary points by solving the system of equations, then find second derivative and decide whether or not the second differential is positive or negative semi-definite. So the example we are going to look at is the following. X powered 4 plus y powered 4 minus x squared minus 2xy minus y squared. So let us start with our procedure gradually. Firstly, let us start with partial derivatives. Partial derivatives, here I'm going to write them down. Well, all of them actually, because we are in need of second partial derivatives afterwards to decide whether or not this second differential is semi-definite. So for the first one, partial derivative with regard to x is 4x powered 3 minus 2x and minus 2y, right? And with regards to y, well, pretty much the same, 4y powered 3 minus 2x minus 2y. We need to find stationary points afterwards, but I'm going just to find second derivatives here. So if we differentiate first partial derivative towards x another time towards x, we get 12x squared minus 2. The same applies for partial derivative, second partial derivative towards y 2 times. It's 12y squared minus 2. And for the case of second derivative towards x and y, we get minus 2 simply. Okay, so the next thing to do is to solve our system of equations in terms of first partial derivatives equal to 0. Well, as you can see, in both parts, in both equations, there is a block minus 2x minus 2y. Thus, basically, this means if those two are equal because they do coincide, then the other terms are equal, which is 4x powered 3, 4y powered 3, because the right side of both equations are the same. Okay, so this implies that in stationary points x equals to y, thus we get an equation 4x powered 3 minus 4x equals 0. We can remove 4, thus we get x powered 3 minus x equals to 0. Thus we get all possible solutions. X equals to 0 equals to y, and x equals to y equals to 1, x equals to y equals to minus 1. Okay, so we get basically 0, 0, 1, 1, 1 minus 1 minus 1 stationary points. Okay, so let us start with 1, 1 and minus 1, minus 1, because simply, as you can see from the look on second derivative, they are quite the same towards the idea of the value of second derivatives here. I'm going to use a green here to stress that I'm working with these two functions. So basically, if we substitute x and y with our stationary point here, we get 12 multiplied by 1 minus 2, which is 10. This is still minus 2, and this is 10. So we need to decide what to do with our second differential. In order to do it, we need to find our negative discriminant, the d capital value, which is 10, second partial derivative towards x 2 times multiplied by 10,
second partial derivative towards y 2 times minus 2 squared, which is 96, which is greater than 0. Thus, our second differential is actually semi-definite, and since our second derivative towards x 2 times is greater than 0, we get convex case. Thus, both two stationary points are minimums. So the only thing we need to decide is whether or not this works for our 0, 0 point, and as for 0, 0 point, everything is just a bit more complicated, because as you can understand, the values of all partial derivatives here are minus 2. Thus, our d value is minus 2 multiplied minus 2 minus minus 2 squared, which is 0, and our rule for convexity doesn't work. More importantly, let us look at this very function. As you do remember, we've said that if the convexity rule does not work, then we do not know anything about convexity, and we should properly look at the function itself. Basically, what we are looking at, just consider, for example, two things. Firstly, the last three terms can be easily rewritten as x plus y squared, right? So let us do it. We are going to write x powered 4 plus y powered 4 minus x plus y squared, right? So for the direction, for example, x equals to minus y, the last term actually disappears, and we get quite nice 2x powered 4, which has a minimum at the 0 point, right? So at least on one direction, our 0, 0 point is a minimum. But it's easy to understand that, for example, if we consider not x equals to minus y, but x equals to y, we can easily get that our function turns into 2x powered 4 minus 4x squared, which is easy to show has a maximal value at 0 point. So as a result, we get that at this 0, 0 point we get, well, we get nothing. It is not an extremum. Not. Okay, that was a full scheme of exploring whether or not this function has extremus and finding out what these extremus are. Now we are ready to move forward to the idea and motivation of famous gradient descent here. So let us remind ourselves what we already know. First of all, we know what is the gradient. The gradient is the vector of partial derivatives. Firstly, secondly, the gradient is a pointwise concept. Basically, for each point exists its own gradient, right? The direction of maximal growth and the speed of maximal growth is also connected with the gradient. Basically, the gradient is the direction of maximal growth, and its length is the speed. Okay, that's nice. Also, let us consider for a minute the geometrical relation between the gradient and the level of the function at a given point. Let us assume the following picture here. I've drawn some levels of some function. Just we don't actually care about what function it is. It's just an example, right? We've considered this red point here, and what about the angle between the gradient at this very point with the levels of the function? Firstly, you need to understand that the angle between two curves is basically defined as the angle between two tangent lines at these curves at this very point, right? So in order to understand what the angle is, you need to understand what is the tangent line for the level of the function. In order to do it, let us remind ourselves that the level is defined by equation, right? So the equation is, for example, f towards x and y equals to c. Basically, let us try and apply the operator of the differential to the left and the right side of this expression. Thus, we get first differential of f at the left side, and 0 because, well, what is differential? Differential is the change of the function if it was a hyperplane, right? But if it was a hyperplane, it's kind of nice because the constant is a hyperplane which we do not change, thus the change of the function in the right side is 0. Okay, let us elaborate the concept of the differential here. Just write by definition that that is the sum of multiplication of partial derivatives and the change of function here. Nice. So basically what we are looking at? We are looking at the scalar product of the gradient at the point AB and some vector dx dy, which is basically the vector of the direction of the tangent line here, because what we are talking about? We are talking about the change of the two variables such as we are still at the curve with infinitesimal change of x. Thus, basically, we are looking at the tangent line here. Another way to understand it is to remember, assume that, for example, y is a function towards x. Well, just consider that we are looking at such a level that we can substitute it with a single varied function, like on our picture here. Thus, we are looking at dx derivative of y towards x multiplied by dx vector, and you can simply normalize this vector by dx. Thus, you get 1 and derivative towards x vector, which is the directional vector of the tangent line for the single varied function. Okay, so basically what we got here? Basically we got here that the scalar product of these two vectors is 0, or in other words, they are orthogonal. So we just get that the angle between the level of function and the gradient at this very point is orthogonal. That's nice. So, assume, for example, that we have to solve some kind of optimization task. For example, we have some function f, and we are going to find its minimum value. So what are we going to do if we need to find its minimal value? We need to consider where to go. What is the direction of minimal growth? As we stated earlier, it's the direction opposite to the gradient, which is anti-gradient or minus gradient, right? Let us draw the picture. So what are we supposed to do? We are supposed, first of all, we're supposed to initiate our procedure. Let us, for example, start with some point x0 on the plane or point x0, y0 here. Right? So at this very point there is a gradient which is green vector, and thus we need to go into the opposite direction of this gradient to the anti-gradient minus nabla f, and there we should somewhere choose our next point, for example x1, y1. In other words, we get our recurrent relation x vector x n plus 1 equals to xn minus some step alpha n multiplied by the gradient at the nth point. Okay, then we should reiterate this procedure and stop in case. Well, in case of what? Firstly, we can stop in case of the gradient being too small. In case of length, function stops to grow. Since you remember that the length of gradient is the fastest growth, if this fastest growth is rather small, then function is close to extremum. Well, idealistically, the extremum implies that we have stationary points, thus zero gradient, and thus this length of gradient will be 0, right? But we shouldn't hope for idealistical case, and we can assume that we have at least pretty small gradient at this very point, so we can use it as a stop condition. Or, for example, we can quit our procedure if we stabilized by the point. For example, the next point is pretty close to the previous one. That basically means that we are doing extremely small steps, and maybe it's because we are already stabilized in around our extremum. Okay, that's basically the idea and the motivation of the gradient descent. But the question here is, we are talking about some steps. What's the length of this step, right? So, well, what is the best possible strategy here? The best possible strategy here is to choose the step which is kind of the longest on this very direction of anti-gradient, right? This is a step where our anti-gradient actually is a tangent line for some level of our function. However, to understand that, that's quite easy. First of all, just assume that, for example, consider the second level we are looking at our picture. Our direction of anti-gradient intersects this level at 2 points. For the first point, the transition through this level implies that we are getting lower and lower. It's a nice thing. But for the second point, we are getting higher and higher, and that basically implies that somewhere in between these 2 points, there was ideal point, ideal time to stop going into this direction. This implies basically for any level which we intersect 2 times. So we should stop at the level which we do not intersect 2 times. What is do not intersect 2 times? Intersect 1 time or be a tangent line to some level, right? The problem here is to find this tangent line, we need to solve the system of equations which implies that scalar product of 2 gradients, gradient in previous points and gradient in the new point, are orthogonal, right? Or one gradient is a tangent line to another gradient, right? But as you can understand, partial derivative itself are not necessarily linear or nice actually functions. Thus, we get some pretty ugly equation here. So, in order to solve it, we need to start some intrinsic numerical method for solving an equation, and it takes a lot of time. It hurts our accuracy and whatsoever. It's not a good case. But okay, so ideal strategy does not work for our numerical realization. That's fine. But what we do understand about our steps? Small steps are good because we are kind of not jumping over our stop point, right? But if we are going too small, then we will be faced with extremely long convergence. We will be forced to learn a lot of time for the methods to find its extremum, right? And if we use big steps, then we are going to sort of play in first Mario level with our extremum, because we are going to jump from one big value to another big value, and from there to there, from there to there, and just hope that somewhere we will find a smaller level. Okay? That's not a nice case. Still, we are gonna have a long convergence. We are gonna have to wait a long time. So there is quite several strategies towards choosing the step of the gradient. The first one is basically constant thing, and it's kind of the idea that you are stepping not a constant in terms of the length of the vector, but constant share of the gradient, right? You need to multiply this alpha step by the value of the gradient at the point of interest, that's your current point, right? But it still kind of implies that this multiplier, this C value, should be not too small, not too big, and it's kind of tricky if you don't know what's the best answer for you. So another idea is the decreasing step, the decreasing length of step. So basically you take the first big step, then you're getting close to your minimum, then you do smaller step, smaller step, smaller step, smaller step. But as you remember in our talk about convergence of series or convergence of proper integrals, 1 divided by n, it's kind of slowly decreasing to the infinity, right? Slowly decreasing to 0. Thus basically this is kind of not the smallest steps if you can imagine. Or you can just search for some more sophisticated cases. For example, in some libraries called Wopal Rabbit, there is an understanding that you can just follow, that your step should follow some power law, but in practice you optimize only the constant multiply here and just fix all the values in this relation. Finally, we know quite a lot about calculus and optimization. We have our swords and shields. Let's try to use it in real-life data. Firstly, we need to understand something about real life. For example, assume that we have a following task. We have some objects which are described by numerical vectors x, 1, 2, 3, and so on. And we have some quantitative output for these objects, for this input data, which is respectively y1, y2, and so on. Okay, so what should we do here? We should start with some proper assumption about our data. Firstly, we start with the assumption of the class which the relation between input and output lies in. So firstly, we are looking at the input, we are looking at the output, and we decide whether or not, for example, output depends linearly on the input, or, for example, exponentially on the input, or something which implies, for example, a recurrent relation in between them. All these cases are assumptions. They are either good, either bad, and in each case you can produce some kind of model and kind of prediction for your output and input. And it can be either good, either bad, and in all the cases, almost probably you will be faced with non-zero mistake. So, firstly, what we are going to say? We are going to say that, assume that we have some kind of model, and we are going to say that that model works in the following manner. It's kind of a function which takes our input data for one object. It has some parameters, maybe more than one, which we're going to call omega. And basically, it's kind of a function from x and omega, where x and omega are always vectors of data and parameter respectively. So we need to understand the following. What is the fittest set of parameters for our given model, since the model is something that we already chose? So, in order to do it, we need to introduce some mathematics here, some kind of estimation, assessment of the fittest. We are not speaking about the biology and Charles Darwin, and we cannot wait enough time to see how model die. We need to understand what is the best in terms of numerical loss. So let us revise what we have here. We have input data, we have real output, we have our model which depends on the parameters. Assume that we have some kind of parameters fixed, then we can produce some predicted output, some output according to our model, right? We are gonna add some triangular head to our y's in order to specify that this is our prediction. Thus, basically, the difference between our prediction and our real output is the loss or some understanding of the quality of our prediction, right? But of course, we are not speaking about only direct, for example, difference in between them. We are speaking about some function on that difference. So, what's the proper function on that difference? What's the proper estimation of loss strategy? Firstly, as you understand, if we have this loss per item, per one input object, then we can sum all the input object and get all the greatest general loss, which actually depends on quite a lot of things. It depends on all inputs, all real outputs, and the set of parameters, right? But the most important thing for us is that it depends on set of parameters. And so we get this accumulated composite loss. Or sometimes it's nice to have an average loss. It somehow describes what is the error per one unit, per one object in our data. So we need to address the following question. What is the best strategy to define what is our loss function? What is g towards x? Okay, let us consider the simplest case. Let g be equal to x. Basically, the difference is the loss. One can clearly see why it is not so good, because if you are looking, for example, if one data has an error something like this, it mistakes in one side, for example, underestimates, and for the other side it overestimates, then by summation these 2 points we get 0 error, but it's kind of not the case. We get 2 errors, 2 significant errors, but our loss estimation tells us that this error is pretty much non-existent. So this strategy for G is kind of misleading. Okay, in order to avoid it, we may provide, for example, absolute value of x, absolute value of difference. That's nice, that doesn't have such bad behavior such as x, but as we now know, since we are studying calculus, the function absolute value of x has one sufficient problem here. This problem is that it is not differentiable at the 0 point, and we are talking about the gradient descent, or for example simple optimization, so we almost definitely need to address the idea that our function should be differentiable at any given point, especially at the extreme. So we need to somehow move from this non-differentiable case. So there is a nice idea to use, for example, x squared, which is a nice function with differentiable for any real values, right? The problem here is that, firstly, we are going to use it, right? That's our best choice for now, but you need to understand that in case, for example, we have some, damaged data, wind blows, people are getting drunk, whatsoever, it's kind of, you can randomly get some outlier in your data. Then by calculating your loss at this outlier, you will get extremely high error here, extremely high loss, which is kind of non-sufficient, non-interesting for us because it's a random mistake. Right? So we kind of expect to expel it during our optimization procedure. So sometimes, for example, people use piecewise strategy. So in around in the neighborhoods of the 0 point, your loss function behaves like g, like x squared, right? And for the rest of the part of these two areas which are somehow distant from the 0, you are using not x squared but absolute value of x with a proper normalization constant to provide a differentiable function. That's a kind of loss, it's called Hubbard loss, and actually implemented in various packages of machine learning. Also, the thing that we are going to discuss is the case of a non-symmetrical loss function when you kind of care whether or not you are overestimating or underestimating, and sometimes it could lead to surprisingly different best predictions. So, for example, it can lead to different parameter set. Okay. So basically, to sum up what one should expect from the chosen function, it should be differentiable in order to properly introduce our gradient descent non-negative, or either symmetrical or non-symmetrical, because we should take an inspiration from the real data or the real task we are talking about. So, to sum up it, what we have our general composite loss. We're gonna speak about averaged loss or mean squared error loss, because we are gonna use our x squared as a functions loss, and we are gonna average all our losses throughout all the data. And we are gonna also use more comprehensive non-symmetrical case. So, what we are asking you to do for the final project. We've proposed to use the house prices dataset. It's quite famous. We've slightly modified it to work flawlessly with our model. And we're gonna assume that our model is linear. It's super easy. We're just gonna have some set of parameters multiplied by different components of the input vector, right? So you need to do some basic things to understand it. The procedure is thoroughly written in the my Python notebook provided with the task in this week. This is your final project. And you need basically to understand what you need to do. You need to find function gradient, you need to implement the method of gradient descent, and the nice idea here is to play with different strategies of step choice, right? All the things that we've discussed. And then compare the results in case you are considering symmetrical mean squared error or non-symmetrical mean squared error. Maybe the results will sufficiently differ.